All right, let's dive in and actually look at the code and run it to actually find the minimum temperature observed for each weather station in the year 1800. Okay, let's see this filter in action. So go to the resources for this lecture. Again, it's that big friendly blue button in the upper right-hand corner and download two things. One is the min temperatures Python script, and the other is the 1800.csv data file, which contains our weather information. So go ahead and download those now, and when you're done, place them into your C Spark course folder, or wherever you're storing all of the stuff for this course. Go ahead and hit pause and take care of that now. When you're ready, let's go ahead and double click on mintemperatures.py and open that up in your editor. Alright, so I think it makes a little bit more sense once you see this all together. Feel free to take some time to just kind of like wrap your head around it and figure out what's going on here, but I'll walk you through it here too. So we start off with the usual boilerplate stuff, importing what we need from PySpark and setting up a Spark context that we're going to call min temperatures. And if we skip down here, we can see that we're loading up our source data file from 1800.csv into a lines RDD. We then parse that out using our parse line mapper function that we define up here. And what that's doing is splitting out each line by commas, extracting the station ID from the first field, the entry type, which is going to be tmin, tmax, or precip from field 2, and then we will extract the actual temperature value from the third field. And again, we will tell Python that this is actually a floating point numerical value that we can do arithmetic on, convert it from tenths of a degree Celsius to degrees Celsius, and finally convert that to degrees Fahrenheit. And our return value will be this composite value, this list of station ID, entry type, and temperature. So at this point we have every line of our input data converted into this structured data where the first element is the station ID, second value is the entry type, which is tmin, tmax, or precip, and the third value is the temperature associated with that entry in degrees Fahrenheit. Next, we filter out everything with the tmin values here with our filter function. So we check that entry type field in field number 1. If it's tmin, then it survives. If it doesn't, then it does not get passed on. And the resulting min temps RDD contains nothing but tmin entries. So at this point, we have an RDD that has the station ID, tmin, and the temperature. Next, we can transform that again to eliminate those redundant tmin entries, because everything's a tmin. It's no longer an interesting piece of information. So what we end up with now is a key value RDD, because we'd have these tuples that we're left with that are just station identifier and temperature in Fahrenheit. So station temps is now a key value RDD, where the key is station ID, and the values are the minimum temperatures observed for every day of the year for each station. So we're very close to what we want. All we need to do now is call reduce by key to combine together all of the minimum temperatures observed every day for each weather station ID and find the minimum value as we go. So what we're left with is a min temps RDD that has only one entry per weather station ID that contains the minimum temperature observed for the entire year. Finally, we just need to collect the results and print them out and make them look pretty and format them to just be 2 decimal points to the right of the decimal place. So let's go ahead and run this and see what it does. Go to Tools, Canopy Command Prompt, and we will run spark submit. Too much coffee this morning. Min temperatures.py. Off it goes. The usual warnings that we can ignore, and it should chug through this pretty quickly. There we have it. So the minimum temperature observed in the year 1800 for this weather station ID, which I think is Paris, was 5.36 degrees Fahrenheit. And for this other place, which I think is the Prague, is 7.7 degrees Fahrenheit. And there you have it. The minimum temperature script illustrating the use of filters and also using key value RDDs yet again. So there you have it, the minimum temperature observed in the year 1800 for 2 weather stations. We used the concept of filters, we used key value RDDs, and we used the reduce by key function to actually boil down the information we wanted for the whole year for each weather station ID. Pretty cool stuff. Now I want you to get your hands dirty. I want you to roll up your sleeves and actually dive into that code and start messing with it. Get some confidence, especially if you're new to Python, that you can make changes to this code and actually make stuff happen yourself. So here's what I want you to do. Pretty simple task. Take that code that we just wrote for the minimum temperature for the year and change it to actually find the maximum temperature observed for each weather station throughout the year 1800. So again, instead of displaying the minimum temperature found for the whole year, I want you to tell me the maximum temperature found for the whole year for each weather station ID. Shouldn't be too hard, just a couple of things you have to change in there really. So give that a try and come back in the next lecture and we can compare what you came up with to what I came up with. Okay, I hope you did your homework. You should, at this point, have a crack at actually finding the maximum temperature for the year for each weather station instead of the minimum temperature using our min temperatures Python script as a starting point. If you haven't, tisk tisk, hit pause, go give it a try. Really, the only way you're going to learn this stuff is by diving in there and playing with it and like actually messing with the code yourself. So I very strongly encourage you to give this a try. It's not hard. And if you have done that though, let's move forward and take a look at my result and we can compare that to yours and see if you got it right. Okay, let's compare your results to mine. Hopefully you didn't have much of a hard time in figuring out the maximum temperature observed at each weather station for the year 1800. It just involved a few changes. So if you go to the resources for this lecture, you can download my solution to it, which is the max temperature script. If you'd like, you can throw that into your Spark course directory and compare it to what you did and compare your results to mine. So let's open that up. All right. So you can see I didn't change a whole lot. The first thing I did though was extract and filter only the Tmax entries in my original data. So originally we were pulling out the Tmin entry types from our source weather data. This time I'm interested in the max temperatures observed on every day for each weather station, and that's what this line will now do. So we are filtering out everything but Tmax and putting that into a max temps RDD. And the rest is the same until we get to the reduction. So now instead of trying to find the smallest temperature observed out of all the minimum temperatures, we're trying to find the maximum of the maximum. So out of every maximum temperature for every day of the year, what's the maximum temperature that we saw throughout the entire year for each weather station? So instead of min, I now have a max here. So as I'm doing my reduction by key and boiling down all the Tmax entries for each weather station for the whole year, we're taking the max to find the largest value observed throughout the whole year. And from there on, it's all the same. We just collect the results and print them out. So let's see what we end up with. Spark-submit max temperatures.py. And it turns out that the same exact temperature was observed for both weather stations throughout the year as the maximum. So they're not that far apart geographically, so not too strange of a result. But 90.14 degrees Fahrenheit was the final result. And obviously that's more precision than the source data had. So if it seems like a coincidence, it really isn't. And that is the answer. So if you ended up with 90.14 degrees Fahrenheit, great, you did it right. If not, go back, compare what you did to me to what I did in the script and try to figure it out. Feel free to play around with it further too. So there's more things you could do there. Maybe keep the answer in Celsius, for example, instead of Fahrenheit, if you're more comfortable with that. So again, just roll up your sleeves, get your hands dirty. My whole point here is just to get you comfortable with messing around with Spark code and Python. So hopefully you've achieved that to some degree. That wasn't so hard, was it? So at this point, you should have a script that also computes the maximum temperature found in the year 1800 for each weather station ID. And you've had a little bit of familiarity with diving in and actually messing with some Spark code in Python yourself. So let's keep building upon what we've learned, and we'll go to another example next. So next we're going to do a really common example in Spark and MapReduce sort of books, where we're going to count all the words in a text file and how many times each word occurs within that text. Now we're going to put a little bit of a twist on this because we're going to work our way up into doing more and more complex twists on that task. But the first thing we need to do is go over the difference again between map and flat map, because using flat map in Spark is going to be the key to doing this quickly and easily. So let's talk about that and actually jump into some code later on and see it in action. Okay, for the next few lectures, we're going to be looking at your standard count the words in a text file sample that you see in a lot of these sorts of courses, but we're going to do a little bit of a twist. So we're going to work our way up from a really simple implementation of counting the words and keep adding more and more stuff to make that even better as we go along. So to start off with, though, we need to review the concept of map versus flat map. And we've talked about this a little bit in the past, but in our examples so far, we've just been using map or map values to transform RDDs. So just to review, a map function will transform each element of an RDD into one new element. So there's always a one-to-one relationship between the RDD that you started with and the transformed RDD that you end with. So for example, if we had a text file that contained the quick red fox jumped over the lazy brown dogs, broken up on different lines like that, and then we wrote a mapper that has this lambda function that calls upper on each line that comes in to make everything uppercase, what we get back is exactly the same number of entries, just in uppercase. So again, we started with 4 lines and we end up with 4 lines. The only difference is that they've been transformed in some way. In this case, they've been all changed to uppercase letters all through. And if you're curious, that's a handy little sentence in the English language that actually includes every letter of the alphabet, if you've never seen that before. Now, in contrast, flat map has the ability to blow out an RDD into multiple entries, elements from each individual source one. So you can end up with an RDD that has more elements than you started with when you use flat map. So as an example, let's see how that works. Let's say that we load up that same text file in a lines RDD, and now we're going to call flat map on it, and our mapping function is going to be the split function. So what that's going to do is split up every line into individual words based on whitespace and output multiple results, one for each word. So x.split returns a list of words, and each item returned in that list from the mapper function will become an entry of its own in the new RDD. So the words RDD ends up containing each individual word as its own entry in the RDD, whereas we only started with 4 entries in the original RDD, one for each line. And that, breaking up text by words is actually a pretty common thing to be doing with flat map, and it's sort of the obvious thing to do with it. So with that, let's jump into the code and start with our simple example of word count. And in order to make it more interesting and real, I'm going to actually use the text of a real book. It's one that I wrote, so I have the rights to include it in this course. So let's go on and go to the resources for this lecture at this point and download both the book.txt file and the word count script, and we'll start playing with that right now. So again, if you haven't already, go to the resources for this lecture and download the word count Python script and the book.txt file, which contains the text of an entire book, and place it into your Spark course directory. Hit pause if you need to go take care of that right now. And when you're ready, double-click on the word count.py script and we'll take a look at it. Alright, very simple stuff, but the key point here is using flat map instead of map, so we're going to do all the typical boilerplate stuff to set up our word count Spark application. And we'll do our typical text file call on the Spark context to load up the text of the book, 1 line at a time. And the way this is actually broken out, it ends up being about 1 paragraph per line. So that's a lot of words on each line, not very useful. Now, since we want to count up how many times each word occurs in the book, we need to bust that out by word, and that's where we're going to do our flat map function that will take every individual line of text, where a line represents a whole paragraph in our example, and our lambda function called split, which just breaks that up based on whitespace into individual words, and it will put that list of words into the words RDD. And then we can very simply call count by value, which is a way to very easily and very quickly in Spark get a count of how many times each unique value occurs. So for every white space separated word in our book, we will get a count of how many times that word occurs. And we will get the results in the word counts list here. And this is just standard Python code here. There's nothing Spark specific about it. We're just going to go through every single word in our list of words. And this just takes care of some encoding issues. So in case something was encoded as UTF-8 or Unicode in our original text, this makes sure that we can display it okay on our terminal in our command prompt by converting it to ASCII format. So it also says that we're going to ignore any conversion errors that might occur in the process of trying to convert from Unicode to ASCII. So this is just a way to make sure that we can display these words without errors, even though they might contain special characters. Just a little Python trick for you there. And if that comes back successfully, we will print out each word and the number of times it occurred. So let's go ahead and run this. Spark-submit wordcount.py. Off it goes. Usual warnings. And that was pretty quick for an entire book. And there's some results. So, we can see, for example, the word extort only appeared once, the word kinds appeared 3 times, and the word other appeared 71 times in this book. But if you look at these results carefully, they're not entirely helpful. Now remember, we're only splitting based on white space here, so we're not really just getting words counted up here. We're getting all sorts of combinations of words with their punctuation underneath them. So web page, followed by a comma, followed by a comma, only counts as one word of itself. Click followed by a comma, that counts as a unique word as well. And Here we have click followed by a quotation mark that also counts as its own unique word, and that's not what we want, right? Like punctuation shouldn't count. Similarly, we also have uppercase and lowercase affecting things, so we have all uppercase leeches, which is probably part of some section of the book, and that would count as its own unique word compared to lowercase leeches. And again, that's not very helpful. We want to combine all of the words together that are the same word regardless of punctuation or capitalization. So we're going to have to improve on this a little bit. The other thing too is that these aren't displayed in a very helpful manner, right? Like ideally we would want to get a list in sorted order, sorted by the most common words, so we could very quickly see what the least frequently used words are and the most frequently used words are without having to search through the entire thing. So we're going to build on this, like I said, and make this script even more useful. So let's take another round at it and try to improve on it in our next lecture. All right, we got some results there, but they're not that great. We still need to clean our data a little bit more, and we're going to do that next in our next lecture. So let's build upon this word count example and make it better. So a main problem in our initial results from our word count script is that we didn't account for things like punctuation and capitalization and things like that. So there's fancy ways to deal with that problem in text processing, but we're going to use a simple way for now, just using something called regular expressions in Python. So let's show how that works and actually run it and see it in action. All right, so if you recall, we had a first crack at counting the number of times each word occurred in our book before, but the results weren't that great. We had each individual word that had different capitalization or punctuation surrounding it being counted as words of their own. And that's not what we want. We want each word to be counted only once, so no matter how it's capitalized or what punctuation might surround it or various variants of the word, we don't want to have duplicate words showing up in there. Now, there are toolkits you can get for Python like NLTK, the Natural Language Toolkit, that have fancy, very complicated ways of normalizing text data like this and automatically figuring out what words are the same. But we can sort of do a more simplistic attack at it and use a regular expression in Python in order to convert words into some common format and strip out all of the extra punctuation that we don't care about. So not really a Spark specific thing, but it's a very useful trick to have in your back pocket, especially when you're doing text analysis. So let's take a look at the code and see how that works. Okay, let's try and improve upon our word count script. So in the resources for this lecture, you should find a word count better Python script. So hit pause and go download that and save it into your Spark course folder. And as usual, let's double click it and take a look. All right, so you see this is a little bit more complicated than what we had before. A lot of the same stuff, but the main difference is that when we're calling flatmap, instead of just using a lambda function that calls split to just split up each word in the line based on white space alone, we're going to pass in an actual function here called normalize words. And normalize words does something a little bit fancy, so let's talk about that shortly. Basically, we're setting up a regular expression, and that's what RE stands for. You see that we added import RE to the top of the script here. And regular expressions, if you're not familiar with them, are sort of a language of their own for text processing. And it allows you to write little strings that define how to split up a string into other values or transform it. So it's sort of a very shorthand way of doing some text processing. And in our case, we're going to call re.compile, and this is the magic little string that means I want you to break up this text based on words. And the W plus, capital W plus, indicates break it up based on words, and the regular expression engine knows on its own how to do that and strip out punctuation and other things that aren't really part of words automatically. We'll tell it that this may have Unicode information in it, and then we will split it up, based on what the regular expression identifies as individual words, and transform those all to lowercase. So the regular expression will take care of breaking up the words, taking account of all the punctuation, and then we're going to force that to be lowercase so that we don't get different results for different types of capitalization on each word. And that should produce better results, so let's give it a try. Again, it's not really a Spark specific thing, but it's just a good tool to have when you're doing this sort of analysis. So we're going to run spark submit word count better.py. Let's see what it does. And there we go. That looks a lot prettier, doesn't it? So we don't have a whole lot of weird capitalization and punctuation going on. This looks like much more usable results. So clicks actually shows up 3 times, the word out 161 times, and so on and so forth. Workaholic only once. I guess that's a good thing. And you can scroll through this and see, you can eyeball what words tend to be popular, but the last thing we need to do is make this more usable by actually sorting it by what words are the most popular or the least popular. And the main problem there is that if we were to just sort this list as is, it would sort it based on the word, right? What we really want to sort on is the count that's after it. So we're going to have to shuffle these results around a little bit before we can sort them the way we want. And let's go over how to do that in our next lecture. All right, things are looking better now. We've accounted for all the capitalization and punctuation weirdness for the most part in our data there, and we were getting some results that are starting to look interesting. But to really be able to interpret them better, we need to be able to sort them the way we want so that we can see the words that are least frequently used and most frequently used more easily. So let's do that next. Okay, let's do one more round of improvements on our word count script. We're going to now sort the results the way that we want, and doing that's a little bit tricky, so let's walk through how that's going to work. Okay, so the last thing we need to do is to sort our results of word count by something useful. So instead of just having a random list of words associated with how many times they appear, what we want to do is get the least used words at the beginning of our list and the most used words at the end, and that should give us some actually interesting information to look at. So to do this, we're going to need to manipulate our results a little bit more directly, so we can't just cheat and use count by value and call it done. So first thing we're going to do is actually implement what count by value does by hand the hard way, so we can actually play with the results more directly and stick the results in an RDD instead of just getting a Python object that we need to deal with at that point. So the way we do that is we take our map of words and we use a mapper that just converts each individual word into that word and the value of 1. And this is a very similar trick to what we did in the earlier script where we computed the average number of friends by age in a fake social network, where we just use that extra number 1 there as a way to count up how many times something occurs. So then when we call reduce by key, our keys here are the individual words, and for every time that word occurred, the number 1 will get added in as part of the reduction. So we're passing in a lambda function that just says add these two things together, and by doing so we'll end up getting values that just keep adding up, 1 plus 1 plus 1 plus 1 for however many times that word occurs. So keep in mind, just to walk through it one more time, we're starting off with a plain old RDD that contains words, every word that appears in the book. We are then mapping that so that every word is instead a key value pair of the word and the number 1. We then reduce that by key, so we aggregate together every time that each individual word appeared, and we use this lambda function to say we're just going to add the values together for each individual key. So that just keeps adding up 1 plus 1 plus 1 plus 1 for however many times that word appeared. So that has the same effect as count by value, except the result gets stored in a new RDD called word counts instead of a Python object that we need to then manipulate. Makes sense? If not, hit pause, stare at this some more. Like I said, it's a very similar trick to what we did in an earlier example, so hopefully that makes a lot of sense. Now, what we have at this point is an RDD that has words and the number of times they appear in it, but we want to sort by the number of times each word appears. So before we sort, we need to flip that around. So we're just going to map things so that our keys becomes values and our values become keys. So we start off with the keys being the words and the values being the numbers of time that word occurred. We're going to flip that around in this mapper and make that instead the number of times it occurred followed by the word itself. And then we can chain together a call to sort by key to sort the final RDD that we store in word count sorted by the number of times it occurred. Okay? Makes sense. It's pretty straightforward. We're just flipping things around so we can sort it the way that we want to. Let's take a look at the code. Okay, let's do our last little improvement to our word count script. So usually this is a really simple example in most textbooks, but we're going to make it something a little bit more interesting. So if you haven't already, go to the resources for this lecture and download word count better sorted.py. And let's open that up in your favorite Python editor. All right, so what have we done differently here? Well, we talked about it in the previous slide, so here it is all together. Basically, instead of just cheating and calling count by value, we're going to actually do that by hand. So we're going to do a mapper where we're going to transform every word into a key value pair of the word and the number 1. And then we reduce by key. where we just add them all up. So for every unique word in our words map from our words RDD, we'll add up every instance using this addition lambda function, and we end up with a key value RDD where the keys are the words and the values are the number of times that word occurred. Now we're going to flip that key value pair around so that the key is the count and the value is the word, and then we can sort by key to get a sorted list by the number of times each word occurs. Finally, we'll just grab the results through a collect action. That'll kick everything off to actually execute, and we'll go out and print out in a slightly different format just the word followed by a colon, couple of tabs, and the count. So let's go ahead and run that and see it in action. Spark-submit. Word count better sorted.py. And this should look a little bit better, a little bit more useful, a little bit more interesting. Let's see what comes up. All right, so indeed, we are sorted by the number of times each word occurred, and the most popular word in my book is the word you. Wow, I must be quite the egomaniac. Oh no, wait, you, it's not me. It could be worse, it's not me, it's you. That's a good thing. To, your, the, a, of, and that, all the words you'd expect to show up a lot in any book, really. And when we start to get into more interesting words, business turns out to be the most popular word, which makes sense because it is in fact a book about starting your own business. Now, I do want to point out a couple of bad things here, though. The S is not a word, and what's up with that? So, well, our regular expression isn't perfect for breaking up words. It turns out that it was probably splitting out the S from contractions like its or Frank's, apostrophe S things. So the S got split out into its own word. So, if you did want possessive forms of a word to count as different words, that would be an issue. And also you want to make sure you account for weird results like that when you're analyzing your results. Again, a more sophisticated natural text language processing toolkit like NLTK would do a better job of that, but it's kind of overkill for what we're trying to do. But it's a good lesson in that your results in data mining or machine learning are often, well, they're always only as good as your input data, right? So a big part of getting good, meaningful, actionable results out of any data analysis you do is going to depend a lot on your ability to clean the data that you're using beforehand into the form that you want. So always look at your results skeptically and be on the lookout for weird things like S and T just showing up, because that's just coming out of contractions, it turns out. Anyway, a little bit of a digression there onto machine learning and data mining in general. Always make sure you clean your data. It's just as important as everything else. All right, and with that, we have a pretty good word counter script. We've actually gotten rid of at least the most egregious forms of splitting on things incorrectly, and we've sorted it by useful results. So, hooray! Let's move on to our next set of examples. All right, I'm pretty happy with those results all in all. We got some real insights into the nature of this book by studying the words that are most frequently occurring in it. So, it's looking pretty good. It's not perfect, but hey, it's good enough for my needs. We've learned a lot along the way here. We've learned about flat map versus map. We've learned about some sorting tricks that you can do with RDDs. And we've learned about, different ways of dealing with regular expressions to cleanse text data. So that's kind of a quick and dirty way to handle some text processing tasks that you might run into in the future. We are collecting a pretty good collection of scripts here. So, make sure you keep everything in your Spark course directory somewhere safe. There's going to be a lot of useful examples in there that you're going to want to refer to again later on, I suspect. So let's move on. Okay, at this point in the course, I think you've seen enough examples and had enough concepts that I can finally set you loose and have you try to write your very own Spark script from scratch. Now, I realize this might even be your first Python script ever, so I'm going to keep it pretty easy, and I'm going to give you a lot of tips on how to be successful with it, so don't be afraid. But let me introduce the problem at hand and give you some tips you need for success, and we'll set you loose. Okay, it's time to actually apply what you've learned so far and write your own Spark script. I'm going to start you off with a pretty simple example here, just to get your feet wet. And what you're going to do is go to the resources for this lecture, and you'll find a customerorders.csv file. And this just contains some random fake data that I generated. And the input data in that file is going to look like this: comma-separated fields of a customer ID, an item ID, and the amount spent on that item. Okay, and what I want you to do is write a Spark script that consolidates that down to the total amount spent by customer ID. So in this example, if we see customer ID 44 appears twice and bought two items, one for $37.19 and one for $40.64. So our final output should display something like customer ID 44 spent a total of $77.83. And similarly, customer ID 35 spent $78.97 based on these two items. And customer ID 47 in this example only bought one thing for $14.98, so that's all that gets displayed for that customer. Okay, so what should your general strategy be? I'll kind of help you think through how to attack this problem. First thing you want to do is write a map function that will read the input data and split it up based on comma delimited fields, and we've done that before, so go back and look at some of the other examples in your Spark course folder for a reminder on how that works. And then you want to map each line to key value pairs of customer IDs and dollar amount spent per transaction. And since we're going to structure this as a key value RDD, that allows us to use reduce by key to then sum up all of the amounts spent by customer ID. And finally, all you have to do is call collect on the resulting RDD that reduce by key gives you, and print out the results. So these are all things you've done before in this class and seen through example. All you have to do is put it together and create a new script that does this. Now a few useful snippets of code just to make it even easier for you. Again, I want you to be successful here. This could be your first Python script ever, I recognize, so I want to make this as simple as possible. Some things you'll find useful in your mapper function are if you do a line.split by a comma, that will split up a comma delimited line of text into a new RDD called fields. That contains each individual field between the commas. And of course you can call line and fields whatever you want. Those are just arbitrary names that we're using for the RDDs in question. And one thing I want to make sure that you don't get hung up on is, since we're going to be doing some math on these results and adding up dollar amounts, we need to make sure that when you're parsing these results in your mapper that you are telling Python that these are numeric fields. So remember, if you're actually parsing this out and extracting the customer ID as field number 0, you might want to tell Python that that's actually an integer value and not just a string. But even more important is that you tell it that field number 2, the dollar amount, is a floating point decimal number. Otherwise, you won't be able to add them up later on. So keep that in mind. And with that, I will set you loose. Let's see what you actually get done and have at it. We'll show you the solution in the next lecture, but please give it a try yourself first. All right, good luck with your assignment. I'll show you my solution in the next lecture, so if you want to compare your results to mine, you can do so, but no cheating. Please try it yourself first. Very important that you get your hands on here and get the success of actually writing your own Spark script from scratch under your belt. So good luck. I'll see you in the next lecture. All right, did you do your homework? I hope so. Hopefully you have a running script right now that adds up the total amount spent by customer in my little fake data set there. And you were able to draw upon our previous examples, hopefully, to be successful. So let's compare your implementation to my implementation and your results to my results and see if they match up. If not, hopefully you'll learn a little bit something from it. And when we're done, I'll introduce your next challenge. Let's have a look at my solution here for the total spent by customer problem. And if you go to the resources for this lecture, you should see my total spent by customer script. Feel free to download that and put it into your Spark course folder, alongside with what's hopefully your own solution to this problem and the book.txt file that you should have from the previous lecture. So let's go ahead and open that up when you're ready. And here's my take at it. So it is a very simple script, but again, the idea was just to get you into the practice of writing your own Spark programs. And even if it's a simple one, this is a big accomplishment if it's your first one. So let's go through how I did it. And if you had any trouble with it yourself, you can compare your code to mine and kind of see what might be different. So the usual boilerplate stuff here. Hopefully that didn't trip you up too much. The only thing I did differently was really set a different name, which doesn't matter that much for what we're doing. And I wrote a mapper function for the original input lines that uses those hints I gave you in the previous lecture. I called split with a comma to actually split up my comma separated value data into individual fields, and then I extract them as key value pairs, where the key is the customer ID cast as an integer and the value is the amount spent for every line, and that is cast as a floating point numerical value so I can add them up later on. Getting into the meat of the program itself, we start off by calling sc.txt file in our Spark context to load up the customer orders CSV data file. That goes into our input RDD, and you could call that whatever you want, of course. Then I call map on that using our extract customer price pairs function that I described earlier, which just creates key value pairs of customer IDs and amount spent. And we're going to save that into a new RDD called mapped input. Now, a common error that I see people do is forget to assign that to a new RDD. You have to remember that if you call map on an RDD, it doesn't do it in place. It creates a new RDD that you need to assign to something. So make sure that you did that. And now that I have my mapped input RDD, I can call reduce by key with a lambda function that simply adds up all the values encountered for a given customer ID. So again, our key is the customer ID, our value is the amount spent, and we're just going to add them all up using this lambda function. So hopefully the earlier examples you had of using reduce by key helped you to figure out the syntax for doing that. And we put our final results into the total by customer RDD. And to get that into a Python object that we can step through and print out, we call collect, which is an action on that RDD and forces Spark to go out and actually do it all. And then we just iterate through every result in the results object that was returned and print them out. So let's go ahead and run that and see what it looks like. Spark-submit total spent by customer.py. Off it goes. And there you have it. So that's my take at it. I try to keep the code as simple as possible, but there are some obvious things you could do to make it even better. So if you actually did some fancy formatting in the output in order to contain the decimal places to 2 after the decimal point, bonus points for you. Good job. I didn't do it here just to keep it simple. But there's your answer. Obviously, it's all random results. There's no real meaning here, but, the way to interpret this is, for example, customer ID 84 spent $4,652 in total in our entire data set here, and so on and so forth. Now, what would be more useful from a pragmatic standpoint would be if I sorted these results based on amount spent. So that is your new challenge. You're not done yet. I want you to go back and actually add some more code to sort these results by amount spent so I can easily see who's the cheapest customer in my database and who is the biggest spender in my database of fake order data. And you can look at some previous examples back when we did something similar. So hopefully you can draw on that to figure out how to do this. Remember, we flipped the orders around and called sort by key in a previous example. See if you can do the same thing here. So again, your challenge, extend the script even further to print out the results sorted by amount spent. So let's let you have a crack at that. And in the next lecture, I'll show you how I did it. Okay, so one more little twist. I want you to sort the results. So again, draw upon our previous examples to do that. And let's see how you do. In our next lecture, I'll show you my solution, and you can compare your results to mine. Okay, let's take a look at my implementation of sorting the results for the total amount spent by customer and compare it to yours. Let's have a look. All right, so before I show you my solution to the total spent by customer sorted solution, sorted by amount spent, if you got this to this point and you haven't actually tried this yourself or been successful and you got stuck, let me give you one more hint. If you look at the word count better sorted script that we used in the previous example for doing word frequency counts sorted by word frequency, we do something very similar in there. So if you got stuck, have a look at that script and give it another try first before you peek at the answer here. All right. Otherwise, go ahead and download the total spent by customer sorted script from the resources for this lecture, and you can compare your solution to mine and see what you might have done differently. There's more than one way to do these things, so just because I did it one way doesn't mean you can't do it another way. As long as it works, that's what matters. So you can see all I really did was add a couple of different lines here. So when I have my total by customer RDD here, which is just the key value RDD of customer IDs to total amount spent, if I want to sort that by the value, first I need to flip it around. So we call a mapper here that has a lambda function of x and y for the key value pair coming in, and it flips it around so we end up with y and x. So that makes our values our keys and our keys our values. So now we have this flipped RDD that contains as the keys the amount spent and as the values the customer IDs. And it might seem a little weird to have, an RDD where you have multiple keys that are the same thing, but we're not doing any reduction, so it turns out to be okay. And now that we have our RDD in that format, we can call sort by key on it to actually sort by our new keys, which are the amount spent. And then we can iterate through that RDD, collect the results, and print them out. So that's all there is to it. Compare that to how you did it. And let's go ahead and run it. Spark submit. Total spent by customer sorted.py. And off we go. And so it turns out our biggest spender is customer ID number 68, who spent $6,375 and some change. So there you have it. Another little example of doing a little bit of a two-stage extra thing with an RDD there. We computed our results, flipped the RDD around, and sorted it the way we wanted to. So if you got this far and you were able to code this up on your own, congratulations. This is a more advanced example, so you're far along the way of becoming a real Spark developer. Let's move on. Okay, I hope you were successful in writing those couple of scripts there for analyzing some fake customer order data. Not very complicated stuff, but hey, if you were successful, congratulations. You're now an official Spark developer. You've actually written some real Spark code that does real data analysis. That's a big deal. Congratulations. But we're not done yet. We're going to keep on looking at some more examples and start building up to more and more complex problems. So let's keep going. All right, let's start working our way up to some more advanced and complicated examples with Spark. Now, like we did with the word count example, we're going to start off with something pretty simple and just build upon it. So let's take a look at our next example, which is going to have us looking at finding the most popular movie in our Movie Lens dataset. All right, let's go back to that Movie Lens data of movie ratings. And what we're going to do is figure out what the most popular movie in that dataset is. And we're going to start off pretty simply and kind of build upon a more complex example here. But for now, let's start by reviewing the data format of the Movie Lens dataset, the u.data file. As you might recall, it consists of, on each line, a user ID, a movie ID, a rating, and a timestamp. So each line says this user watched this movie, gave it this rating, and did it at that time. And our task is to just figure out what movie was watched most often. So which movie ID appears most frequently in its entire data set. Now, this isn't a very hard thing to do. In fact, if you want to go give it a crack yourself, feel free. But we'll take a look at the implementation that I came up with and get that to run and see what we come up with. Off to the code. All right, let's have a go at finding the most popular movie in our Movie Lens dataset. So off in the resources for this lecture, you'll find a popular movies Python script. Download that, put it in your Spark course folder. Hit pause and I'll wait for you. Come on back when you're ready. All right, let's open this up. So what we're going to do is just print out a list of all of the movies and the times that they appear and sort them based on how often they appeared. So pretty simple script here. There's nothing really new in this example, but there will be when we build upon it. But let's walk through it real quickly just to reinforce some of the stuff we've learned already. Your standard boilerplate stuff up here. We're going to open up the u.data file, which contains the user ID, movie ID, rating, and timestamp for every individual rating within that data set. Then we're going to call a mapper that just simply splits it out and pulls out the movie ID from field number 1. So what we end up with is just a movies RDD that is nothing but a list of movie IDs. And each movie ID may occur many, many times. Our task is then to just count them up. So notice that we're actually outputting a key value pair here. We have the movie ID and then the number 1. And what we can do then is use reduce by key and just add up all of those ones together to get the count of how many times each movie appeared. So let's go over that one more time. Our mapper is going to extract the movie ID, put it in a key value pair where the key is the movie ID and the value is the number 1. We will then call reduce by key, which will group together and aggregate all of the values seen for each individual movie ID and add them all up. So all those ones get added up together and we end up with the final count of how many times each movie appears within our Movie Lens dataset. But we're not done yet. So at this point, we have a key value RDD where the keys are the movie IDs, but we want to sort it by the values. So we're going to use that same trick we did before where we flip things around so that the values are the keys and the keys are the values. So that's what this line here does with moviecounts.map lambda xy becomes yx. But we end up in the flipped RDD is now the count as the key and the movie ID as the value. We can then sort by key in order to sort our RDD by the count of number of occurrences, collect the results and print them out. So let's see what we get. If you want to hit pause, if that didn't make sense, if you stare at this for a while, it will. do what you gotta do to understand it. But let's move on. Canopy command prompt, and we will run this thing. Spark-submit popularmovies.py. Off it goes. And there we have it. Sorted by number of occurrences, it turns out that the most popular movie in our data set was movie ID number 50, which was watched 583 times by people in that data set. Well, that's all well and good, but what the heck is movie ID 50? That's not very helpful, is it? Well, we can go look it up by hand and do it the hard way. I mean, if we go into the ML100K dataset here and open up the u.item file, you might have to right-click that and say open with, and open with, and select WordPad, so you can actually look at it. We can scroll through here and see what movie ID 50 actually is, and it turns out that 50 is Star Wars from 1977. Not too big of a surprise, Star Wars being the most popular movie when this data set was created in 1998. That was certainly one of the most popular films, and certainly popular with the people that tend to frequent websites about machine learning and movie recommendations on the internet. So there you have it, Star Wars, the most popular movie, but we want to make this better. So wouldn't it be great if I could just automatically print out the name of each movie instead of the ID? So in our next lecture, we'll go through how to actually build up a table of movie IDs to movie names and broadcast that table to every node that might be running your Spark job, so we can actually display the names instead of the IDs and make these results more useful and more human readable. So we'll do that next. All right, that was a pretty simple example, but the results we got kind of reflect the work that we put into it. It's not very easy to interpret the results because we have to go look up what those movie names are. So let's take care of that, and we'll start to introduce some more advanced concepts in Spark in the process. Okay, let's figure out how to actually include information about the names of those movies with our Spark job and include them in such a way that they'll get broadcast out to the entire cluster. We're going to introduce a concept called broadcast variables to do that. So let's see how it works. All right, so let's make this result a little bit better for our most popular movie script, and we want to display movie names and not just the ID. So there are a few ways we could go about doing this. I mean, the most straightforward method would be to just read in the u.item file that we looked at to look up what movie ID 50 was and see it meant Star Wars. And we could just load up a giant table in Python and reference that when we're printing out the results within our driver program at the end. And that'd be fine, but you know, what if our executors actually need access to that information? How do we actually get that information to the executors? You know, what if one of our mappers or one of our reduce functions or something needed access to the movie names? Well, it turns out that Spark will sort of automatically, magically forward any Python objects that you might need for your mappers or reducers to complete. And that can be very handy, but it can also be very inefficient. If that table were very massive, you'd end up transferring that table across to all of your executor nodes every time it was needed. And that, if you have a big table, that can add up quickly and cost you a lot of performance. But Spark offers a way to actually just transfer information once to every executor node in your Spark cluster and keep it there. So if you do know you're going to need some lookup data or some other data or any kind of object really on the various nodes of your Spark cluster, there is a way to do that efficiently and send it up there once and just keep it there handy so it can be referenced whenever needed. And that is called a broadcast variable. So Spark offers something called a broadcast object, and the way it works is you take your Spark context object and you call broadcast on it, and as a parameter you will ship off whatever object you want to broadcast to every node, and it will do all the work of serializing it and sending it across the wire and making it available to every executor node in your cluster. And then from your code, you just call .value to actually retrieve the object from the broadcasted object. And it'll make a little bit more sense when we look at it in an example, so let's go off to the code and actually make that happen. So let's see how broadcast variables let us transmit the table of movie IDs to movie names to whatever nodes our job might be running on. So in the resources, look for the Popular Movies Nicer Python script. Save that to your Spark course folder, and we'll open it up. Okay, you can see I've added a few things to our previous script here. The First being this load movie names function, and what that's going to do is create a dictionary in Python that maps movie IDs to movie names. And if you're not familiar with dictionaries in Python, they're like hash tables or hash maps or maps, depending on what language you might be coming from. But the general idea is that you can reference them in this fashion. Basically, you have a dictionary and you have brackets in which you have a key value, and that will let you either assign a value to that key or retrieve a value from that key. So it's kind of like a little mini key value data store, and that's not a new concept in this course for sure, but it's a native way of doing it within Python. So if we walk through this, we initialize a movie names dictionary as being empty here, and those curly brackets signify an empty dictionary, so just so we can set it off and kind of tell Python that movie names is in fact a dictionary. We then open up the u.item file, and we will go through every line in that file. And you notice we're actually doing this within Python itself. There's no Spark code going on here to do it. We're just stepping through this file one line at a time, splitting it up based on its pipe delimiters, and then we extract the movie ID, cast it as an integer, and use that as the key for our dictionary, and assign that to the movie name, which lives in field 1. We then return the entire movie names dictionary object to whoever called us. So moving on, we have our usual boilerplate stuff here, and the first thing we're going to do is create a name dict object that comes back from Spark Context Broadcast. So this is going to call our load movie names function, which returns a dictionary in Python that maps movie IDs to movie names, and it's going to broadcast that to every node of our cluster so that it's available when needed. All right, now everyone else on the cluster is going to refer to this as nameDict because that is the object that's been broadcast. So from now on, we're not going to use that movie names object. We're going to use nameDict. All right, the rest is the same. For a little bit here, we're just going to, in our driver script, load up the u.data file, call a mapper that will split it up and create key value pairs of movie IDs to the number 1, and then count them all up using reduce by key, just like before. And then we flip them around because we want to sort by the number of times each one occurred, and the results end up in sorted movies. Now we want to look up the sorted movies and replace the movie IDs with names. And here's where it gets interesting. So now we have a mapper that, as its lambda function, takes in each key value pair, where the key is the count and the value is the movie ID at this point, and our mapper will replace that with a new key value pair, where we're using the nameDict object that was broadcast to every node. We call value on it in order to retrieve the original dictionary object and use that to look up the name for that given movie ID. So our mapper is taking a key value pair of count and movie ID and transforming that into a movie name and account using our nameDict broadcast variable. Okay, and we can do this within a mapper only because we broadcast that to every node ahead of time. If we were not using a broadcast variable, it would still work, but it would end up transmitting that entire dictionary across the wire, possibly more times than it would need to. At that point, we can collect the results and print them out, and this time our sorted movies with names RDD will actually contain movie names instead of movie IDs and be more readable. So let's run that and see it in action. Spark-submit. What do I call this again? Popular movies nicer.py. And there you have it. Much easier to make sense of that, isn't it? So Star Wars is the most popular movie, and now that we can actually tell what things are, it's a lot easier to figure it out. So as of 1998, when this data set was created, Contact was pretty hot, and not too surprising because it had just come out the year before. Fargo was still hot. It's a good movie. Return of the Jedi, Liar, Liar. Again, kind of a surprise. And later on, we're going to be looking at similarities between movies and movie recommendations using the same data set. So if you start to see some of these same titles appear again, don't think the results are too weird. Remember, these were hot movies back in 1998. So just because you see some movie being similar to The English Patient or to Liar later on, that shouldn't surprise you because in the context of 1998, it may have made perfect sense. But anyway, that's an example of using broadcast variables in Python, in Spark. So you can actually transmit information to every node on your cluster and do that efficiently. Now, again, we are just running this example on one computer because we set the master to local when we created the Spark configuration. But if you were to actually run this on a cluster, which we'll do later on in this course, it would have actually transmitted things to every node. So we're just doing this for the sake of illustration, just to kind of get you introduced to the concept of broadcast variables, because they are a useful concept in Spark and you will definitely be using them. All right. And there you have it, the most popular movie as of 1998, at least when that data set was acquired. Not too much of a surprise, but hopefully you've discovered how a broadcast variable works and how you can use that to actually share information efficiently across all the nodes in a cluster. Okay, so believe it or not, there's actually a publicly available data set out there where someone actually figured out all the appearances that Marvel superheroes had with each other in different comic books. And we can use that to figure out relationships between superheroes in the Marvel universe and other aspects of them that we might find interesting. So let's start off with a more simple example where we just try to find the most popular superhero in the Marvel dataset. Is Spider-Man or the Hulk the most commonly appearing superhero in Marvel comics? Well, the answer might surprise you, so let's go dig in and find out. All right, time to get to the fun part of the course. So we have this data set of Marvel superheroes. Let's figure out who the most popular superhero is in the Marvel universe. And we actually have a social network that someone constructed of superheroes just by looking at what comic books people appeared in together. So the idea is that if a comic book character appeared together with another comic book character in the same comic book, they're considered to be friends, if you will. They have a co-occurrence, and they are therefore connected. And you may have people connected in complex patterns here. So this is really like a social graph that we're dealing with here. So let's say, the Hulk appeared in a comic book that had the Thor in it, and he also appeared in another comic book that had Iron Man in it. But maybe Iron Man and Thor appeared together, but, they never had all three of them together in the same comic book. And maybe Spider-Man's off to the edge here, and maybe he appeared with the Hulk, but never appeared with Thor, never appeared with Iron Man. So these complex relationships going on that exist in these networks. But we're going to start with a simple example and just try to figure out who's the most popular superhero. And we're going to define that by who is the superhero that appears with the most other characters. Okay? So let's take a look at our input data. Basically, there's two files that we're going to include here and take a look at. One is called marvelgraph.txt, and this is something I prepared ahead of time. And the format here is just a given superhero ID, followed by a list of all the superhero IDs that character appeared with in other comic books. So every line has the first entry being a given hero, followed by a list of all the other heroes that they appeared with, and so on and so forth. Now, an important point, a hero may span multiple lines. So in our source data, they would actually break really long lines up into multiple lines, and that's been carried along here. So you can't just count up the number of entries and be done with it. We actually need to aggregate things together, as we've seen so many times before in this course. We also have a Marvel names.txt file that maps superhero IDs to actual human readable names. So for example, hero ID 5306 is Spider-Man / Peter Parker. We've probably heard of, but there's also a lot of more obscure characters in there too. I don't know who General Yuri Spetsborough is, or Sphinx, or Anton Spurzel, or anyone, but the Marvel universe is pretty huge, it turns out. So there's an introduction to your format of data. We have a lookup table of IDs to hero names, and then a graph file that maps each superhero ID to all the other superhero IDs that they appeared with. So our strategy for finding the most popular superhero, or more specifically the one that had the most appearances with other superheroes, the most co-occurrences, we're going to start off by parsing out our file and map that input data to a key value pair RDD of hero ID to number of co-occurrences per line. So we're just going to count up how many other heroes they appeared with per line. And since we can actually have heroes that span multiple lines, we're going to need to add them up using reduce by key. And that will give us the final count of how many occurrences by hero ID exist. And then, since we want to find the most popular superhero, we're going to have to flip that around. So like we've done before, we're just going to swap the keys with the values and end up with a key value RDD of the number of occurrences as the key and the hero ID as the value. And then call max on that RDD to find the hero with the most co-occurrences. Finally, we'll look up the name of the winner and display the result. So let's look at the code and run it. All right, we have our general strategy and how we're going to figure out who the most popular superhero in the Marvel universe is. So let's dive into some code and see how it all comes together. A little bit more of a complicated example than we've done in the past, but you should still be able to wrap your head around it pretty easily. All right, let's dive into the code for finding the most popular superhero in the Marvel universe and get our answer. Who will it be? We'll find out soon. Well, let's find out who the most popular superhero is and turn this into some code. So, go to the resources for this lecture and you're going to download 3 things. The Marvel graph.txt data file, which contains our social network of superheroes, and our Marvel names.txt file, which maps superhero IDs to human readable names. And finally, get the most popular superhero script. Download all of that into your Spark course folder. Hit pause, go take care of that right now, if you haven't already. And then we'll open up most popular superhero.py in your Python environment. All right, let's see what's going on here. So the usual stuff, and let's skip down to the meat of it. So the first thing we're going to do is load up our names file into an RDD called names using sc.txt file. Now we're going to do this name lookup a little bit differently than we did in the previous example. So instead of using a broadcast variable, I'm going to store the superhero ID to name information as a key value RDD instead. And that too can be used across different nodes on your cluster if necessary. So just another way to solve the same problem. So what we do is we load up that text file and then we use the parse names function to map it from lines of input data to actual key value pairs. And if we look at what parse names does, it splits it based on the / delimiter, extracts the superhero ID, stores it as an integer as a key, and then after encoding things into UTF-8 format as a string, stores the superhero name as the value. So at this point, names RDD is a key value RDD, where the key is the superhero ID, the value is the human readable and displayable name of that superhero. So we'll use that later. Next, we load up the graph itself, the social graph of superheroes, into a lines RDD because it's just containing raw lines of input. And our mapper will turn that into something more useful with the count co-occurrences function. And that's going to split up each line based on white space and return key value pairs, this time of the superhero ID, which is the first ID in the list of each line, followed by just the number of elements found in that line, subtracting 1 to account for that first entry. That's the hero ID that we're talking about. So the output of this will be a key value RDD, where the key is the superhero ID and the value is the number of times that hero occurred with other heroes within this line of data. Now remember, heroes can span multiple lines, so we need to call reduce by key next to actually add them all up together. So in the case where we have more than one line for a given hero, our standard lambda function here for combining things together in a reduce operation, we'll just add them all up. So if we have 2 different entries for, superhero ID 5, it will get the counts for each and add them together and reduce them into a single entry here. So now we have total friends by character, which is itself a key value RDD, where the key is the superhero ID and the values are the total number of co-occurrences seen for that character. So we're getting close to our answer here. Now we have the information we need in that RDD, but we need to find the maximum number of friends for all of the people in it. So kind of like when we want to sort things, we need to flip things around to get what we want. Since we want to get the maximum count of characters, we need to make that count the key. So we're just going to do our usual flippy trick here and have a mapper that just swaps the keys with the values. You've seen that a few times before. And what we have now is a key value RDD where the key is the count and the value is the superhero ID. And now we can just call max on that key value ID, which will find the maximum key value, which is basically going to give us back the entry for the superhero ID with the most co-occurrences. Finally, we need to look up a name so we can actually display who that is. And we're going to use that names RDD that we created earlier to look up the name for that character ID, and that will give us back the value from that key value pair. That value is simply a list that contains a single string, so we're going to extract that value by using the array operator 0 there. That will give us back the actual name string itself into most popular name, which we can then just print out. And we also have the count that's still in the key value from our original result that we can use to display as well. So we can say who is the most popular superhero and how many co-appearances did that person have with other superheroes in our data set. So I'm itching to find out, who do you think it's going to be? Any guesses? My guess would be Spider-Man, but let's see if I'm right. Spark-submit. Most popular superhero.py. Off it goes. And the answer is... Ooh, isn't that a surprise? 1,933 co-appearances for Captain America. Yay, he is the most popular superhero in our data set. Seems like a pretty positive role model, and his character seems like a nice guy. Personally, I prefer a more global perspective on the world, but there you have it. A little bit unexpected. I would have guessed someone else, but Captain America it is. Captain America? I wouldn't have guessed that. But hey, I guess the folks at Marvel like the guy. He shows up in a lot of comic books, it turns out. And there you have it, an example of using Spark in a little bit more of a complex manner. Let's keep on playing with that Marvel superhero data and do some more interesting stuff with it next. All right, maybe you've heard about how everyone's connected through 6 degrees of separation, that somebody you know knows somebody else who knows somebody else and so on, and eventually you can be connected to pretty much everyone on the planet. Or maybe you've heard about how Kevin Bacon is within a few degrees of separation of pretty much everybody in Hollywood. Well, I used to work at imdb.com, and I can tell you that's true. Kevin Bacon is pretty well connected, but a lot of other actors are too, and Kevin Bacon's actually not the most connected actor, but I digress. Anyway, we want to bring this concept of degrees of separation to our superhero data set, where we have this sort of virtual social network of superheroes. So let's figure out the degrees of separation between any two superheroes in that data set. So is the Hulk connected to Spider-Man closely? How do you find how many connections there are between any two given superheroes that we have? Now, to find the answer, we need to introduce an algorithm called breadth-first search. And it's sort of a computer science-y network theory sort of a thing, but it's not that hard to understand. So let me walk you through how breadth-first search works, and then we'll talk about how to implement it in Spark. Okay, it's time to get into some more complicated examples of using Spark. So I'm going to take some problems that you might not think of as Spark problems initially, but they can be framed as Spark problems, and they have some real-world analogs too. So let's say you're working at, pick your favorite big social network company. They're going to have a lot of similar data to deal with there, and it's going to be data on the scale such that you can't do it on a single machine. So you kind of have to use Spark or something like it to analyze data and pick relationships out of some of these larger social network data sets. Anyway, what we're going to be doing is playing with superheroes in our superhero data set, and we're going to talk about an algorithm called breadth-first search for finding the degrees of separation between superheroes. And along the way, we'll introduce a concept called accumulators that kind of let different executors keep track of something together. So let's talk about how we're going to go about this. So remember, what we're trying to do is figure out degrees of separation between superheroes. So we want to basically, pick someone and call them like the Kevin Bacon of superheroes or something. Let's say we want to find out how far apart Iron Man is to Spider-Man. And these lines all indicate, these heroes all appear together in the same comic books. So in this example, Spider-Man is connected to the Hulk, who is connected to Iron Man. Therefore, Spider-Man and Iron Man are 2 degrees of separation from each other, whereas the Hulk and Thor are 1 degree. The Hulk and Iron Man are 1 degree, and Thor to Spider-Man is 2 degrees. Make sense? So that's what we mean by degrees of separation. How many hops do you need to go through some common acquaintance in order to find a connection with somebody else? And to do that, we're going to use an algorithm called breadth-first search. And it's kind of a computer science-y network theory sort of thing, but it's not that hard of a concept to grasp, so let's go through it. You are going to have to understand how breadth-first search works in order to understand how we're implementing it in Spark to solve this problem. And it's basically a way to search through a graph like this and figure out what are the distances between any given 2 nodes within that graph. So we're going to pick someone to start with, like the Hulk, and search our way through the whole graph, keeping track of the distances, the minimum distances, from the Hulk to any other character. So here's how breadth-first search works. It's such a hard thing to say. Let's imagine that every one of these circles represents one of the superheroes in our social graph, okay? And the lines represent the connections between them. So the line means that two superheroes appeared together in the same comic book at some point. All right? And you can see you can have these kind of complicated relationships that go on. So it's not really a straightforward problem. We need an algorithm to solve it. Now, the idea is that we've associated each superhero with one of these circles. And not only is there a superhero ID associated with each one of these nodes, but there's also a distance to the node that we're interested in, as well as a color that we'll use to keep track of its processing state. So let's say that node S represents the Hulk, and we want to measure how many degrees of separation people are from the Hulk. Okay, so we're going to start with node S here in our example. And initially, we're going to color all of the nodes white, meaning that they are completely unprocessed. And we're going to have an initial distance of infinity, meaning that we just don't know yet. It's infinitely far away. We haven't computed it yet. Now for our initial conditions, we know that we want to start with the Hulk, who's in this node. And we're going to change the color of that node to gray. And gray means that a node needs to be expanded upon. We've just come across it, and we need to work our way out from there. And the number 0 represents the degrees of separation from the Hulk. Because the Hulk is the Hulk, he has 0 degrees of separation to the Hulk. Okay, so our initial condition, everybody's white and infinitely far away. And we're going to start off with the person we're interested in measuring the distance from, color them gray, and give them an initial degrees of separation of 0. Now things get interesting. This is an iterative algorithm, so we're going to pass through the graph multiple times until we're finally done discovering every node in it. So in our next pass through the graph, we will take our gray node, which was the Hulk. We're going to color it black, meaning that we have processed it completely. We don't have to look at it again. But then we're going to go out to all of its connections and color those connections gray, meaning they need to be expanded upon next. And we are going to increment the distance from the original node by 1. So 0 plus 1 is 1. So we now know that nodes R and W, whoever they happen to represent, are 1 degree of separation from the Hulk, node S. Then we pass through it all again, and we have to then expand this guy and this guy in the next pass. So we'll start with him. Color that black, meaning we've processed it. Color its connections gray, meaning they need to be explored next. And increment the distance one more time. So now we know that these two nodes are 2 degrees of separation from the Hulk. And we still have to do this guy over here. Color him black. Again, increment the distance to 2 and color this new node that we just discovered gray, meaning that we need to explore it further as well. So this is the end of our second pass through the graph. Let's start our third pass. We'll start with this guy, color it black, meaning we've explored it. This guy we've already come across before, so we're going to leave him untouched and leave the previous minimum value there. But this connection is new. We're going to color that gray and increment its distance to 3. So now we're at a connection that has 3 degrees of separation from the Hulk. And then we'll explore this guy again, which will cause us to discover this node over here, who is also 3 degrees of separation. Color the original black. These ones are gray. So see what happened there? And we still have to process this guy who isn't connected to anybody. So all we have to do is mark him black, meaning we're done with him. Just have these last two to go through. And obviously they're not connected to anybody new, so nothing's really going to happen other than coloring them black to indicate that they have been visited and processed. And finally, we are done. So that is breadth first search. If that didn't make sense, it might be beneficial to go back and watch that little animation again of how the traversals work and how we actually arrived at the degrees of separation from node S as we worked our way through the graph. So next, let's talk about how we actually turn this into a Spark problem that we can run iteratively. And it's kind of interesting, so stay tuned. Okay, that's the basic concept of how breadth first search works from a conceptual standpoint, from an algorithmic standpoint. Now let's figure out how to actually apply that in Spark and in Python and actually get the results that we want to figuring out the degrees of separation between superheroes. Now that we have the concept of breadth first search under our belt and we understand how that can be used to find the degrees of separation between superheroes, let's apply that and actually write some Spark code to make it happen. Okay, so how do we turn breadth first search and finding degrees of separation between superheroes in our social network into a Spark problem? Let's go through that. Now this is going to make a lot more sense if that explanation of how BFS works is still fresh in your head. So if it's not, it might be a good idea to go back and rewatch the previous lecture because it will really help a lot. So the first thing we need to do is actually convert our data file, our input file, into something that looks like these nodes that we described in the BFS algorithm. So if we're starting off, for example, with a line of input that looks like this, that says hero ID 5983 appeared with heroes 1165, 38, 36, 43, 61, and 1282. What we want to do is convert that to something a little bit more interesting and useful. So we want to convert that to structured data where we have, for example, the hero ID in question, the list of their connections, a distance, and a color. So remember, we had in our nodes not only their connections to other nodes, but also a distance from the hero that we want to start from, and also a color that keeps track of what's been processed and what hasn't. Okay, so this is kind of how we're going to represent one of those nodes within Spark and within Python. Now remember, our initial condition is that nodes are all infinitely distant, and we'll represent that as 9999 because, believe me, no one's going to be that far apart in a social network. And the initial color will be white, meaning everything has been unprocessed. Let's turn that into some code. So, a big part of the code is just the conversion of that source data into something that looks like a node. And what we're going to do is convert that to an actual key value pair, and sort of a key of a hero ID and a value that's this composite value of the list of connections, the distance, and the color. So that way we can group things together by hero ID later more easily. So all that's going on up here is, pretty straightforward stuff. We split up the input line, extract the hero ID from the first field, and then a little bit of a Python syntax you might not have seen before. This 1: thing means we're going to extract all of the fields from number 1 forward. So basically that lets us iterate through all of the friends, if you will, of that hero ID that are in fields 1 going forward. And that appends them into a list of connections. Okay, so at this point we have a hero ID that we've extracted and a list of all of the connections for that hero ID. Finally, we set the initial conditions like we talked about to white and an infinite distance that we're just going to represent with 9999. Except for the initial condition. So if we're starting with, say, the Hulk, and the hero ID that we're encountering is the Hulk, we know that's the guy we want to start from. So let's say we want to measure degrees of separation from the Hulk. We would color his node gray and give him an initial distance of 0, meaning that the Hulk is the Hulk and therefore is 0 degrees of separation from the Hulk. And the color gray represents that this node needs to be processed and expanded upon through the next iteration of breadth first search. And again, our final output will be the hero ID as the key, and the value will be a list of connections. Remember, this is actually a list, the distance, and the color. Okay. And then we're going to go through the entire graph multiple times. So we're going to do this as many times as it takes to find the other character that we're interested in. So we want to find the degrees of separation between two given characters. So we will go through each time, and we will look for gray nodes that need to be expanded upon. When we're done expanding them, we'll color them black. And as we go along coloring new nodes gray, we update the distances to increment them and keep track of the degrees of separation from our starting point, just like in the animation from the previous lecture. Now to do that, we're basically going to create a map function that will go through looking for gray nodes, and if it is gray, it's going to create new nodes, okay, that have a distance incremented by 1 and a color of gray. And these new nodes will have no connections. We'll combine them back together with their connection list in the reducer. And obviously this is going to be a flat map operation because we might be producing multiple nodes for each input node. We then color that node black, and we will copy the node itself into the results returned by the flat map operation so we don't lose it. Our reducer kind of recombines everything, so it looks for nodes tied to the same hero ID. So these are all information associated with the same node. Remember, there's only one node per hero in our graph, okay? So anything that comes together for that hero ID needs to be combined back together. So it's going to look for the shortest distance of all that information and preserve the darkest color for that node that we found. And then it will then find the list of connections that we passed along originally when we copied the original node back in and marry that back into the final node for this iteration, okay? So we'll just do this over and over again until we encounter the character that we're interested in. And at that point, we can count how many iterations we've had to go through to figure out the degrees of separation. But how do we know when we're done? I mean, this is running potentially on a cluster, and there's no set way of knowing when we've actually encountered the character we care about. Well, that's where accumulators come in. So remember how broadcast variables let you share objects across all the nodes in your cluster? Well, an accumulator allows all the executors in your cluster to increment some shared variable. So it's basically a counter that is maintained and synchronized across all of the different nodes in your cluster. So an example usage, you can call the accumulator function on your Spark context with an initial value of, say, 0, and call that accumulator object your hit counter. And then when we're going through our iterations, if any node that happens to be running this job encounters the character we're looking for, we can just increment that hit counter accumulator. And then every other node and our driver script has access to that. So after each iteration, we can check that hit counter to see if anybody incremented it, maybe even multiple people incremented it. And if it is greater than 1, we're done, right? So we know that once hit counter gets incremented by some value, we've found the guy we're looking for, and we can declare victory. Okay, so let's go look at this in action. Let's actually make it happen. Okay, we know how we're going to attack this problem from Spark, so let's actually make it real, dive in, run the code, see what happens. Let's actually run that code in Spark to find the degrees of separation between any two superheroes using breadth first search. Okay, let's actually find the degrees of separation between two given superheroes in our Marvel superhero dataset. So in the resources for this lecture, download the degrees of separation script into your Spark course folder. We're working up a pretty good library here of different examples here, so keep this around. You know, there's a good chance that some problem you face in the future will have a similar pattern to something we've already done here, and this might be a useful reference for you. Once you have that, double-click it. We already have the Marvel graphs and Marvel names text files for our input from previous lectures. And here it is. So again, the point here is just to illustrate how problems that may not seem like they lend themselves to Spark at first actually can be implemented in Spark with a little bit of creative thinking. And we also want to introduce the concept of accumulators here as we go. So let's look at our code here. We have the usual boilerplate stuff, nothing changed there. And we're going to define two character IDs that we're interested in. So we're going to say that we're going to be interested in degrees of separation from Spider-Man, who turns out to be character ID 5306. And what we're interested in finding out is how many degrees of separation is Adam 3031, whoever that is, to Spider-Man. And I intentionally picked some random character who I've never heard of because it's a little more interesting if it actually takes a few iterations to get through here to get a result. Now we talked about using a accumulator to signal to the driver script when we've actually found Adam 3031. So we're going to set up that accumulator that all of our different executors can use to signal once we've actually found that node that we're looking for. Okay, and we'll set an initial value of 0 on that accumulator, and we'll call it hit counter. We covered the convert to BFS function in the previous lecture. So just to recap quickly, this sets up the initial conditions of our graph and converts our input data into node structures, where each entry of our RDD is going to consist of a key value pair, where the key is the superhero ID, and the value is a composite value that consists of its list of connections, the distance, and the color. And initially, distances will be 9999, indicating infinity, and a color of white, except for Spider-Man, who will be colored gray to start with a distance of 0, because Spider-Man is Spider-Man, and gray indicates that we need to expand upon that node. Okay. Skipping down a bit to the meat of it, a lot of stuff going on here, but if we get down to the main program, we start off calling create starting RDD. Okay, let's see what that does. So what that does is load in our input file, the Marvel graph.txt, and then it's going to call the convert to BFS map function that we described just a minute ago, and convert that into something that looks like node IDs. So nothing too complicated yet. We're just converting our input data into something that looks like nodes in a breadth first search traversal. Okay? What happens next? Now next we're going to go through some upper bound of iterations. So we're going to assume that we're never going to be more than 10 degrees of separation from anybody in this graph. If so, they're probably not connected at all. So we're just picking some arbitrary upper bound here. And we will iterate through the graph doing a BFS traversal up to 10 times. So the first time we'll say we're running BFS iteration number 1. And then we will call our flat map, which runs that first step that we talked about in the previous lecture of blowing out all the gray nodes. So that is calling our BFS map function. Let's see what that does. That's up here. And like we talked about, it just extracts the information from each node and looks for gray nodes and blows them out and colors them black, creates new gray nodes from their connections, and this is a flat map, so we're returning a results list of nodes that get added into the new resulting RDD. Finally, we put the original node back into the list as well, so we can reconnect its connections back to that node in the reducer. So this creates, not only the original node we started with, but new nodes potentially that are colored gray that need to be expanded upon. And for each new node, we've incremented the distance to keep track of the degrees of separation. You're better served going back and looking at the previous 2 lectures if that doesn't make sense to you. It's a little bit more easy to understand graphically than by looking at the code, actually. And then next, we will call our... oh, yeah. So to actually make that happen, we have to actually call an action. So remember, we have lazy evaluation in Spark. So just calling flat map doesn't actually make anything happen. And a very key thing happened in the BFS map function. So if we actually encountered the character that we were looking for, we incremented our hit counter, our accumulator, right? Very important point. So the moment that we encounter Adam 3031, this hit counter is going to get incremented, signaling back to our driver script that we have found the person we're looking for. But the problem is, map functions are transforms. They don't actually cause anything to actually get run in Spark until you call an action. So what we're doing here is a little bit of a cheat. We're calling the count function on that RDD to force it to get evaluated. And that way our accumulator will get set at this point. And it also prints out some interesting information as a side effect. We can see how we're actually processing more and more nodes as we expand outward from our starting node. If we did, in fact, encounter Adam 3031 upon that mapping pass, we will check that hit counter, see if it's greater than 0, and if so, print it out and say, hey, we found our guy. And we can actually print out how many times that hit counter was hit, because you can actually come at a given character from many different directions potentially. But if not, we'll keep on processing. So we will call the reduce by key function to actually gather together all of the nodes that we might have generated in that flat map operation and recombine them together for each given character ID, because there can be only one node per character ID, and that enforces that. So BFS reduce simply gathers them all back together, and it preserves the minimum distance and the darkest color found and reconnects all the list of connections that were found for that original node. So if you want to stare at that code in a little bit more depth, you can get into the syntax of how it does that, but conceptually, that's what's going on. Okay, and that's it. Finally, we just keep on iterating through until we hit a maximum of 10 iterations, but nothing's going to get that high. So let's go ahead and run it and see what happens. Spark submit. Degrees of separation.py. All right, we're going through once, twice, still no Adam 3031. There he is. So on the 3rd iteration through our breadth first search traversal, we finally found the guy we were looking for. He was only hit from one direction, so this guy is in fact pretty obscure. But our answer is Adam 3031, whoever the heck he is 3 degrees of separation from Spider-Man in our social graph. So there's your answer. And you can plug in different character IDs for anyone you want in here if you're curious and you want to play around with it. Also notice how we started blowing out to more and more nodes that we were looking at. So we started off with just 8,330 connections to Spider-Man himself, but we started looking at the connections of the connections, and we start getting into a very large number very quickly that we're processing on each iteration through. So you can see how these social graphs tend to branch out to a large number of people pretty quickly. And people really are a small number of degrees of separation from each other in many cases. And there you have it. Turns out the rumors are true. People really are connected pretty closely through various degrees of separation. Granted, this is a fictitious data set, but we had to pick a pretty obscure character to find someone who was even a little bit removed from Spider-Man, for example. And if you were to try to do this between any 2 well-known superheroes, they're probably just connected by 1 degree. So there is truth to this whole degrees of separation thing. It's not just a made-up thing. But I digress. The whole point was to illustrate how to do a more complex algorithm like breadth first search using Spark. So you're not limited to just doing simple mapping and reducing functions with Spark. With a little creativity, you can take more complicated problems like this and frame them as Spark problems. And that's really the skill that they're going to pay you the big bucks for. So the more you can think about how to frame problems as distributed Spark problems, the more valuable you'll be as a data miner. Next, we're going to cover a topic that's near and dear to my heart, collaborative filtering. And if you've ever been to someplace like Amazon.com and see something like people who bought this also bought, or similar movies on IMDb.com, I used to work on that. And I'm going to show you some general algorithms on how that works under the hood. Now, I can't tell you exactly how Amazon does it because Jeff Bezos would hunt me down and probably do terrible things to me, but I can tell you some generally known techniques that you can build upon for doing something similar. So let's talk about a technique called item-based collaborative filtering and how that works, and we'll apply it to our movie lens data to actually figure out similar movies to each other based on user ratings. Let's see how that works. Okay, we did breadth first search and degrees of separation. Now we're going to do collaborative filtering, actually finding similar movies just looking at movie ratings data. So we're doing some pretty complicated and advanced stuff here at this point. And the good news is this is probably the culmination of the course in terms of difficulty level. Stay with me, bear with me, because after this lecture, things get easier. Trust me. Mainly, again, I just want to make sure that you understand that complex problems that may not appear to be a Spark problem can be framed as Spark problems. So this is yet another example of taking something that you might not think of as being distributable and actually making it into something that you can run on Spark with massive data sets. Now, in addition to talking about finding similar movies using the Movie Lens ratings data set, we're also going to introduce a concept called caching and persisting RDDs, which is very important to know as well. Okay, so we're going to find similar movies to each other based on movie ratings, and Movie Lens does this for you under the hood. It can actually find movies that are similar to each other, and it uses that to power its recommendations. And this is also, something you see on websites all over the place. Amazon does this stuff. IMDb does this stuff. Like I said, they all have their own little secret sauce on how they do it. Netflix does it too. So this is just one way that I'm going to show you right now. So how does item-based collaborative filtering work? Well, here's how we're going to do it. And it's only one way to do it. There are many techniques. This is just one that's easier to explain. So what we do is we find every pair of movies that were watched by the same person, okay? And then we find all the users that watched that pair of movies and compare how similar their ratings were for each one. So the idea is that if you have, two movies that were watched by a bunch of people and they all rated them similarly, those movies are probably similar to each other in some way, shape, or form. So after we do that, we can then compute the similarity of each movie pair, sort them by the movie, and then by the strength of similarities. And then you can slice and dice the results and look up a specific movie and find the movies that are most similar to it. Okay, so again, that's just one way to do it. Makes a little bit more sense with an illustration. So, let's imagine that this good-looking little clip art woman watched Star Wars and Star Wars The Empire Strikes Back and rated them both similarly. And, Mr. Clip Art Mohawk guy here comes along and also rates both movies and rates them in a similar way to the first person did. So with that information, we can establish a connection between these two movies, and we know that there is some relationship between those two. So Mr. Handlebar Mustache comes along, and he lives in some strange world where he's never seen the first Star Wars movie, but he has seen The Empire Strikes Back. So what we could do at this point, if we were creating movie recommendations, would be to take the fact that we discovered a connection between The Empire Strikes Back and Star Wars based on these other ratings, and then we can say, hey, here's another movie you might be interested in. Star Wars, it turns out, is somehow connected to The Empire Strikes Back, so maybe you should check that out too. So that's it in a nutshell. That's item-based collaborative filtering. Pretty simple concept, fancy name, right? That tends to be the case in machine learning and data mining, actually. You hear a lot of big fancy words and terms that sound very highfalutin and academic, but when it comes down to it, the concepts aren't that complicated. However, turning this into a Spark program is complicated. And I'm just going to kind of walk you through the approach that I used here. Again, the point here is just to illustrate how you can take something like this and turn it into a Spark problem. It's just an example to look at. So if you don't totally get everything that's going on here, that's okay. Important thing is that you see that you can take a complex problem like this and make a Spark problem out of it and make it actually work. So here's our strategy. And what we're going to do is map the set of input ratings from the Movie Lens data set to key value pairs where the key is the user ID and the value is this composite movie ID and rating structure. Okay, so for every line of input, we're going to create a key value where the key is the user, and the value is the rating for a given movie ID. Now next we need to find every movie pair that was rated by the same users. Okay, and to do that, a while ago I talked about some operations you can do on key value RDDs that were very SQL-ish, and one of them was a join operation. And it turns out if you join a database with itself, you end up getting every possible permutation within that database. So by doing a self-join, basically joining that RDD with itself, I'll get back every single possible pair of movies that were rated by that same movie. So what I end up with here is this huge list, because this blows up quickly. It's like, a Cartesian combination, right? Where I have this huge list of user IDs followed by every possible pair of movies that they watched together. So we'll have a user ID watched this movie and rated it something, and they also watched this other movie and rated it something. And we will get that for every combination of movies that they had watched, okay? Now we're going to get some duplicate pairs as part of that process. We're going to get some things that are in different orders, or maybe we'll get the same movie and movie ID 1 and the same movie and movie ID 2. We're going to strip out all that duplicate, redundant information just to boil things down a little bit more, okay? Now next we're going to make the movie pairs the key, because what we really care about is the similarity strength between pairs of movies. Okay, that's the end goal here. So we're going to shuffle this data around, and we're going to map this data so that it looks like movie ID 1, movie ID 2, this composite value ends up being the key, and the value ends up being the ratings of those two movies. So we can say movie ID 1 and movie ID 2 were watched together by some person and rated with these two values. Okay, at this point, the user ID is irrelevant. We don't really care who the individual was. All we care about is that some person watched these movies together and gave them these ratings. Okay, with me so far? Next, we're going to do a group by key. So we want to combine together all the ratings that individuals made for that given pair of movies. All right, with me so far? So what we had before this point was for every individual movie pair that was watched by a given user, what that user rated each one. And now we're going to combine together all of the ratings that were made for that movie pair across the entire data set. And once we have all that together, we can compute the similarity between those two movies just by looking at the similarity between the sets of ratings that different users gave to that movie. Okay? And there are many ways to compute similarity. We'll pick one that's easy to do. And now we have what we need. We just need to sort, save, and display the results. So let's go off and look at the code and make it actually happen. So one thing I want to point out first too is that we're doing some pretty heavy lifting here. That self-join is a huge operation. It generates a huge RDD. So it's time to start splitting this up across more than just one CPU. Odds are your PC at home has at least 2 cores on it. So by doing this one little trick here, instead of just saying setMaster local, we're going to do setMaster local open bracket star close bracket. And that syntax means go take advantage of every core you have available on this computer and run a separate executor. So for the first time, we're going to be running a Spark program across multiple executors. It will still be on just on your computer, but we're actually going to be running as many executors as you have cores and combining the results back together later on. So again, let's go take a look. One other thing I want to mention too is caching RDDs, and I'll point this out as we go through the code. Now we're actually going to compute the RDD of movie similarities, and we're going to look at it a couple of times. And the way Spark works, as soon as you call an action, it just discards that RDD. So if you actually want to use an RDD more than once and perform more than one action on it, you need to tell Spark explicitly to cache it and make it persistent. Otherwise, Spark might have to go back and reconstruct that RDD all over again, and you might end up, doubling the amount of work that you have to do. That would be bad, because that join operation, that self-join, is very expensive in this example, and we don't want to have to do that twice. Okay? So what we'll do instead is once we have that RDD of movie similarities, we're going to call cache on it or persist in order to keep it around and prevent the need from recomputing it again. What's the difference between cache and persist? They're actually very similar. The only real difference is that persist gives you an optional argument that lets you cache it to disk instead of just memory. So if you're really paranoid about losing that RDD and you don't want to lose it even if a node fails, you can use persist to make sure that it writes it to disk. Obviously, that's going to take more time and consume disk space, whereas cache will not. Now, let's really go look at the code and run this beast. So there you have the concepts behind item-based collaborative filtering. It's a fancy word, but it's a pretty simple concept, right? So let's figure out how to take that and turn it into a Spark problem. So again, this is an example of taking a more complex business problem and trying to frame it as a Spark problem that can be horizontally partitioned on a Spark cluster, so you can take massive amounts of ratings data and process them still with good results. So let's dive in next and turn this into some code. Okay, it's been a lot of work leading up to this point, but we have a Spark program that should give us similar movies to each other just by looking at some movie ratings data that users have put in. So we'll figure out what movies are similar to each other just based on similarities between user ratings. Let's run it and take a look at the results. All right, let's turn this movie similarities problem into some real code. And go to the resources for this lecture. You will find a movie similarities script. So go ahead and download that to your Spark course folder. Hit pause and come back when you're done, and we'll open that back up. We're going to keep on using the Movie Lens 100,000 rating data set for this example as well, so there's no new data to download, just the script. All right, this is, the most complicated thing we're going to do in this course, so let's just get through this script and walk through what it's doing. We described it at a high level in the previous lecture, but let's go through it again. So, we're going to be importing the usual stuff. We do need to import the square root function from the math package in Python as well, so we can do our similarity metric and compute similarities later on. But let's skip down to the meat of it. So we create our Spark context, and again, we're doing this with a local star master argument here, and that means that we're actually going to use Spark's built-in cluster manager and treat every core on your desktop as a node on a cluster. So for the first time, we're going to be running on more than one process, and you actually kind of need it for this problem. Next, we'll load up the dictionary of movie names. We've seen that before. So if we look at the load movie name script, it's just returning a Python dictionary that maps movie IDs to human readable movie names so we can look at them more easily. And we're using the usual decode trick to make sure that we can actually display them in our terminal here. That's all that decode stuff is doing. Now, we're not going to muck around with broadcast variables in this particular example. We're just going to use that dictionary at the very end when we're doing our final display, okay? So keeping that a little bit simpler. All right, we'll load up our source data of movie ratings data. Again, the u.data format is user ID, movie ID, rating timestamp, and that goes into a data RDD. We then do this big, long operation here to map it into our initial pass here. So we start off by splitting the data on white space into individual fields, and then we map it again into the format we want. So this is going to give us back together an RDD that is user ID as the key, and the values will be these composite values of movie ID and rating. So we have a key value RDD at this point. Keys are user IDs, and the values are movie rating pairs. Next, we do a self-join operation to find every possible combination of movies that were rated together by the same user, okay? And that blows up really quickly. This is where most of the work is going to be happening in this script, because when you start looking at every possible combination, you're looking at factorial relationships here. It blows up like you wouldn't believe. But with Spark, we can actually do it because it's scalable. So at that point, we're going to end up with user ID still as the key, but then we're going to get lists of every movie ID rating pair that were viewed together by that user ID. So we have this huge RDD now where the keys are user IDs and the values are every possible combination of movie rating pairs that user watched together. Next, we need to eliminate duplicates, because out of those possible permutations, we're probably going to get the same movie twice, just in a different order, and we'll even get the same movie related to the same movie. And we need to filter all that junk out, because that's not helpful. So our filter duplicates map function up here simply enforces that we only return pairs where movie 1 is less than movie 2. So we enforce only one ordering of the movie pairs that are in sorted order, and we also eliminate pairs where the movie 1 is the same thing as movie 2, because that's not helpful either. So we talked about filters before. This is another example of using filter to reduce, well, reduce is probably a poor choice of words, but to cut down a large RDD into a smaller one by throwing away information you don't want. Okay, so now we have a cleaned up RDD that contains every movie rating pair, every movie pair for each user. Now, next, where were we? We filtered out the duplicates. Now we need to shuffle things around. So what we care about in the end is the similarities between pairs of movies, between unique pairs of movies, okay? So we're just going to run another map operation on that to make the new key the movie pair itself, and that's what the make pairs map function does. Up here, it extracts the movie and rating for each pair of the input RDD and outputs a new key value RDD where the key is the movie pair and the value are the ratings for that movie pair. All right, we're almost done. Now we're going to do group by key to actually get together all the rating pairs for each unique movie pair. So for every pair of movies, we gather together all the pairs of ratings from every user that watched that pair of movies. And now that we have every set of ratings from every user that watched a given pair of movies, we can compute the similarity between those two movies by actually comparing the similarities between those two sets of ratings. And that's what compute cosine similarity does. I don't want to get too much into this from a mathematical standpoint, but it is basically a metric of how similar two vectors are, in this case two vectors of ratings, and it uses that to determine a similarity score between these two movies. And as it is sort of a cosine-like function, a strong similarity will be a rather high number, close to 1.0, but less than 1.0. So 0.95-ish would be a good similarity, for example. And as we mentioned before in the previous lecture, we're going to cache that result because we're going to need to use that movie pair similarities RDD more than once. If you did not do that and you were to call more than one action on movie pair similarities, then you'd be in trouble. We'd have to go back and recompute it all over again, and that would be a shame. Now, if you want to, we could actually save the results to text files and go examine them offline later. And if you want to do that, you can uncomment these. And this is just a little example of how you can use the save as text file method to actually output the results to text files. Now, bear in mind, since we're running this from four different, on my four core computer, we would get four different output files, right? So each individual executor will end up writing out its own results here. So you would have to combine those together by hand at the end. Just something to keep in mind. But for now, I'm going to introduce another concept. I'm actually going to take in an input parameter on this script that indicates the movie that I care about, that I want to get similarities for, and just extract the similarities for that one movie. So if I do provide an argument to this script, I am going to go look for that movie ID and run the filter operation to filter out only movies that actually include the movie that I am interested in. So let's say I pass in movie ID 50, which is Star Wars. I'm going to run another filter on my similarities results to extract only the similarities that include Star Wars in the pair. Okay? And furthermore, I'm going to introduce a minimum threshold on the quality of the similarity by saying I only want results that have a score greater than 0.97 and have at least 50 different people that watch the same pair, because that gives me more confidence in the quality of the results. If I were to allow similarities between movies that were only watched by one or two people, I'd get a lot of spurious results that didn't make sense. So that's a very important thing to take into account. Finally, I will sort the final result by key, by the quality score. So I do the usual trick here of flipping the key and value to actually get the thing I want to sort by in the key, and then sort by key, and I will actually do it in descending order and take the top 10. Okay, going through this a little bit quickly, but go back, look at it more closely on your own. It's mostly self-explanatory if you think through it, but that is a one-line way of flipping the RDD to sort it by the similarity score in reverse order and taking the top 10 results, and then I can just take those results and print them out. Okay. So let's go ahead and do it. Like I said, very complicated example, or most complicated that we'll see in this course. So if you need to go back and stare at it some more, please feel free to do so. Let's actually run it and see what happens. Spark-submit. What do I call this thing again? Movie similarities. And remember, I need to take a parameter for the movie ID I care about, and as you recall, movie ID 50 is Star Wars, so let's use that as a well-known example. Off it goes. All right, we load the movie names lookup table, and off it goes. And you're going to see a bunch of stuff here that you haven't seen before, because we're actually running this using Spark's built-in cluster manager this time, remember? So it's actually going to give us how the cluster manager is progressing, where it's treating each core of my desktop computer as an individual executor node. Off it goes. Now it's going to take a little bit of time. You know, we have 100,000 ratings, and remember that self-join is going to create an entry for every possible combination of movies that were watched together by the same person. So that ends up being a very large amount of data. But we're actually getting through it relatively quickly. There we are. Cool. So we have some real results here based on real data and real ratings. And it turns out that the top 10 similar movies for Star Wars, the first two are exactly what I would expect. The Empire Strikes Back and Return of the Jedi. And Raiders of the Lost Ark, not a bad choice either. 20,000 Leagues Under the Sea, I can go with that. Things start to get a little bit weird after that. I mean, to be honest though, I'm a Star Wars fan and I've seen a lot of these movies and I liked them. And a lot of these had to be taken within the context of 1998 as well, when this data set was published. So pretty good results. They're not awesome, but they're pretty good. So, you know, let's talk about something you can do to try to make it better. That's an exercise for the reader, and there's a lot you can do. There's a whole art and even a science to making good movie similarities data. So let's dive into it a little bit more. And there you have it. We have some reasonable results for movie similarities out of this initial take at our program here. But there's more than one way to do it. You know, this is just one technique, and there are definitely better techniques out there that you can use to improve the quality of your similarities even better. So in our next lecture, let's introduce a learning activity that has you dive in and do just that. Okay, it's time for your homework assignment. I want you to make the quality of these similarities even better, and it's purely a subjective thing. Really, the objective here is just to get you to roll up your sleeves, dive in, and start messing with this code to make sure that you understand it, and you can modify it and get some tangible results out of your changes. So let me give you some pointers and some tips on what you might want to try here, and we'll set you loose. All right, your mission, should you choose to accept it, is to dive into this code and try to make it better. So we're just using a very naive algorithm here with a cosine similarity metric, and the results, like we saw, weren't that bad, but maybe they could be better. And, you know, there are ways to actually measure the goodness of a recommendation or a similarity, but without getting into that, just dive into there and try some different ideas and see what effect it has. And maybe they qualitatively just look better to you. And at the end of the day, maybe that's all that matters. So some ideas of some simple things to try. Maybe you could just try throwing out any movie that has a bad rating. So, you know, if someone rates something 1 star, is that really useful for your purposes? I mean, maybe strictly speaking, it lets you see that bad movies are similar to each other, but at the end of the day, do you really want to be recommending bad movies to people? I don't think so. So if that's your intended use of this information, try just filtering out the bad ratings and see what that does. You can try different similarity metrics. There are things like the Pearson correlation coefficient or Jacquard coefficient that you could replace our cosine metric with and see what you get. Some of those might be better, might be worse. One way to find out. You can also try adjusting the thresholds for the minimum co-raters or minimum score. Maybe we're just not being picky enough with the final results. And you can try to invent your own similarity metric. One thing, maybe we don't really need that minimum threshold for minimum co-raters. Maybe we can just take that into account as part of the actual similarity itself and automatically account for how much confidence we have in that relationship. Also, there's the u.items folder in the Movie Lens dataset that contains things like genre information. So it might be interesting to extract that information and give a boost to movies that are in the same genre. So for example, similarities to Star Wars that are science fiction, maybe that should count a little bit more, right? So, you know, just dive in there, give it a try, see what you can come up with. Have some fun with it. I mean, it's an interesting problem. It kept me occupied for a few years, so play around with it, get familiar with this script. It's a complicated one, so I want you to dive in there and get familiar with it. All right, go have some fun. All right, good luck. You're off on your own to actually try to improve upon our results for movie similarities. There's no right or wrong answer here. As long as you have results that make sense and your script still works, consider yourself successful. So we're not going to come back and compare your improvements to mine because there's infinite ways to actually approach this problem. There is no right or wrong answer. I just want you to get in there, play around with it, see what you come up with, all right? Get some familiarity with the code, get some more familiarity with Spark in your development environment. That's the real goal here. So have fun and see what you can come up with. It's time to graduate off of your desktop computer and actually start running some Spark jobs in the cloud on an actual Spark cluster. So the easiest way I know of to actually get up and running if you don't already have a Spark cluster is by using Amazon's Elastic MapReduce service. And even though it says MapReduce in the name, you can actually configure it to set up a Spark cluster for you and run that on top of Hadoop. And it sets everything up for you automatically. So let's walk through what Elastic MapReduce is, how it interacts with Spark, and how to decide if it's really something you want to be messing with. Okay, let's talk about running Spark on an actual cluster of computers in the cloud and getting off your desktop. So, an easy way to get started if you don't already have a cluster to run on is by using Amazon's Elastic MapReduce service. And it's an easy way to rent just the time you need on a cluster to actually run your Spark job. And it makes things pretty easy. So even though it says MapReduce in the name, it actually installs Spark for you by default as well. And you don't have to just run MapReduce jobs. You can actually run Spark and use the underlying Hadoop environment to actually run as your cluster manager. So yeah, it has something called Hadoop Yarn, and if you took my earlier class on MapReduce and Hadoop, you've heard about that already, but basically Yarn is Hadoop's cluster manager, and Spark is able to run on top of it, and that is also installed as part of Elastic MapReduce for you. So let's back up a little bit. I mean, this is a service offered by Amazon.com, and basically what you're doing is renting time in their massive data centers of computers, and you're saying, I want to rent 6 or 7 different instances of computers that I want to run my cluster across. And instead of actually buying those computers, you're just paying by the hour. Now, Spark also has its own built-in standalone cluster manager, and you can actually use that to run on EC2 and has scripts to support that as well. But I find that if you're going to be using EC2 anyway, you may as well just use the Amazon Web Services console application on the web to launch a Spark cluster that's already set up for you. And then all you have to do is SSH into the master node in your cluster and copy your script over and run it from there directly. And I think that's a lot more straightforward than trying to figure out how to use the EC2 scripts, especially from Python. It gets a little bit tricky. Now, I do want to warn you that if you did go through my earlier class on MapReduce and Hadoop, we also used Elastic MapReduce in that course, and it was dirt cheap. And the reason it was dirt cheap was because we were using dirt cheap instance types, which is basically the kind of computer that we're using in our cluster. But with Spark, by default, we're using something that's a little bit more expensive, actually a lot more expensive. And those are M3.X large instances. So even though we'll see that Spark runs a lot faster, bear in mind we're using much more powerful computers than we did in the previous course. And myself personally, I racked up about $30 in Amazon Web Services charge developing this course. So I had to run the jobs we're going to go through to do movie recommendations on the cluster 4 or 5 times, and that ended up running about $30. And that was me being very careful about only spinning up these clusters when I needed them and terminating them as soon as I was done with them. So they add up quickly. So please, if you are going to follow along, remember to shut down your clusters when you're done, or else you're going to rack up a very big bill very quickly, and you're not going to be very happy about that. Now, if that makes you nervous, if you don't think you have the the discipline to actually remember to come back and shut down that cluster and terminate it when you're done running it, maybe you shouldn't actually follow along with this and just watch me do it, because there is a very real risk here that you could run up a very large bill very quickly accidentally if you're not careful, okay? Now, if you do have a corporate account with Amazon Web Services and you're doing this on somebody else's dime, maybe that's a different story. Or if you already have a cluster for Spark that you already have access to through your employer that's running all the time, by all means use it. I'm just going to walk through this as an alternative so you have a way of experimenting with Spark on a cluster from home if you want to play along. But again, please make sure after your jobs are done, you need to manually terminate them in the console, and I'll show you how to do that later. And the other important point to make sure that you keep your costs under control is to always run things locally on your desktop on a subset of your data first. Remember, we have operations on RDDs like top and sample that you can use to create a smaller sample of a data set. And by doing that, you can create a subset that you can use to work the initial kinks out of your system at least. And then when you're actually running on the cluster, hopefully the only bugs you're dealing with are things that are specific to running on a cluster. And that will save you a lot of time and money. So with that all said, let's take a look at Amazon Web Services and how to set up an Elastic MapReduce account, and then we'll move on from there. That's Elastic MapReduce in a nutshell. So if it does seem like something you want to get down and dirty with and actually create an account, I'll walk you through some of the basics on how to get started with that next, and also how to connect to it using a terminal from a Windows system. Okay, real quick, let's go through how to actually get set up on Amazon Web Services and create an account that you can use to spin up your own Elastic MapReduce cluster for running Spark jobs on a cluster. And we'll also talk about how you can connect to that cluster, because going forward, you're not going to be running your driver scripts on your desktop anymore. You're actually going to be running them from a master node on an actual EC2 Linux instance in the cloud. So you're going to have to be able to connect to that EC2 instance from your desktop, and I'll show you how to do that on Windows right now. All right, so to get started with Amazon Web Services, first we're going to walk you through how to create an account on AWS if you haven't already. Just a quick pointer of where to go there. And when we're done, we're going to figure out how to actually connect to the instances that we might be spinning up on web services. So when we actually create a cluster for Spark, we need a way to actually log into the master node on that cluster and actually run our script there. So to do so, we need to get our credentials for logging into any instances that our Spark cluster spins up. And we'll also set up a terminal if you're on Windows called PuTTY and go through how to actually use that to connect to your instances. So let me walk you through that right now. Okay, let's go through how to set up an Amazon Web Services account if you need one, and get started with Elastic MapReduce, and also figure out how to connect to our instances on Elastic MapReduce. So again, you know, if you don't want to risk spending money, you're gonna need a credit card number to sign up for an account here. It's gonna cost some real money, and it can actually add up. So if you do just want to watch, that's okay. But if you want to follow along, feel free. Just make sure that you're careful to shut down and terminate any clusters that you spin up in the course of this course, or else you're going to rack up a pretty significant bill. And to get a sense of the current pricing, you can click on the Pricing tab up here and go to Products and Services and look at EC2, the Elastic Compute Cloud, because that's the primary cost of our clusters that we'll be spinning up, is just renting time on these computers. And if you scroll down, you can see what individual types of instances cost. Now, by default, a EMR cluster for Spark is going to spin up M3.X large instances, and these are 4 CPU, 15 gigabyte apiece instances, so these are very beefy. And 26 cents per hour, it may not sound like much, but it can add up. Okay, I mean, that's actually a very reasonable rate for a computer that powerful. You know, I'll grant them that. But if you're running 10 of these things in a cluster, all of a sudden that's $2.60 per hour. And if you're running 10 of these for 10 hours, then you're now up to $26, right? So you got to be careful that you shut these things down when you're done, because they can add up quickly. If you were to run that for a whole month and not even realize it and just get the bill at the end, I don't even want to think about how much money that would be. So do exercise caution if you're going to do this yourself. But if you are confident in your ability to shut things down when you're done, and you have, you know, some extra money to spend, by all means sign up here and follow along with me. Otherwise, let me incur the expense. Like I said, I ran up about $30 in the course of developing this course, so there you have it. If you need an account, just click on the Sign into the Console link here up in the corner, and I'm already in there, but if I wasn't already logged in, you would see a screen that would allow you to either enter your username and password or create a new one, and at that point you could say Create New Account, and it would ask you for all of your personal information and credit card information, and it would actually call you as part of a two-factor authentication process to make sure that you are who you are. And after you get through all of that stuff, which I won't bore you with making you watch, you should be eventually at a screen that looks like this, which is the AWS console. And if you need to get to it, it's always available through this little cube icon here. Okay. Now, we're going to be doing a lot of work with EMR, the Elastic MapReduce product from Amazon Web Services. And it's not just MapReduce, it's actually a managed Hadoop framework. So it spins up a Hadoop cluster for you. And that actually includes Spark as well. So EMR, it's not just for MapReduce anymore. You can actually use the Yarn component of Hadoop as a cluster manager that Spark runs on top of. And by just kicking off an EMR cluster in Amazon Web Services, you can very quickly get a master node and as many client, slave nodes as you want for the job that you have at hand. And maybe one is all you need, given that you have 4 cores and a pretty powerful computer. But it gives you everything you need. It deploys all the software you need automatically. So all you have to do is log into your master node on the cluster, copy your script there, and make sure any data that it needs is accessible to it, and run it. And that's it. So it's very easy to use. But first, you need a way to actually connect to those instances once you've spun them up. And to do so, you're going to need login authentication credentials. So to do that, you're going to need to get a private and public key pair that you can use for signing in to your EMR cluster. So click on the EC2 service here. EC2 is the Elastic Compute Cloud, which is the underlying service that EMR uses to actually spin up the different computers in the cluster. So click on EC2, and you want to click on key pairs over here. And from here, you want to click Create Key Pair and name it something you'll remember. I already created one called Spark Key. So you might want to call it the same thing. And when you hit create, it will download to your downloads folder a sparkkey.pem file, which contains your public and private key pair. Make sure you actually download that file and keep it somewhere safe and back it up somewhere, because once you've downloaded it here, you can never get it again. Okay? You can always create a new one if you need to, but for security reasons, they make it impossible to actually re-download your public and private key. And that's in case somebody breaks into your AWS console account. They don't want them to be able to gain the credentials to actually get into all of the computers on your cluster and rack up a big bill for you. So I've already done that and downloaded it into my Spark course folder, and I have a sparkkey.pem file there. And if you're on Windows, you're also going to need some sort of terminal application so you can log into your master node on the cloud and actually get your scripts there and run them. And I recommend a program called Putty that you can search for if you need a terminal for Windows and you don't have it already. It will bring you to a website that looks like this. Not very fancy, and Putty itself isn't very fancy either, but it works. And you can either install the full Windows installer here, or you can just install the pieces you need. The only parts you actually need are putty.exe, which is the terminal application itself, and puttygen.exe, which we're going to need to convert our PEM file that contains our public-private key pair to a PPK file that Putty can use. So I've already done that and downloaded them into my Spark course folder. Hit pause if you need to do the same. And once you have that, you can open up puttygen.exe and click on load. And what you need to do is change this drop-down for the file filter to all files and select your sparkkey.pem file. And it will load that. And in order to save it as a PPK file that Putty can actually use, you now need to save it as a private key. I'm going to leave the key passphrase empty, because it just makes life a lot more complicated when you're actually trying to use this key file. And as long as you have, good physical security for your desktop, I wouldn't worry about it too much. If it does make you more comfortable to have a passphrase, put one in, but it's not as necessary as you might think. So I'm going to click on Save Private Key. It's going to say, you don't have a passphrase, but yeah, that's fine by me. And I will save it as sparkkey.ppk. I've already done this before, so I already have one. So I'm just going to overwrite the one that I have. And at that point, you have a sparkkey.ppk file that will let you log into any cluster that you spin up using the sparkkey key pair later on. Now, to actually use that PPK file within Putty, we'll open up Putty itself. And when you actually spin up your cluster, you'll get back a host name that you can use to actually log into the master node of your Spark cluster. But the first thing you'll want to do is go to the SSH tab here, open it up and click on Auth. And here you'll select your PPK file. And once you have that, you can just enter in the host name of the master node of your cluster, and you can log in automatically without having to sign in with the username and password. And that's actually more secure that way. So there you have it. You have an EMR, Elastic MapReduce, Amazon Web Services account ready to go, and you have a terminal ready and able to connect to that cluster as soon as you spin it up. So we want to make sure we have all these pieces in place beforehand, because again, time is money on that cluster once we spin it up, and we want to have everything we need ready to go. So we are now at that point. So now you have everything you need to actually spin up a cluster and connect to it. I'm not going to actually connect to it yet though, because as soon as I spin up that cluster, the clock's going to start ticking and my bill is going to start getting run up. So we're going to wait until the last second to actually do that, because like we said before, this really costs money, and you should be very, very careful if you're actually going to be running these clusters yourself, because if you forget to shut them down when you're done, if you forget to terminate them, you're going to get a very big bill at the end of the month, and it's going to be a lot bigger than the bill for this course. So I cannot caution you enough to be careful when you're experimenting with EMR and running Spark in the cloud, because if you leave those instances running, you're going to get a really big bill. So for that reason, you might want to consider just watching and following along with the videos here. But if you do choose to follow along with me and actually do these activities hands-on, remember to terminate your clusters when you're done, okay? I can't stress that enough. And with that warning, let's move on. So now that we are running on a cluster, we need to modify our script a little bit, our driver script. And we're going to be looking at the movie similarities example again and figure out how we can scale that up to actually using 1 million movie ratings. And to do so, you can't just run it as is and hope for the best. If you were to do that, it wouldn't actually succeed at all. Instead, we have to think about things like, how is this data going to be partitioned? And it's not hard, but it is something you need to address in your script. So let's cover partitioning and how to use it in your Spark script. All right, so let's talk about actually running our movie similarities script on a cluster. And this time we're going to talk about throwing 1,000,000 ratings at it instead of 100,000 ratings. Now, if we were to throw, just modify our movie similarities script to use the 1,000,000 rating data set from grouplens.org, it's not going to run on your desktop, obviously. The main reason why is because when we do that self-join to generate every possible combination of movie pairs, that blows up like you wouldn't believe. And you're just going to run out of memory and your job will fail pretty quickly if you just run it on your desktop. But even if you were to run it on a cluster on Elastic MapReduce, with no matter how many computers you throw at it, it's still not going to run. What will happen if you just run it as is that your executors will start failing and they'll just hang and you won't really know why. And it's not very easy to track down what's going on. And there's a lot of things about Spark that I love, but one thing that's not so hot is that it does not automatically, optimally spread out the work of your job throughout a cluster. You kind of have to think about that yourself and deal with it manually to some extent. And that's where partitioning comes in. So partition by is a method on an RDD that you can use to say, hey, I'm going to run some large operation, and I know I have enough compute resources to actually split this up into many different executors, many different runs. And that tells you basically how many pieces I want to break this job up into. So if we actually call partition by on the RDD that we do a self-join on first, we can then split it up into smaller chunks that a given executor can actually deal with, and then our job will actually complete successfully. And once you do that, that partitioning Spark will attempt to preserve that partitioning going forward as much as it can. So I want you to take a look at this list of different RDD methods: join, cogroup, group with, join, left outer join, right outer join, group by key, reduce by key, combine by key, and lookup. Some of these are very common. We've definitely used group by key and reduce by key a lot. And we've used join in this MapReduce, in this movie similarities example already. Anytime you're going to call one of these operations on a very large RDD, they will benefit by using partition by on it beforehand. So keep that in mind. And as part of your code review before running a large job on a cluster, look for places where you're calling any of these methods and ask yourself, do I need to call partition by on it first? Odds are you do. Okay. So how do I choose the argument for partition by? How many partitions is the right partition size? So, well, if you have too few partitions, it won't take full advantage of your cluster. It can't spread it out effectively. But if you have too many, you end up shuffling data around and breaking things up into too small of chunks. And there's some overhead associated with running an individual executor job. So you don't want too many executors either. But you want at least as many partitions as you have cores in your cluster, or as many will fit in your available memory. So, 100 is usually a reasonable place to start. Let's say you have, 5 or 10 computers in your cluster. That will split it up into a reasonable amount of operations. And I found that 100 actually worked well on my own example here across a cluster of 10 computers. So let's go back and make some modifications to our movie similarity script to both make it work on the 1,000,000 rating data set and also to make it work on a cluster by making sure we think about partitions. Okay, at this point we know about partitioning and we have the tools we need to actually go back to our movie similarity script and modify it such that it will run efficiently on a cluster with a much larger set of ratings. So let's do that next. So let's have a quick look at our movie similarity script that we're going to modify to run on the 1,000,000 ratings data set from Movie Lens. And we'll cover how we're going to address partitioning in this new script too. So let's take a look at the code. Okay, so let's modify our movie similarity script to actually work on the 1,000,000 rating data set and make it so it can run in the cloud on Amazon's Elastic MapReduce or any Spark cluster for that matter. So if you haven't already, go grab the movie similarities 1,000,000 Python script from the resources for this lecture and save it wherever you want to. It's actually not that important where you save this one because we're not actually going to run it on your desktop anyway. You just need to look at it and know where it is. So open it up just so we can take a peek. And I'll walk you through the stuff that we've actually changed here. Now, first of all, we've made some changes so that it uses the 1,000,000 ratings data set from GroupLens instead of the 100,000 ratings data set. So if you want to grab that, go over to grouplens.org and click on datasets, and you'll find it in the MovieLens 1M dataset, 1 million ratings. And this data's a little bit more current from 2003, but still pretty out of date. They do have a current dataset that is updated as of this month, but you're going to need a pretty large cluster to handle the 40 million plus ratings in that data set. So let's stick with 1 million for now, just to keep costs under control, if nothing else. Go ahead and download that if you want to. And when you get it, you'll see that it's structured a little bit differently, and we need to account for that in our script. So first thing we do, the movie ID to movie name lookup table is now in a file called movies.dat. And what I'm going to do is make sure that that file exists in the same directory as my script, as my driver script, when I'm running this on the master node of my cluster. So the function that just loads up that dictionary of movie ID to movie name is just going to look locally in our current directory for movies.dat. And we know that that's actually delimited by this double colon thing now, which is kind of a new format. But otherwise, it's doing the same thing as before. The other things that I've changed, notice that we're loading the actual ratings data from S3. This is Amazon's simple storage service, and that is actually a distributed and redundant data store. So if you are going to be dealing with really big data, often it's data that's going to be living in the cloud itself on some distributed file system. And if you have a HDFS data store, you could also have an HDFS URL here if you wanted to. This basically tells Spark, go out to Amazon's S3 service with this S3N URL, look in the sundog-spark bucket that I've created, and under there it knows where to find the large ratings.dat file that I got from the GroupLens 1 million ratings dataset. So technically speaking, you should install this yourself in your own S3 bucket, because you're not supposed to. You're supposed to go get it from their website and not from me, as according to their license agreement. But hey, secret's safe with me. The other thing I changed here is the format of that data file for ratings has also changed. It's also delimited by these double colon characters. So that's the only change I've made there. And one other thing worth pointing out is when I'm creating my Spark context, notice that my Spark conf object is empty. I'm not putting anything in here at all for what the master is or what the name is, because instead I'm going to pass that on the command line when I actually run the script on the master. And by doing so, I can take advantage of some pre-configured stuff on EMR, Elastic MapReduce, that will automatically tell Spark to run on top of Hadoop Yarn using the cluster that I've created using EMR. So if I were to actually keep my master equals local here, it would only run on the master node, and that's certainly not what we want. So by leaving that empty, it will fall back to the command line arguments and the built-in configuration files for Spark that Amazon sets up for me. So that's a very important point. If I did not change that, I wouldn't really be running on a cluster at all, and I wouldn't have very good results. So that's pretty much it. I mean, the main differences here, again, just to recap, are that I have moved my text file to be in the cloud from S3. I have left my Spark configuration empty, and I've changed the format in the file names of the data file to actually account for the differences between MovieLens's 1 million rating dataset and the 100,000 rating dataset. So we're just about ready to start spinning things up and start playing with it. Everything else is pretty much the same. One other note is that the IDs for movies have changed between the 100,000 and 1 million movie rating dataset. So Star Wars is no longer movie ID 50, it's movie ID 260. And I left myself a little bit of a cheat sheet up here as to how to actually run this on the cluster when we get there, but we'll talk about that more next. Okay, our code is now ready to run on a cluster on Elastic MapReduce using Spark on multiple machines. So let's find out how to do that. What do I actually have to do to run a script on a cluster? Let's find out. Okay, it's time to actually run our similarity script on a Spark cluster in the cloud on Elastic MapReduce. Pretty big deal. This is kind of the culmination of the whole course here, so let's kick it off and see what happens. So before we actually run our script on a Spark cluster using Amazon's Elastic MapReduce service, let's talk about some of the basic strategies that we're going to use here. So like we talked about before, we're going to use the default empty Spark conf in the driver script, and that way instead we'll use the defaults that Elastic MapReduce sets up for us, and that will automatically tell Spark that it should be running on top of EMR's Hadoop Yarn cluster manager, and that way it will automatically know what the layout of the cluster is, who's the master, how many client machines do I have, who are they, how many executors do they have, and whatnot. Now, when I'm actually running this, I'm going to need to pass one extra argument to Spark Submit. So in the past, we've always just called Spark Submit followed by the script name and whatever parameters we're passing into it. But there's a bunch of other options you can pass in too. And specifically, we're going to pass in --executor-memory 1G. And that's because I know from past experience that if I try to run this with a default memory of 512 megabytes per executor, that's not enough for that self-join operation to actually succeed. So by passing in executor memory 1G, I'm saying I want 1 gigabyte of memory per executor. And that should give me plenty to work with, throughout that partition that's been broken up into 100 partitions for that self-join. Anything lower just won't work. Really, the only way to figure this out is through trial and error, unfortunately. So, I tried the default setting of 512 megabytes. My executors kept failing. Increased it to 1 gigabyte and everything was happy. So no real science to it. You just have to experiment with what works and try to do that experimentation as quickly as possible because time is money on these clusters. So there are other options you can pass in as well. For example, --master yarn will tell Spark Submit explicitly to run on a yarn cluster, but EMR actually sets that up for us by default. However, if you're running on your own cluster, you might need to pass that in by hand. Okay. Now, ahead of time, I've copied everything to AWS's S3 service just so I can access all of my scripts and data files that I need quickly. And I can use that to quickly copy over my script from S3 and also refer to my large, big data, if you will, using S3N URLs so that I can just load my data directly from Amazon's S3 service. One good thing about using Amazon Web Services EMR cluster is that it has very fast and very good connectivity to S3, so S3 becomes a good choice for a distributed file system to use together with EMR. You can also spin up an HDFS file system as well if you want to. All right, so our next thing we'll do will be to spin up an EMR cluster for Spark using the AWS console. The clock starts ticking on our bill at this point. As soon as those clusters become available, we'll get the external DNS name for the master node and log into it using PuTTY. And we will then copy our driver program, run it, let it run and watch the output. And as soon as we're done, we're going to terminate that cluster so that we stop getting billed for that time. Very important. That's in all uppercase and bold letters for a reason. So if you do in fact follow along with me, don't forget, terminate the cluster when we're done. So let's go and start the process. All right, it's time to actually run this script on a real Spark cluster in the cloud. And here we go. So again, remember that we're going to be racking up some real charges here. It's going to cost real money to run this on Amazon Web Services. So feel free to follow along as long as you're careful to remember to terminate your cluster when you're done. It should only cost you a few dollars to run this once. But if you have any doubts about your ability to remember to terminate this cluster, don't do it. Just watch me do it, okay? It's going to be cheaper and a lot safer that way, but follow along at your own risk, okay? You have been warned. All right, now to make life easier, I've actually gone ahead and copied the 1 million ML1M 1 million rating data set to a Sundog-Spark bucket on Amazon's S3 service so that my Spark cluster can access it. And I've also copied the script itself to my Sundog-Spark S3 bucket as well. So that way I can quickly obtain a copy of it from my master node on my cluster. So once I spin up that cluster, first things I'm going to do, because time is money, the clock starts ticking right away, I'm going to call this little script to actually copy the movie similarities 1m.py script from S3 to that master node. And then I'm going to copy over the movies.dat file that it's going to use to load up and create that movie ID to movie name lookup table that it's going to use in the final output. And finally, I left myself a little cheat sheet of what to actually run to execute this job. Okay, so let's do it. Go to the aws.amazon.com console, and we're going to go to the console. I'm going to sign in, and I'm going to click on EMR. And I'm going to create a new cluster. I'm going to call it 1 million similarity, or 1 million ratings, more specifically, right? 1 million ratings. I don't really need logging because there's no easy way for me to look at it anyway. I'm just going to go ahead and launch the cluster as opposed to using steps. And we are going to use the latest EMR release. And we want primarily Spark. So to save a little bit of time, I'm not going to bother installing Hive and Mahout and Pig and stuff that I don't need. I just want Spark 1.5 running on top of Hadoop's Yarn Cluster Manager. And I will stick with the default m3.xlarge instances, 3 of them. Let's go with 5. More is better. All right, for the key pair, remember in the previous lectures we actually created a key pair, and we need to select that now. So for me, I'm using the Spark key pair. This will correspond to the PPK file that you're going to use to connect to your master node using PuTTY or whatever terminal you have. And I will leave everything else as the default. Okay. Here we go. Create cluster. At this point, the bill starts adding up. So again, don't hit this button unless you're comfortable with spending a few dollars here and you're comfortable with your ability to terminate this cluster as soon as you're done using it. Okay. If you're not comfortable with that, just watch me. Here I go. All right, now it's going to take about 5 minutes for these to actually get provisioned. So what's happening under the hood here is Amazon's Web Services Framework is going out. It's finding 5 available m3.xlarge instances, computers out there in its data centers that I can have, and it's going to reserve those for me. It's going to install the operating system on them. It's going to install Spark, and it's going to install Hadoop. And that will take a few minutes. So until this actually says, stop saying provisioning and actually says that these systems are actually ready to go and started, we can't actually do anything quite yet. So through the magic of video editing, we're going to cut here, and I'm going to come back in about 5 minutes when these systems should be all spun up for me. So I'll be right back. Okay, through the magic of video editing, we're back about 5 minutes later, and sure enough, my instances have spun up. So I now have a running master node of one M3 xlarge instance and 4 core nodes of an M3 xlarge running as well. So let's go ahead and, without further ado, connect to that and kick off our script because the bill is going here and time is money. So up here we have the public DNS name of our master node. And if you click on the SSH tab here, it will actually give you instructions on exactly what you need to do to connect to it. And we have instructions for both Windows, which I've been describing, and also for Mac and Linux. So if you are doing this from Linux or Mac OS, this will tell you in a little bit more detail what you need to do. Again, you just need that sparkkey.pem file that we got from the key pair from EC2 earlier. And you can type in something like this to actually connect into it. But we are using PuTTY, so I'm going to copy this bit here, which is what I need to type into the hostname field. And go ahead and open PuTTY. I'm going to paste that into the hostname. And I'm going to go to my SSH section, go to auth, and select my PPK file that I created earlier. And that should get me right in. Yeah, I know, we're fine. And there we are. Isn't that cute? ASCII art. All right, now it's time to get busy. Let's kick this thing off. So if you recall, I left myself a little cheat sheet here in my script comments of what I need to do. So let's go ahead and do all of this. First thing I want to do is copy the script itself down. So I'm going to type in AWS S3 CP S3://sundog -spark /movie similarities 1m.py/. And what that's going to do is go out to S3 and copy my Python script, my driver script, here to this local directory here in my home directory. I also need the lookup file for movie IDs to movie names, so let's do that next. AWS S3 CP S3://sundog -spark /ml-1m /movies.dat, also to the current directory. And there we have that. Finally, I'm going to kick off the job itself. Here we go. Spark-submit --executor-memory 1G to give 1 GB of memory per executor. And the name of the script, movie similarities 1m.py. And finally, the movie ID for Star Wars, which I am interested in getting similarities for. And off we go. All right, I'm going to let this go a little bit just to make sure everything's happy. You can see it's doing all sorts of stuff, and we're getting a bunch of info messages that we had filtered out on our desktop configuration, but while you're running on the cluster, you want a little bit more insight as to what's going on in case something goes wrong. Alright, you can see here that it's already kicking off that sort by key operation here with 16 output partitions. Doing all sorts of good stuff here. Alright, I'm going to come back later and we'll revisit this because this will take a little bit of time to finish. And we'll take a look at the results when it's done. Well, there we have it. We've kicked off our job. It's running on a cluster at this point. Pretty awesome. I'd say we're actually, doing big data now. And we're running it on a Spark cluster in the cloud. So let's let that run and we'll take a look at the results in our next lecture. Okay, time has passed, so let's review what happened and look at our results from our 1 million rating movie similarities run. Alright, about 15 minutes later, we have some actual results here to look at. So let's take a look at what we ended up with. After analyzing 1 million ratings and using that same script, our results were, for the top similar movie to Star Wars Episode 4 was Star Wars Episode 5, not too surprising. But the next entry is a little bit surprising, some little movie called Sanjuro that had a very high similarity score. But let's look at what's going on there. Its actual strength, the number of people that actually rated that together with Star Wars was only 60. So, I think it's safe to say that's kind of a spurious result. And now that we're using 1 million ratings, we probably need to increase that minimum threshold on the number of co-raters in order to actually display a result. So by doing so, we could probably pretty easily filter out movies like that and instead get Raiders of the Lost Ark as our second result, which I think is interesting because it's actually scoring better than Return of the Jedi. So, I'm no film critic, but maybe you too also enjoyed Raiders of the Lost Ark more than Return of the Jedi. I know I did, so that's not that crazy. We then get Run Silent, Run Deep from 1958. Again, kind of a spurious result with only 145 co-raters, and that sounds like a lot of people, but in the context of 1 million ratings, not so much. So, moral of the story is a lot of times you need to go back and kind of adjust your algorithms and clean your data a little bit differently when you're running at a larger scale to get the results you want. So, data mining and using big data is not magic. You do not automatically get better results just because you have more data. In fact, often the opposite is true. So let that be a lesson to you. But hey, we actually successfully ran this thing, so that's a cool thing. Let's shut down this cluster before we forget. Okay, so now that I have a result, the most important thing is to remember to terminate that cluster so I don't keep getting billed for it. That would be bad. All right, so let's go to the console.aws.amazon.com, and I'm going to click on EMR and find my cluster. There it is with the green circle next to it, meaning that that is currently running. Racking up a bill for me, but let's shut it down. So let's click on that cluster and then click on Terminate. Am I sure? Yes, I'm going to lose everything. I'm totally okay with that. Just stop billing me for it. All right, and you want to make sure that actually terminates and that the status actually goes from running to terminated. And assuming you do, you will stop getting billed. And that's all there is to it. All right, we have successfully run a 1 million ratings analysis on a cluster on Elastic MapReduce using Spark on top of Hadoop. And we've shut down the cluster now that we're done with it. Pretty cool. And there you have it. Movie similarities from 1 million ratings running on a cluster in the cloud on Elastic MapReduce using Spark. Pretty awesome. Remember to terminate your cluster when you're done, okay? I'm just going to keep saying that over and over and over again because you don't want the bill if you're actually running this yourself. Terminate any clusters in the Amazon Web Services console using the EMR tab, okay? If you leave those running, you're going to get a big bill and you're not going to be happy. But hey, we got results. That's awesome. You are now officially processing big data in the cloud. That's what this course is all about. So congratulations. Let's talk about troubleshooting jobs next and what you need to do when things go wrong. So let's start talking about what we do when things go wrong with our Spark job. It has a web-based console that we can look at in some circumstances, so let's start by talking about that and have a look at it. Let's talk a little bit about troubleshooting Spark jobs on a cluster, and honestly it's a little bit of a dark art. I mean, usually if it's not immediately obvious from the output of the Spark driver script what's going on, a lot of times what you're going to end up doing is just throwing more machines at it, throwing more memory at it, like we looked at with the executor memory option there. But if you're running on your own cluster at least, or one that you have within your own network, Spark does offer a console UI that runs by default on port 4040. And it does give you a little bit more of a graphical, in-depth look as to what's going on and a way to access the logs and see what executor is doing what, and that can be helpful in understanding what's happening. Now, unfortunately, in Elastic MapReduce, it's pretty much next to impossible to actually connect to Spark's UI console from outside of Amazon's network. But if you have your own cluster running on your own network, it might be a good option for you. So just so you see what it looks like in case you end up using a Spark cluster that's run by your employer or something, where you do have access to the console, let's take a look at it just running on our local machine. So we'll kick off a larger similarities build script and take a peek at it, see what it looks like. So real quick, let me show you the Spark UI, the console, if you ever need it. If you're running on if you have local network access to your master node on your cluster, then you should be able to access this on port 4040. So let me kick off a script that takes at least a minute here, our original movie similarity script here on my desktop. And we'll kick that off. And as soon as that starts, I can open up a browser and navigate to localhost :4040 to open up port 4040 on my computer. And you can see here we have this display of any active jobs currently running, and we can click through on that to drill in and see some cool stuff. We have an actual visualization of the directed acyclic graph that Spark used. We have a timeline here that we can use for troubleshooting where all the time is being spent in our job, for example. So we could click on one of these and get more details on that stage. And you can just drill down there and try to figure out what's taking all the time and what you might need to optimize, what might need to be partitioned better. Another useful thing is the environment tab here, which tells you all the various paths and dependencies and software versions that are installed. So if you're running on a cluster that you don't necessarily have direct control over, that can be useful information. And I think our job already finished, but I pretty much showed you everything. We can kick it off again just to go through it again. So executors actually shows individual executors, and you can drill into thread dumps and actually see what's going on here in as much depth as you want to. The Stages tab also shows you details on each individual stage running. So yeah, if you need to get more insight into where your Spark job is at, where it might be stuck at, and things you might need to optimize, this gives you all the information you might need. So it's actually pretty slick. There you have it. So there you have the Spark console. Like I said, it's hard to get to on EMR. That might change in the future. I hope it does. But if you're running on some other cluster that you have more direct access to, or even in your own within your own network, it's a good way to figure out what's going on and get a good sense of how long different steps are taking. You can also just watch the output of your driver script too to get a good sense of what's going on as well. But obviously the UI gives you a better sense of what's happening under the hood. So let's talk about some more troubleshooting tips next. So next I want to talk about a few more troubleshooting tips with Spark. There are weird things that will happen and have happened to me in the past, and not always obvious what to do about them, so let me impart some of my experience upon you here. And then we're going to talk about managing code dependencies within Spark jobs as well. So let's go there. So let's talk about troubleshooting a little bit more, and I can tell you I did need to do some troubleshooting to get that million ratings job running successfully on my Spark cluster. So where are the logs? I mean, we saw some stuff scroll by from the driver script, and in practice, if you're running on EMR, that's pretty much all you're going to have to go on. Now, like I showed you, if you're in standalone mode and you have access directly, on the network to your master node, all the log information is displayed in this beautiful graphical form in the web UI. But if you're running on top of Yarn, those logs end up getting distributed, and you need to collect them after the fact using this command yarn logs -- your application ID and use that to actually bring them all back together so you can see them. Your job is distributed, and so the logs are distributed, and that makes them a little bit difficult to actually consolidate and look at what's going on. But a lot of times you can kind of intuit what's happening. What happened with me when I was trying to get this movie similarities with 1 million rating script running was that when I first started running it, I kept getting errors in the driver script that said that executors were failing to issue heartbeats. So it would kick off an executor to do some job, and that executor would just go away and never respond again, and it hung, right? So when that happens, it's probably a good sign that you're just asking too much of each executor. So one thing is you can throw more machines at it, and indeed I found that by going up to 10 machines in my cluster, it ran a lot more reliably than with 4 or 5. And it might also mean that each executor may need more memory. So even after doing that, they still hung unless I gave them 1 gigabyte per executor, like we did earlier. with the default value of 512 megabytes. It just wasn't enough, even with 100 partitions. And that brings me to the last point. You can always increase the number of partitions in order to demand less work from each individual executor job by using smaller partition sizes to split up your job into smaller bits. So whenever you have executors that just get hung like that and they start losing their heartbeat, Spark's going to start to try to destroy those executors and create new ones to try again. But after about 4 tries, it's just going to give up and your entire job will fail. So even though Spark and Hadoop and Yarn build themselves as being extremely fault tolerant, at the end of the day, if you're asking too much out of one of your executors and it just plain can't do it, your job will still fail. So don't rely on fault tolerance from Hadoop to ensure that your script will actually run successfully, because there is no such guarantee. Now, once you've configured things such that you are asking a reasonable amount of work from each executor, then yeah, fault tolerance does what it should be doing. And if you have a genuine failure of one of your nodes or some weird network area, then yeah, it can recover from that. But nothing Hadoop does can recover from poorly structuring your code, having a wrong number of partitions, having not enough memory, or asking too much of each executor. Those are problems you need to identify and fix before you put your job into production. Okay? Other thing I want to talk about is managing dependencies. So something to remember, even if something runs perfectly on your desktop doesn't mean it'll run on your cluster, because you might not have the same Java environment, you might not have the same Scala environment, you might not have the same Python environment. That could be an issue. Now, another point too is like the same data won't be there. So if your scripts are referring to absolute file paths or file paths on your local desktop system, you're going to want to make sure you fix those before you run them on the cluster. One thing you can do is, refer to a path that's on some distributed file system that each node has access to, or you can use things like broadcast variables to actually share data outside of your RDDs and broadcast that to all of the nodes. But still, your master node needs to get to that data somehow originally before it can broadcast it to all the core nodes. And, try not to depend on obscure Python packages. Now, if you do have a driver script that needs some weird Python package as a dependency and it's not preloaded on your Spark cluster, you can always set up a step in Elastic MapReduce to run pip and install whatever you need before it actually, as it's in the process of spinning up each node. There's also a --py-files argument you can pass to Spark submit to add individual libraries and pass them off to the executor nodes. But again, that's only going to work if you already have the packages you need on the master node. So you kind of have this chicken and egg thing going on. I mean, pip is probably the only realistic way to deal with this problem if you have to. Otherwise, you still have to get what you need to the master node somehow. But honestly, just try to avoid using obscure packages if you can. I mean, time is money in your cluster, and the less time you spend fiddling with dependency issues, the better. So if you don't need some weird package that doesn't come pre-installed on your cluster, don't use it. That's the best solution. If you do need some weird cluster, you can use a step in the EMR process to actually get that installed as part of the Bootstrap process for setting up your individual nodes. And that is my brain dump on running Spark in a cluster. All right, this concludes the part of the course about Spark Core, the things you can do with Spark itself. And we've done pretty much everything there is to do, and we've actually run 1 million ratings analyzed on a real cluster in the cloud using Spark. So congratulations, you are now pretty knowledgeable about Spark if you got this far. Next, we're going to talk about some of the technologies built on top of Spark that are still part of this greater Spark package, and that'll be our last section. Let's go ahead. So let's spend some time talking about Spark SQL. This is an increasingly important part of Spark, and basically lets you deal with structured data formats. So instead of these RDDs that contain arbitrary information in every row, we're going to give those rows some structure, and that will let us do things like treat our RDDs as little databases. So we're going to call them data frames and data sets from now on, and you can actually perform SQL queries and SQL-like operations on them, which can be pretty powerful. So structured data, basically we're going to extend the concept of an RDD to a data frame object, and this is just imparting some structure. So it's basically an RDD of row objects is how you can think of it. Now, by doing this, we can construct SQL queries. We can have distinct columns in these rows, and we can actually form SQL queries and issue commands in a SQL-like style that we'll see shortly. And because we have an actual schema associated with the data frame, that means that Spark can actually do even more optimization than it could normally. So it can actually do query optimization just like you would on a SQL database when it's trying to figure out the optimal plan for executing your Spark script. Another nice thing is that you can directly read and write to JSON files or JDBC compliant databases. So if you do have your source data that's already in a structured format, like inside a relational database or inside JSON files, you can import that directly into a data frame and start to treat that just like you would a SQL database. So very powerful stuff. In Python, it's pretty straightforward to use. There's actually a couple of different interfaces, and we'll look at that in the examples in more depth. But in short, you can, like I said, import things directly from a JSON file. You can import things directly from a Hive database. You can connect directly to a JDBC database. And you can also convert RDDs to data frames if you know their schema under the hood. Once you have a data frame, you can do things like create or replace temp view to actually create a table in memory that you can actually issue SQL queries on. So pretty cool stuff. And then you can actually do stuff like SQL, select foo from bar, order by foo bar, whatever you can dream up. And you don't even have to use SQL queries. There are ways to do that programmatically as well. So it's a very powerful syntax. For example, you can call show if you're debugging to just show the top 20 rows in your data frame. You can select a given row and create a new data frame out of that. And another neat thing is that you can actually construct these little expressions in here. So for example, you could do .filter with my result data frame, some field name greater than 200. That would filter out from the data frame anything where a given row's some field name column was greater than the value 200. So you can do these very intuitive syntactic expressions to actually express complicated logic inside your queries. You can also do group by on a data frame and do a mean or a count or whatever you want on that. So things that were kind of more challenging earlier in the course, like just counting up the number of a given movie rating or a number of ratings for a given movie ID, suddenly become a lot simpler. We don't have to go through all these contortions to map things to key value pairs where the value is 1 and then count up and add up all those ones together. You can just do group by and count, and you're done with one line of code. So again, this is a higher level API that actually gives you a lot more power, and it can often result in much simpler code. So in general, if you can express your problem in terms of data frames, you should. Now in Spark 2.0, they talk about data sets. And this can get a little bit confusing because up until Spark 2.0, people talked about data frames a lot, and it kind of got its way into the lexicon of Spark. People talk about data frame APIs, but in Spark 2.0, all a data frame is a data set of row objects. A data set is just a data frame of structured data. So it can contain more than just a row object, it can contain a specific type of class. Now, this is more important if you're coding in Scala or Java. Since Python's untyped to begin with, you're not really gonna sense the difference when you're coding Spark code in Python, but you just need to be aware of the terminology. So when people talk about data sets, they're really talking about a data frame full of structured data. And more accurately, a data frame is a data set of row objects. So a data frame is a data set, okay? So within Python, you can kind of use those terms interchangeably. But given the choice, use a data set. That's the way to go in the future. Another cool thing about Spark SQL is that you can actually expose a shell that you can connect to. So if you actually cache a table, you can actually connect to it by starting up a little server and issue SQL queries to it just like you would any other database. So think about how that powerful that is. You can actually have a Spark cluster running that encompasses a massive database that's spread out across an entire cluster of computers. And you can query that cluster just as if it were a relational database using a SQL prompt. And if you're using, for example, Databricks has something called the Databricks Community Edition, which is a product that lets you play around with Spark inside of a Python notebook. And you can actually just issue SQL queries interactively using that system as well. So it's kind of a neat feature. One last thing to talk about with Spark SQL, you can also have user-defined functions. So you can define your own functions. For example, here we're going to define a square function that takes x and returns x times x. And once you define that function and register it, you can actually use that within your SQL queries. So you can actually extend the SQL syntax yourself to actually do specialized operations, and that will get executed across your cluster automatically. So let's look at a few actual examples of using Spark SQL. We're going to do three things. First, we're going to look at using SQL commands directly. We're going to look at using more SQL-style functions in a problem. And finally, we'll look at going back to an RDD-based solution that we did earlier in the class and actually implementing it with data sets instead. So again, data sets are the way of the future in Spark 2.0. You're going to see that it's being used more widely as a common interface between the different components of Spark. So MLlib now has a dataset-based API. Spark Streaming has a dataset-based API. So data sets are a very important concept to understand, especially as Spark develops in the future. So let's go and look at some examples. All right, so go ahead and open up the spark_sql.py file that's included in the course materials and attached to this lecture. And let's take a look at it as a real-world example of using Spark SQL in Spark 2.0. So you can see we're importing a few things here. We're importing the Spark session object and the row object. And Spark session is basically the Spark 2.0 way of creating a context to work with Spark SQL. And we'll import collections as well. So before we used to create Spark context objects, but instead we're going to create a Spark session object this time. So what we're doing here is we're creating something called Spark that's going to be a Spark session. We use a builder method on that, and then we can just string on these different parameters to actually get back a session that we can work with. And this will give us back not only a Spark context, but also a SQL context that we can use to issue SQL queries on. So the first bit here, this config spark.sql.warehouse.dir, that's only needed on Windows. It's kind of working around frankly, a bug in Spark 2.0. So if you're not on Windows, go ahead and delete that part of it, okay? The part that I've highlighted. If you are in Windows, leave that in and make sure that you have a temp folder under your C drive, or else point that to someplace else, okay? All right, we're going to give it an app name of just Spark SQL, and then we just call get or create to actually go and make it. So that gives us back a Spark session that we can start using. Now, what we're going to do is take that fake social network data that we had in an earlier example, and we're going to this time use SQL queries to analyze it instead of doing RDD operations. Now, unfortunately, that data is not structured to begin with. It's just a CSV file, so it's just a bunch of text as far as we're concerned. So before we can actually import that data into a structured data frame object, we first need to impart some structure to it. So just like we would normally, we're going to just open up the text file and give it to a mapper that will actually convert that into a row object. So this is basically converting an RDD that's splitting out the comma separated values into a data frame. Remember, a data frame in Python is really just an RDD of row objects. So let's go into this in a little bit more detail, give it a little bit more attention. So first of all, you can see that we're calling Spark context on that Spark session object we made. That gives us, the same kind of Spark context that we've had previously in the course. And from there, we can just call text file with fakefriends.csv. And now that we have that, we can pass that into our mapper function, which just splits up each line by commas. And then it creates row objects, where we're actually giving some structure here. We're saying that we're going to have an ID column that consists of the customer ID, a name column that consists of a string name. We're going to have an age column that is an integer-based age, and we're going to have a num_friends column that is an integer-based number as well. So this little bit here is basically imparting structure and a specifically typed information back to our RDD. So under the hood, Spark can use that information about how each row is structured and what these columns are to more compactly represent the data frame under the hood and deal with it in a more optimal manner. Okay, so at this point, you can think of people as almost being a data frame. We just need to call spark.createDataFrame to actually officially make it a data frame and take those row objects, that RDD of row objects, and treat it as a data frame. Now we're going to cache that because we're going to do more than one thing to it, okay? So because we're going to reuse that schema people data frame, we're going to cache that. So first let's start by actually issuing actual SQL queries on it. So we can call create or replace temp view, and what this does is create sort of a temporary SQL table in memory called people that we can issue queries on. And since schema people is now a data frame, it's gone and looked at those rows and looked at the names of those rows and created columns. So again, looking back at how we define this row, these are our column names, and we can issue those in actual queries. So we can say teenagers equals Spark, that's our Spark session.sql, and we can just write out, just like it was a SQL database, select star from people, that's the name we gave to our temporary table, where age is greater than or equal to 13 and age is less than or equal to 19. And because we defined our row up here with a name of age, it knows that the age corresponds to the third column of that data frame. So it all just works. It's kind of magic, but it's pretty cool. So there you have a very high-level API. We can just issue arbitrary SQL queries on a data frame. All we had to do was structure our data and input it into a data frame using row objects, and we can do that. So at that point, I could just call teenagers.show to kind of print out the top 20 results, or I can treat it like an RDD. I can say I can collect the results and print that out, and that will print out the individual row objects of that data frame. Okay, so we'll do that. Now, you don't have to use SQL queries either. It's arguably a little bit more efficient to use SQL-style functions instead. So here's a way to do that. So remember in previous lectures, we had to kind of jump through some hoops to reduce things together and actually do things like count people up by how many people of each age there are, for example. We can do that with one line of code using data frames. So take a look at what we're doing here. We're using that cached schema people data frame, and we're calling group by the age column and count. So that's exactly like issuing a SQL query that's group by age, count, and then ordering the results by age and then showing them. So what this is going to do is group together all the people of a given age, count them all up, and then at that point we have a data frame of ages and how many people of that age occur in the data frame. We will order that by age so that it gets sorted by age and show the top 20 results. So in one line of code, we've done what would have been a more complicated and convoluted implementation just using straight up RDDs. We don't have to actually create key value RDDs where the value is 1 and then reduce them together to count them up. We can just say group by and count to do the same thing in one line. So let's see how that works. So let's actually run this and see if it actually does what we think it will do. So open up your command prompt and go to wherever you are storing your course materials, and we'll say spark-submit spark-sql.py. And you could do this just as well in the interactive Python prompt as well. And there we have it. So check it out. That first thing we did was print out the actual contents of the data frame that we had after doing that select star from people where age is greater than or equal to 13 or less than or equal to 19. So that should give us back all the teenagers in our data frame. And sure enough, it does. And what we're getting back are the actual row objects of that data frame with the individual named columns inside each one. So giving you a little bit of a peek into the inner structure of that data frame. Now I could just call show and it would show that in a more compact manner, or I could actually do a select command on that to actually extract specific rows that I care about, for example. The next thing we did was actually use this syntax here to count up how many people of each age exist and sort that by age. And sure enough, that worked as well. That's this output here, and you can see that in our data set we had 8 18-year-olds, 11 19-year-olds, and so on and so forth. So we just the show command will just print out the top 20, but you could collect the whole thing and print it out if you wanted to as well. So there you have it, Spark SQL in action. Like I said before, this is the direction that Spark is going toward. So as you can see, it's a very powerful and higher level API, and it also allows Spark to do more optimization under the hood. So while not everything can be thought of in terms of SQL queries, a lot of times it can. And if it can, you should use data frames instead of just straight up RDDs. It may seem a little bit counterintuitive that this higher level API can actually be faster and more efficient, but it does allow Spark more opportunities to optimize things under the hood when you're using this higher level API. So again, data frames, very important to understand. It's so important, I want to go into an example of actually going back to one of our earlier exercises using RDDs and solving it using data frames instead. So let's do that next. So just to drive home how you can actually use data frames instead of RDDs, let's go through an example of actually going to one of our earlier exercises that we did with RDDs and converting it to use data frames instead and see how it might be a little bit simpler. So what we're going to do is go back to that example where we figured out the most popular movies based on the Movie Lens dataset ratings information. So let's have at it. So we'll start by importing Spark Session, which again is our new API in Spark 2.0 for doing data frame and dataset operations. We'll import the row, class, and functions so we can do SQL functions on it. We have our load movie names function here that just creates a map of movie IDs to movie names, and that's unchanged from the earlier example. We're just going to use that to look up the movie names as we're printing out the results at the end. So let's get into the meat of the script. We'll create a Spark Session object just like we did earlier. And again, make sure that if you're on a non-Windows system, you delete this config clause here. That is only needed on Windows, and it's only to work around a Windows bug in Spark 2.0. So if you are on Windows, leave that on and make sure you have a ctemp folder. If you're not on Windows, delete that part. We'll give our app a name of popular movies, and we'll then have a Spark Session object that we can work with. So first we'll load up our dictionary of movie IDs to movie names that we'll use later in the script for printing out human-readable results. But we'll start by just getting the Spark context object that's part of our Spark Session and calling text file to import our unstructured data initially. So u.data, again, is just a text file as far as Spark is concerned. Now, if that was in a structured format like JSON, we could do instead something like spark.read.json, and that would convert it directly to a data frame, which would be pretty cool. But in this case, we have to first impart our own structure onto it. Fortunately, it's pretty simple. What we're going to do here is call map, just taking each line of the input and creating a row object that consists of a single column named movie ID. Since all we're doing is counting up how many times each movie ID occurs, the only column that we really care about is the movie ID column. So we will go ahead, split that row up, and extract column number 2, and call that movie ID. So what we're going to have now is an RDD called movies that consists of row objects, where each row consists of a single column named movie ID. We can then convert that to a data frame, which will allow Spark to treat it as just a little miniature database, really, and that will give it all the opportunities of optimizing queries on it. All right, so at this point we have a data frame called movie dataset. And remember, a data frame is just a data set of row objects as far as Spark terminology is concerned. So now we can do something like this, kind of like in our previous example. We'll do movie dataset group by movie ID. And again, we just know from this row object that we constructed that that is the name of that column, movie ID. Count it up by movie ID, order it by count in descending order. So we can pass this extra parameter to order by that says, I want you to go in descending order and therefore get the most popular movies on the top. I'm then going to cache that resulting data set because I'm going to do more than one thing to it. So at this point, I can show the top 20 results with a show command that's very handy for debugging, and I should get something that looks like this. Just a new data set that consists of my original movie ID column and a new count column that was added by this count command, okay? And finally, to get the results I want, I can call take 10 to get the top 10 results out of that data set and print them all out using my name dictionary that I had earlier to actually map the names to human-readable movie names. When I'm done, remember to stop the session. From a coding standpoint, this Spark session is just like opening a connection to a database, and you want to make sure you close that connection when you're done. So let's go ahead and run this puppy. I'm going to open up a command prompt to where I put my course materials, and again, if you want to do this through a Canopy command prompt, that's fine too, doesn't really matter. Just showing you more than one way to do it. Spark-submit popular movies dataframe.py, just like that, and let's go ahead and run that. It's a large data set, 100,000 ratings, remember, so it's going to have to chug away on this a little bit, do a little bit more work than we normally do. It's actually breaking it up into multiple stages for us. And there we have it. So remember, we started off by printing these intermediate results here, where we looked at the contents of the top movie IDs data set. And you can see that we ended up with our movie ID column and our count column that was added by the count command. So we're seeing the list of movie IDs and their total counts. And we just showed the top 20 for debugging purposes. And to get our final results, we took the top 10 and mapped them to their human-readable names using our dictionary. And the results are the same as before. So you can see Star Wars is the most rated movie, just as we expected, followed by Contact, Fargo, Return of the Jedi, Liar, Liar, and The English Patient. This data set is showing its age from the 1990s, but it is accurate data, so there you have it. But it is interesting how you can actually use these higher-level APIs using Spark SQL. And remember, to do the same thing that we did in this one line of code, we had to kind of jump through some hoops and create key value RDDs and reduce that RDD down and all sorts of nonsense that wasn't very intuitive. But by using Spark SQL and data sets, you can do these exercises in a much more intuitive manner. And at the same time, you're allowing Spark the opportunity to represent its data more compactly and giving it the opportunity to optimize those queries in a more efficient manner. So again, data frames, the way of the future with Spark. If you do have the choice between using an RDD and using a data frame to do the same problem, opt for the data frame. Not only is it more efficient, but it will give you more interoperability with more components within Spark going forward. So there you have it. Spark SQL, data frames, and data sets in a nutshell, in action. Remember this lesson, it's very important going forward. All right, let's move on. So if you're doing any sort of real data science, data mining, machine learning stuff with Spark, you're going to find the MLlib library very helpful. It's a bundled piece of Spark, so it's always accessible to you. And MLlib stands for Machine Learning Library, and it has a lot of useful functions. So let's review what some of those are and take a look. So let's talk about MLlib. This is a library built on top of Spark that's part of the Spark package, and it contains some useful libraries for machine learning and data mining and some functions that you might find helpful, so you don't have to reinvent some of these functions. And when we're done, we'll actually use it to generate movie recommendations for users using the Movie Lens dataset again, only much simpler. So I don't really have time to go into what machine learning is and what all these different techniques use, but if you are coming from a data science background or a statistics background or a data mining background, these should mean something to you. I'll go through them real quickly, but these are all different features of MLlib where they have support in the library to help you with these various techniques. So feature extraction, a very common approach to handling search, especially for web pages, is term frequency inverse document frequency. And MLlib has some built-in ways to compute that given RDDs. So if you're dealing with a massive corpus of, say, web pages, if you're, say, a big web search company, for example, you might find a way of distributing that through a Spark cluster to be very useful, and MLlib can help with that. Also it gives you some very basic statistics functions. So if you just want to very quickly find out the minimum or maximum value in an RDD or the mean or the variance of an RDD, it provides functions to do that real quickly. And it also gives you ways to compare two RDDs together using Pearson or Spearman correlation functions. And it gives you functions for the chi-square test. So, even if you just take Statistics 101 or go read Statistics for Dummies, you should learn what all of those various terms mean if you don't know already. It also has functions for linear regression and logistic regression. So if you have an RDD full of data point that is, a time series of some sort, you can predict future performance based on past performance just by, basically fitting a curve to the set of data and extrapolating it to where it goes. MLlib can help with that. Support vector machines, naive Bayes classifiers, decision trees. So naive Bayes, a common example there is a spam filter, actually training a Bayes classifier as to what is spam and what is real email by giving it a set of known spam and known email. And you can use that to actually try to classify future emails as spam or not spam. So that's an example of supervised learning. Decision trees. So you can actually use MLlib to construct decision trees from a group of data and actually automatically compute, what tree of various conditions do I need to follow in order to get to a certain point in my data? So there's some cool stuff you can do there. K-means clustering, a way to automatically discover interesting groups that exist in your data. And finally, we have principal component analysis and singular value decomposition. Very big, complicated topic there, but it's a very powerful one. I've actually used that in the past for movie recommendations, and although it's a very expensive thing to do, splitting it out on a Spark cluster makes it a little bit more accessible, which excites me because the results I've seen from that have been creepy good. I mean, SVD-based approaches, you have to wonder if it's some insight into how the human brain works because it really borders on artificial intelligence, what can come out of this stuff. So I'm excited to see what people do with that part of MLlib in the future. And finally, it gives us a recommendations algorithm built in using alternating least squares. And that's important because that's actually the approach that the Netflix prize took. So a long time ago, Netflix actually offered a large cash prize to any researcher that could improve upon their movie recommendation algorithm. And the winner was actually an approach that used this technique called alternating least squares, and that is built in to MLlib. So if you want to create recommendations of not just movies, but anything else, and that can actually be based on either explicit ratings, like we've been seeing in the Movie Lens dataset, or implicit ratings, which might just be the act of somebody viewing something or purchasing something. MLlib has a way of doing that with just a few lines of code. So since we've looked at movie recommendations before in this course, let's do it again. Now, one thing you need to understand with MLlib is that it does have a few special data types. For example, it has a vector type that can be either dense or sparse. Sparse vectors can be useful if you have a matrix in machine learning where most of the cells are empty. So it's a more compact way of representing vectors or arrays of data where a lot of the values have nothing in them, and that actually happens pretty often when you're doing things like recommendations. It also has labeled points, so you can actually attach some sort of meaning to a data set, a data point. And finally, in the context of recommendations, it has a rating type that we'll look at right now. And if you want to learn more about this stuff, like I said, there are various basic statistics books, and we'll get into more resources you can go into at the end of this course. But a quick recommendation, I like the book Advanced Analytics with Spark from O'Reilly, because not only does it show how to use this stuff in more depth, and it's really worthy of a course of its own, but it also assumes that you don't really that you're not a machine learning expert already. It actually takes the time to very concisely and accurately convey some of these concepts for you. So if you want to learn more about MLlib, I'd recommend starting there. And hey, I might actually do a course on it myself at some point too. All right, let's make some movie recommendations. So believe it or not, this code is all you need to replicate what was done with the Netflix prize and actually create what should be really good movie recommendations. But as we'll see, your mileage may vary. Anyway, this sample boilerplate code, let's walk through it. All it's doing is opening up a text file from your hard drive, the same old u.data file you're used to all the time. It's going to map it out just like we did before. So it's going to split it out based on white space and then map that to a rating structure. Like we talked about, MLlib has some special types, and rating is one of them. And the rating is basically you rated something, some value. So we're going to pull out the user and the rating and the item. I'm sorry, the user, the movie, and the rating itself. And we're going to cache that because we're going to use that ratings RDD more than once. So remember, if you're going to use more than one action on ratings, under the hood, our ALS MLlib function is going to call that ratings RDD multiple times. So we need to make sure that we cache or persist that RDD for it to work efficiently. And from there, it's just really a one line of code thing. ALS stands for alternating least squares, and that's part of the MLlib library. We tell it to train itself based on our ratings data. And there are several magic numbers that you need to pass into it that are extremely important and affect the results greatly. And unfortunately, there's no real guidance given as to what you should set those to. So you kind of have to experiment and iterate and try different values until you get results that you like. We're going to, in our example, use a rank of 10 and a number of iterations of 20. I find that the more iterations you have, the better it does. Although the more iterations you have, the more work it needs to perform and the less likely it is to actually succeed on a single node. And finally, we just use the resulting model to actually recommend products, in this case movies, for a given user ID. And we're saying we want 10 recommendations for whatever user ID we want. And that's all there is to it. I mean, what is that? 1, 2, 3, 4, 5, 6, 7, 8-ish lines of code to make movie recommendations. Seriously? Well, let's give it a try. Let's see how well it works. So that's MLlib in a nutshell. And since we've been dealing a lot with movie recommendations here in this course, I can't resist showing you what the alternating least squares part of MLlib can actually do. So let's kick off an ALS movie similarities job using the movie lens data and see what happens. Okay, let's take a look at some code to actually run alternating least squares recommendations on the movie lens data set, and you'll see just how simple it is to do, and we'll take a look at the results. All right, let's see if making recommendations with alternating least squares with MLlib is really just that easy. So you can download the script from the resources for this lecture, look for movie recommendations ALS, and download that into your Spark course folder, and then we can play with it. Now, this is going to require me to input a user ID that I want recommendations for. So how do I know if recommendations are good? So since I don't really know personally any of the people that are in this data set from MovieLens, I'm going to create a fictitious user, kind of hack their data to stick it in there. So in the ML-100K folder, I'm going to edit the u.data file. And what I've done here is I've added 3 lines at the top for user ID 0 because I happen to know that user ID 0 does not exist in this data set. And I looked up a few movies that I'm familiar with so I can get a little bit more of a gut feel as to how good these recommendations might be. So 50 is actually Star Wars, and I've given that a 5-star rating. 172 is The Empire Strikes Back, and I've given that a 5-star rating as well. And 133 is Gone with the Wind, which I gave a 1-star rating. Actually, I didn't hate it that much. But the point here is, I'm trying to create a persona of a science fiction nerd who really likes Star Wars and really doesn't like old movies from the 1930s that are, about melodramatic people, to put it politely. So let's see what kind of recommendations we would get. I would expect to see, other similar science fiction related blockbuster action-y films and, see things that are like Gone with the Wind not appear, right? So there we have it. Let's run it and see what we get. So we've already looked at the code, but we'll open it up and take a look at it in Python just for completeness. And a lot of this code is the same. We have the same boilerplate stuff. One thing to point out is that we do need to explicitly import the ALS and ratings classes from pyspark.mllib.recommendation in order to use them. We're going to run this across our entire cores that we have. And otherwise, everything is like we had it before in the slides. We train it based on the 100,000 movie lens ratings, and then we simply ask it to use that same model to generate recommendations for a given user ID that we input as a parameter. And this will give us the top 10 recommendations for user ID 0, assuming that's what I pass in. So let's kick it off and see what happens. Spark-submit, movie recommendations, ALSPY, and with user 0, because again, that is my Star Wars fan who doesn't like Gone with the Wind. So we've kicked off our job to do alternating least squares recommendations on the movie lens dataset. Finishes pretty quickly. Let's take a look and analyze the results in our next lecture. Off it goes using all cores that I have. That was pretty quick, wasn't it? So for such a fancy algorithm, that came back creepily fast, almost suspiciously so. And let's take a look at the results. So for my fictitious user who loves Star Wars and loves Empire Strikes Back and hated Gone with the Wind, the #1 recommendation it produced was something called The Endless Summer 2. And Crooklyn? What? What is this stuff? That's crazy. Lost in Space, okay, I can go with that, but the rest of this just doesn't make sense. And what's worse is if I run it again, I'll actually get different results. Now, it could be that the algorithm is taking some shortcuts and randomly sampling things to save time, but even so, let's see what we get this time. Totally different set of stuff. Again, there's some in there that I might agree with. I mean, Army of Darkness, yeah, people who like Star Wars might be into that, but this other stuff, not so much. One more time. I mean, we got to get something good out of here at some point. Well, hey, at least The Empire Strikes Back showed up. But wait, that was actually one of the movies I started with. Why is that even in the results? I don't know. Well, let's talk about what might be going on here in our next section. All right, so those results are pretty sketchy, honestly. But let's talk about what might be going on there. So one thing, there are a couple of parameters, and there's even more optional parameters that I didn't show you to that ALS method there for alternating least squares. And the results are very sensitive to the parameters you choose there. So it actually takes a lot of work to find the optimal parameters for a given data set to get good recommendations out of it. Now, there are some techniques you can use in machine learning to try to arrive at the right parameters. So there's a technique called train test, where basically you withhold a portion of the data as sort of a training data set and another portion as a testing data set, and you evaluate your ability to predict user ratings using your algorithm going forward. And you can actually measure, there are measures of recommendation accuracy that use that technique. So what you could do is actually create a nested loop to try every possible combination you can think of those parameters and measure which one gives you the best results. But even that's kind of a dodgy thing to do because you could end up overfitting to the data set that you have. So one algorithm might work very well, one set of parameters might work very well for this particular 100,000K movie lens data set from 1998, but that doesn't mean the same parameters will work well on a data set from a different UI where different people were using it, or from a different time or a different location. And, you know, there's also this sort of bigger question of what is a good recommendation anyway? I mean, does the ability to predict movies that I already saw and rated make a good recommendation, or should I be recommending things that I haven't heard of before? I don't know, it's kind of debatable. So, I don't know, it's a little bit dodgy. And honestly, those results were so sketchy, I'm not even convinced it's working properly internally. And putting your faith into a black box like this is kind of a dodgy thing to do. I mean, we're kind of trusting that a very complicated ALS algorithm under the hood works perfectly, and that may not be the case. We'd actually get better results just using our movie similarity results from earlier and recommend similar movies to movies that you already said that you liked. So complicated isn't always better, and a black box isn't always better. Never put your blind trust into something like this when you're analyzing big data. Question things, and remember that small problems in your algorithms can explode into big ones with large data sets. And often the real issue is the quality of your input data, and that also needs to be looked at too. But that all said, MLlib's still really cool. I mean, some of its other components are very useful and much more simple. So there we have it. Our results from alternating least squares were a little bit underwhelming, yeah? So, you know, all the more reason to go and do it yourself the way that you want to. I mean, if you go back, I think the results we were getting out of our movie similarity script just using a simple cosine metric were actually better. And if you were to use that in a item-based collaborative filtering context to actually recommend new movies to people based on those similar movies, I think those results are actually preferable. But this is the algorithm that won the Netflix prize, so there's got to be something to it. Maybe we just didn't choose the right parameters. Who knows? Maybe the data isn't really amenable to it. But hey, that's what you get when you have a black box algorithm like that. You don't have a whole lot of insider control as to what's actually going on within there. But it is in there for you to use, and some of the more basic functions of MLlib are going to be a lot more straightforward and easy to understand. So definitely don't shy away from MLlib because of this. It has a lot to offer and a lot of useful functionality in there that you may find useful to have in your toolbox going forward. So let's talk about some more Spark technologies next. So back when we talked about Spark SQL, remember I said data frames are kind of the way of the future with Spark, and it's going to be tying together different components of Spark. Well, that applies to MLlib as well. So there's a new data frame based API in Spark 2.0 for MLlib, and that is the preferred API going forward. The one that we just talked about is still there if you want to keep using RDDs, but if you want to use data frames instead, you can do that too. And that opens up some interesting possibilities. It means you can import structured data from a database or JSON file or even a streaming source and actually execute machine learning algorithms on that as it comes in. So it's a way to actually do machine learning on a cluster using structured data from a database. So let's see how that works. We're going to look at an example of doing that with linear regression. And just to refresh you, if you're not familiar with linear regression, all that is fitting a line to a bunch of data. So imagine, for example, that we have a bunch of data of people's heights and weights, and we imagine there's some linear relationship between these two things. So taller people tend to weigh more, right? Makes sense. So if we have a bunch of known data points of people's heights and weights, we can actually use that to construct a linear regression model, where we actually create an equation of a line with a given slope that actually is a best fit and minimizes the error between the actual observed heights and weights and what we're predicting with our line. And once we have that line, we can use it to predict new heights for people given their weight or vice versa. So that's the idea behind linear regression. Let's see how it works with MLlib and using data frames. So first we'll import from the ML library a regression, linear regression class, and note that we're using ML instead of MLlib here. That's basically where the new data frame APIs live, and that's going to be where Spark wants you to start using these going forward. We're also going to import Spark session and vectors, which we're going to need to actually represent our feature data within our algorithm. So let's go ahead and look at the script itself. We'll start by creating a Spark session object, just like we did back in the Spark SQL lectures. And again, remember that this .config clause here should be removed if you're not on Windows. This is a Windows-specific hack to work around a bug in Spark 2.0 on Windows. Make sure you have a C temp folder if you're going to run this on Windows. All right, we'll just call this thing linear regression and get our Spark session that we can work with. Now, again, we're going to start with unstructured data. So I've provided a regression.txt file with this lecture that you should be working with. So along with the Spark linear regression.py script file, you should also have saved the regression.txt data file into your course materials as well. And this could represent anything. It's just normalized data, so we've actually mapped this to a normal distribution, the idea being that you would scale it back up when you're done to its actual value. So you can imagine it represents anything. Let's stick with heights and weights in this example. So it's basically two columns of information that are separated by columns. And in machine learning terminology, we talk about labels and features. So typically a label is the thing you're trying to predict, and a feature is a set of attributes of objects that you can use to make that prediction. So let's imagine that we're trying to predict heights based on your weight. In that case, the label would be the height, and the feature would be the weight, okay? So to express things in that terminology, that's the format that MLlib is going to expect. We're going to map that input data. We're going to split it by commas and then map it into this format here where we have our label, which is just, let's call it the height. And then we construct a dense vector of our feature data. So whatever our features are, it has to go into a dense vector. That's what MLlib expects. In this case, we only have one thing in that vector, which is the weight, right? So at this point, we can actually convert that to something MLlib can understand. Let's convert that to a data frame where we're going to say we're going to construct, we need to give these columns some names, right? So we're going to say explicitly this first column is going to be called label, the second column is called features, and at that point we have a data frame that ML can work with. All right, so now that we have our data frame of feature and label data, our heights and weights if you will, we can construct a model from that. And a little Little bonus lecture here on machine learning in general. So the way you can evaluate the effectiveness of a model in machine learning is using a technique called train test. And the idea is that you split your input data into two sets randomly. You take a set of that data and use it for actually constructing your model and training your model, and then you hold aside a set of other data that you're going to use to test that model. So the idea is that if you take a bunch of data that your model has never seen before, you can evaluate how well that model can actually predict the labels in that test data set. So what we're doing here, we're splitting up our data frame into two sets randomly, 50-50. We're going to take the first data set that comes back and call it our training data frame. And we're going to call the second one our test data frame. Okay. So next we'll create a linear regression model with some certain parameters that we've chosen. And we're going to fit that model to our training data. So that 50% of data that we held aside for training the model, we will call fit on. And since that is in exactly the right format that the linear regression model expects, a data frame of labels and dense vectors of features, it can actually use that to create a linear model that fits that data. All right, and now we can take our test data and use our model to make predictions of it. So we now have a new data frame that contains not only our labels and features, but also a new prediction column. And we can actually cache that, so we can do multiple things to it. So let's see how that works. Let's select the prediction column out of that resulting data frame and map that to just plain old values. And we'll also extract the labels. So we've basically taken what the model has predicted out of that data frame and the known labels, the known correct values out of that data frame. We'll zip them back together, and then we can just print them out side by side and compare the two. Now, there are more principled ways of doing this. You can actually compute things like r squared, but I don't want to get into too much machine learning lingo here. So let's just print out the predicted and actual values side by side here as an exercise. So let's go ahead and see if that works, okay? So open up your shell, wherever it may be, and we'll type in spark-submit spark linear regression.py and kick that off. Got to think about that a little bit, huh? There we go. All right, and there you have it. So you can see that our model's pretty good. There's a pretty good correlation between our actual observed values and the predictions. They tend to go in the right direction, so they're not too far apart. And there you have it. We've basically constructed a linear model using MLlib, using data frames. So again, the point here isn't really so much to show you how linear regression works, it's to show you how to use data frames with MLlib. So just to review quickly again, we constructed this data frame of labels and features, fed that into a linear regression model, and then we could use that model to make predictions. So that's all there is to it. It's actually a fairly simple API when you get down to it. So there you have it, an example of using data frames with MLlib. Again, that is the way of the future in Spark 2.0 and beyond. So there you have it. All right, the last two things I want to cover are Spark Streaming and GraphX, which are two technologies built on top of Spark, one which handles continually incoming real-time data, say from a series of web logs from web servers that are running all the time. And GraphX offers some tools for network analysis, so kind of like the social network analysis that we were doing back when we were looking at superheroes and their relationships to each other. Now, neither one of these really has good support for Python yet, so all I can really do is talk about them at this point, but I think you'll get the idea, so follow along and let's see what's there. So lastly, I want to talk about Spark Streaming and GraphX, and I'm going to cover these at kind of a high level and kind of hand-wavy for one very good reason, and that's that they're currently incomplete. Right now they only work in Scala, and they're in the process of being ported to Java and Python. But by the time you take this course, they might very well be available, so let's talk about it, and if you want to go learn more, you can certainly do so. Spark Streaming, it's useful for very specific tasks. If you have a continual stream of data that needs constant analysis, then Spark Streaming is for you. A common example is if you have a fleet of web servers running and you need to process log data coming into it continuously. Who knows what you want to do? Maybe you want to keep track of, the most frequent occurrences or keep an eye out for a certain kind of error or something like that. Spark Streaming can do that. And the way it works is that at some given interval that you define, it will aggregate the data that's coming in and analyze it however you say. So you can reduce things or whatever you want to do to it or map it at some given time frame after a certain batch of data has been taken in from your stream. And now you can feed data to it, just plain old text information over some port that you open up. That's the most straightforward way to use Spark Streaming, but it can also connect to things like HDFS, Amazon's Kinesis service, Kafka, Flume, and others. The list is growing all the time. And another thing that Spark Streaming offers is something called checkpointing. So for fault tolerance, it would kind of suck if your entire job that's been running forever suddenly lost everything that it was doing because one machine failed. Checkpointing will store the state of your Spark Streaming job to disk periodically. So if you do have some sort of hardware failure, it can seamlessly pick up where it left off, at least in theory. And like I mentioned, Python support for Spark Streaming is currently incomplete, although it is underway and partial. So by the time you read this, there's a good chance it will be done and available for you in Python as well. But for now, we're stuck with Scala for it. And we'll look at a little example here in Scala, knowing that Scala code in Spark looks a lot like Python code, so this shouldn't be too far-fetched from what you would see in Python. Basically, Spark Streaming sets up what we call a dstream object that breaks up your incoming stream into a bunch of distinct RDDs. So as individual time frames elapse, you will receive a new RDD to process with your stream. And here's a simple example that just sets up a streaming context based on some configuration that will actually boil things down every 1 second. And we will connect that to port 8888 on our local host. And all we have to do is say lines.filter, lines being what's coming out of our text stream every 1 second. Filter out things that contain error and put that into our errors RDD and print out the results. So this is a very simple example of Spark Streaming that just listens for lines of text that contain the word error and prints them out when they occur. Now, that's not all you need to do. You actually need in your driver to kick this off and actually call stream.start and stream.await termination to actually start your Spark Streaming job. And once you do that, it will start listening to port 8888 and print out anything it receives that contains the word error. And potentially you can do that in a distributed manner. Now, some things to remember with Spark Streaming. Remember, your RDDs only contain one little chunk of incoming data. So if you need to aggregate data over time, there's a couple of ways that it lets you do that. One is by using what's called windowed operations, and that lets you combine results over some window of time, some sliding time window. So let's say, for example, you had sales data coming in through your stream, and you wanted to print out the top sellers over the past 24 hours. You could create a sliding window of 24 hours and actually tell Spark to keep reducing by that 24-hour window. And operations like window, reduce by window, and reduce by key in window make it very easy to do something like that. And top sellers are most frequently viewed web pages on your website over some period of time. Those are some examples of applications you could very easily do using Spark Streaming. Again, an example of where I wish I could go back in time and redo some of the stuff I did at Amazon and IMDb, because that would make life so much easier. There's also update state by key. So if you need to maintain something like a running count or some sort of state that persists across the entire run of your job, you can do that by using update state by key to maintain that state across many batches as they come in as time goes on. So another tool in your toolbox for doing things over longer periods of time than your actual batch size in Spark Streaming. All right, shifting gears, let's talk about GraphX. So GraphX is another library built on top of Spark Core. It's not that kind of graph where you have like lines and pies and charts and bars and stuff like that. It's graph in the sense of graph theory. So for example, our social network of superheroes is an example of that kind of a graph. And currently it is Scala only, although Java support is almost done, and as soon as Java support is done, Python support will pretty much follow on top of that. So they're actually very close to getting that done at this time, and by the time you view this course, there's a good chance Python and Java support will exist for GraphX. However, currently it's only useful for some very specific things, and obviously it's going to evolve over time, but GraphX in its current form wouldn't have actually helped us very much with our degrees of separation example that we did. But it can do things like measure the properties of a social graph or any graph of information for that matter. So if you need to measure things like connectedness or degree distribution, average path lengths, triangle counts, these are all high-level measures of the properties of a given graph, and GraphX can help you compute those very quickly in a distributed manner. It also has tools for quickly joining graphs together and transforming graphs quickly. So if you need to do operations like that, GraphX is worth a look, and go see if you need to learn Scala or if they actually have Python or Java support at this time. Under the hood, it introduces two new types of objects, a vertex RDD and an edge RDD. So, for example, in our social network of superheroes, a superhero might be a vertex, and a connection between two superheroes would be an edge. But apart from that, GraphX code looks like any other Spark code, so it's going to look very familiar, and it's not that hard to pick up, really. But there are very specific tasks and very specific fields that will find GraphX useful. So I just want you to know that it's out there, and if you do have a problem in that realm, check it out. All right, that's Spark Streaming and GraphX, and with that, we've covered pretty much everything there is about Spark, at least as of this date. Congratulations, you are now very knowledgeable about Spark, and if you've actually followed along and gone through the examples and done the exercises, I think you can call yourself a Spark developer, so congratulations. Let's talk about where to go from here next, and kind of what the next steps might be for continued learning. So if you made it this far, congratulations, and thanks for sticking through this whole course with me. If you feel like it was a useful experience and you learned a few things, please leave a review on this course. It will help me improve the course going forward and let me know what I'm doing right and what I'm doing wrong. And it will help other prospective new students understand if they should give this course a try. So really appreciate your feedback, and I would appreciate it if you could take a minute right now and go leave a review for this course. So where do you go from here? What's next? Well, there's obviously a lot more to learn. We've really covered a lot of the basics of Spark, but there is more to the field of data science and big data as a whole, of course. If you want a sort of a desktop reference to refer to instead of videos, there are some books that I can recommend about Spark. I don't make any money from these or anything, so don't worry about it. I'm not trying to sell you anything, but just personally what I've enjoyed, the O'Reilly series I think is very useful. They have a book called Learning Spark that I found to be a useful reference while learning, and has a lot of good little snippets and code examples in there that you may find useful. And if you're going to be using Spark for some real machine learning and data mining work, I also really like Advanced Analytics with Spark, also from O'Reilly Press. And it takes more of a data mining look at things. So, it goes into things like, it goes into MLlib in a lot more depth, for example. So what I really like about this book is that it doesn't really assume that you're a machine learning or a data mining expert. It takes the time to actually review things like what is k-means clustering and, what is a Pearson correlation metric. So it doesn't really assume that you're already an expert in this stuff, and it's written in a very conversational tone, and I like it for that reason, because really data mining doesn't have to be hard, machine learning doesn't have to be hard. The concepts themselves are actually pretty straightforward once you grasp them. You just got to get through the terminology and all the fancy language. On the other hand, there's also a book called Data Algorithms by O'Reilly, a very, very thick book. And it's not really Spark specific. It's actually written for Hadoop and MapReduce and also Spark as sort of kind of a third option. So they have a bunch of recipes for different types of problems you might encounter in the machine learning world and some sample solutions to those problems using both MapReduce and Spark side by side. It does spend a lot of time on the MapReduce side, and Spark is always last. So I'm not really sure. These were always written with Spark in mind from the beginning, and the tone, as in contrast with this book, is a little bit more academic. So you might find it a little bit less accessible if you're new to the field, but there are some useful recipes in there. So my recommendation would be go check out the table of contents on your favorite bookseller website and just keep that list around. So if you do need to figure out how to perform some specific algorithm in Spark, see if it's in that book, and if so, it might be worth checking out. And beyond the world of Spark itself, there's obviously a lot more to the world of data mining and data science in general. Just knowing Spark does not make you a data scientist that will make lots and lots of money. There are other tools and techniques out there. For example, MapReduce is still the granddaddy of the tools in this area. So learning more about MapReduce is an option, and there are courses on Udemy for that. And just learning about data mining in general is a good idea too. Like I said, the Advanced Analytics with Spark book touches on that a little bit, but picking up a course like Statistics for Dummies is probably a good place to start if you're totally new to that field. And we can also look for courses on machine learning and data mining are probably the keywords you want to look for, and data science in a more general term. So there's a lot to learn there as well. All right, well, I hope that gives you a good starting point on your journey toward a career as a data scientist, or if you're already a data scientist or an engineer working at a large software company that has lots of big data to process. I hope you have a new tool under your belt, Spark. It's a very easy and very fast and efficient way to munge large amounts of data on a cluster. So, if you have access to one, even if you don't, EMR gives you a good way to get one for pretty cheap. So, hey, it's been a good ride. Thanks for coming along with me. I really appreciate it. There is one more bonus lecture at the end of this at the end of this course. So appreciate it if you could give that a watch. It's a chance for me to tell you about some other stuff that I can offer for you. And again, thank you. And if you haven't already, please leave a review on the course. Thanks a lot. Hi, welcome to my course on taming big data using Apache Spark. My name is Frank Kane, and I spent 9 years at Amazon.com and IMDb.com wrangling millions of customer ratings and customer transactions to produce things like personalized recommendations for movies and products, or people who bought this also bought. And I tell you, I wish we had Apache Spark back then. I spent years trying to solve these problems there, but by the end of this course, you're going to be running scripts yourself that can actually analyze 1 million movie ratings and produce movie recommendations for individuals in the cloud on a cluster of computers with only about 40 lines of code. How cool is that? Spark is one of the hottest technologies in big data analysis right now, and with good reason. If you work for or you hope to work for a company that has massive amounts of data to analyze, Spark offers a very fast and a very easy way to analyze that data across an entire cluster of computers and spread that processing out. And that's a very valuable skill to have right now. Now, I wrote this course for people who have at least some programming or scripting experience in their background. We're going to be using the Python programming language throughout this course, which is very easy to pick up. And I'm going to give you over 15 hands-on real examples of Spark Python scripts that you can run yourself and mess around with and play with and learn from. So by the end of this course, you should have the skills needed to actually turn business problems into Spark problems, code up that Spark code on your own, and actually run it in the cluster on your own. My approach in this course is to start with some simple examples and work our way up to more complex ones. And we'll have some fun along the way too. So in addition to using movie ratings data and playing around with similar movies and movie recommendations, I also found a social network of superheroes, if you can believe it. And we can use that data to do things like figure out who's the most popular superhero in the fictional superhero universe. And have you heard of the Kevin Bacon number, where everyone in Hollywood is supposedly connected to Kevin Bacon by some small number of degrees? We can do the same thing with our superhero data and figure out the degrees of separation between any two superheroes in their fictional universe too. So we'll have some fun along the way and use some real examples here and turn them into Spark problems. Using Apache Spark is easier than you might think. And with all the exercises and activities in this course, you'll get plenty of practice as we go along. And I'll guide you through every line of code and every concept you need along the way. So let's get started and learn Apache Spark. So some really quick housekeeping here, just so you know where to put all the stuff for this course. I want you to go to your hard drive here and create a new folder called Spark Course, someplace where you're going to remember where it is. So for me, I've put that in my C drive under a folder called Spark Course. And this is where you're going to put everything for this course. So as you come through individual lectures, you'll see that there are resources attached to those lectures. And if you click on the resources button, you should find a way to download them. And there can be different kinds of resources. There can be files, there can be downloads. Just make sure you look at them all. But when you download them, make sure you put them in this folder that you created. So this is the ultimate destination of everything you're going to download for the course, and you'll just accumulate all this stuff over time as you work your way through it. So just remember where you put it. You might need to refer to these files by their path. So you'll have to remember that it's, in this case, C:\\Spark course is where all these files were put. Just make sure you download them to a consistent place, and you should be good to go. Now, if you're on Mac or Linux, of course, you're not going to have a C drive. Put it wherever it makes sense. Just be cognizant of differences in file paths between operating systems. So instead of using a C drive, you'll just have a slash in the full path name. Capitalization might be important where it's not in Windows, and things like that. So, and also forward slashes instead of backslashes in paths is another difference between Windows and other operating systems. So if you are using something other than Windows, just keep those differences in the back of your mind. Don't let them trip you up. If you see a path to a file in a script, make sure you adjust it accordingly to make sense on where you put these files and what your operating system is. Okay, so with that out of the way, let's move on. So let's dive in and get what you need installed to actually develop real Spark code on your desktop using Python. There's a lot of steps involved, so please be careful and follow along carefully. Hit the pause button on the video as you need to keep up with me, okay? It's important that you get every step right. We need to install Enthought Canopy, which is going to be our development environment in our Python environment. We need to install Spark itself, which itself is a pretty big process. And we need to install a JDK as well before we do any of that. So let's do this. And when we're done, we'll actually run a real Spark script and get a little payoff for all that work. Let's get started. All right, let's get you set up with everything you need to get started as quickly as possible. First thing you're going to need is some sort of development environment, an IDE for Python code. And what I'm going to use in this course is Enthought Canopy. It's a scientific computing environment, and it's going to work well with this course. Now, you might already have an existing Python environment, and if you want to stick with it, and you're comfortable with it, that's okay. Just make sure you know how to install packages into it. The other thing you need to be aware of, though, is that Canopy installs a Python 2.7 environment, whereas the environment you're using might have a Python 3 environment. And there are differences between Python 2.7 and Python 3 code that you need to be aware of. So, for example, if you want to use Anaconda, you're going to have a much easier time if you put Anaconda into Python 2.7 mode while you're using this course, okay? If you really want to use the Python 3 environment, you're going to run into some little glitches with my scripts in this course here and there. It's mostly little things like, print statements need to have parentheses around them in Python 3. Nothing major, so if you are comfortable with Python and Python 3, you can stick with it, but you will have a much easier time if you follow the steps here and actually use Nthought Canopy or a Python 2.7 environment. So to get Canopy installed, just go to nthought.com here, www.nthought.com. There'll be a link for this in the resources for this lecture, and say download Canopy. It is free. And we're going to select your operating system and architecture. For me, that's Windows 64-bit, and download. We don't have to give them any personal information, so I'm not going to, and down it will come. So there's a pretty standard Windows installer here. I'm not going to bore you with the details, so we'll just let that download kick it off, and then through the magic of video editing, we'll come back when that's done. Okay, so we finished the installer and we let it run for the first time, after which it did a big Canopy setup operation, and after you run it, you should see something like this. It's going to ask if you want to make Canopy your default Python environment, and normally you'll say yes. If you do have another environment you want to use as well, you can say no and switch it back and forth in Canopy's preferences like it says. But let's go ahead and start Canopy. And if things install successfully, you should see something like this. All right, we're good. All right, let's go on to the next step. All right, let's get Spark set up on your desktop. There's a lot of steps involved, so follow along carefully. Okay, hit pause when you need to keep up. First thing we need to do is install a JDK. So if I just go to Google and search for a JDK, that's the Java Development Kit, it should take us to the right place. Go ahead and click on that. The reason we need a JDK is even though we're developing in Python, Spark ultimately compiles down to Java bytecode. So we need a Java development environment and a Java runtime environment for that to work. Go ahead and click on the latest JDK download here. And we'll accept the license agreement, select the development kit appropriate for your operating system. For me, that's Windows 64-bit. Download it and install it. All right, I've launched the installer for the JDK. We'll just walk through it here. Now, I am going to change the install path to be, in this case, CJDK. How about that? Just because I need to remember it, and it needs to be something that's relatively short. Everything else I'll keep as default. And it's actually going to prompt me again for a path. So I'm going to have to change that path a second time once it gets to that point. So let's wait for this to finish, and then we'll do that. All right, here we are at the second step of the JDK installation. Again, I need to change the path, and I want it to be CJDK. And off it goes. And we'll come back when that's done. All right. So our JDK is installed. Hooray! We can move on to installing Spark itself. So now let's get Spark itself set up. Head on over to spark.apache.org, and you should see a website like this. And go ahead and click on the Download tab here. And we want to select the latest Apache Spark release. We want a pre-built for Hadoop 2.6 version, okay? This is very important, otherwise it's not gonna work, okay? Make sure you get a pre-built version. And we can just hit the download link now to go grab that. Now you'll notice that this is actually a TGZ file that's coming down. We'll use whatever mirror site they recommend. Now Windows does not have support for TGZ files built in. It's basically a compression format like a zip file. So if you don't already have something installed that can handle TGZ files, what I use is a program called WinRAR. And you can just head over to WinRAR. Search for WinRAR or WinRAR. It's hard to say, isn't it? WinRAR downloads. And you can find it here for whatever operating system you're using. So if you install this on Windows, it will let you right-click on these TGZ files and extract them like we're about to do right now. So that's still coming down. Let's, through the magic of video editing, come back when that Spark package is fully downloaded. Okay, so Spark is downloaded. Again, this is a pre-built for Hadoop version. And I'm just going to open that up wherever it downloaded to. And since I have WinRAR installed, I can just right-click on that puppy and extract it. And there are a lot of files in there, so that'll take a little bit of time. So let's open up the folder it decompressed into here. And you should ultimately see something like this. So within this Spark, whatever version you downloaded folder, is the contents of the Spark distribution itself. Okay, so let's keep this window over here and open up a new File Explorer window. And I'm going to create a directory where Spark is going to live. And for me, I'm going to put that on my C drive, and I'm going to create a new folder called Spark. So Spark for me is going to live under C Spark. So let's open up that C Spark folder. And then I'm going to copy all these contents of the Spark distribution into that C Spark folder, okay? So very important, I'm pasting in the contents of Spark, not the Spark folder itself. All right, so what I should have now is my C drive with a Spark folder in it that contains all this stuff, all right? All right, well, we're not done yet, unfortunately. There's a few things we need to configure, so while we're in here, let's open up the conf folder. And in order to make sure that we don't get spammed to death by log messages, we're going to change the logging level setting here. So to do that, we're going to click on this log4j.properties.template file and take off the .template part and make it an actual log4j.properties. And Spark will use this to configure its logging. And now we can open that up in a text editor of some sort. And you see here where it says log4j.root category equals info. Let's change that to warn. In fact, you might even want to set it to error, but warn will be enough to get rid of most of the annoying messages. So save that. And that step is finished. All right, a few more things we need to set up. There are some quirks about Windows, so this next step is for Windows only. What we're going to do is download a utility called winutils.exe. And there'll be a link to this in the resources, but if you need to copy it, here is the path where you can download that from that I'm hosting myself. And what this is a little hacky thing that kind of tricks Spark out into thinking that it's actually on a Hadoop cluster, even though it's really just running on your Windows desktop. So once you've downloaded that file, and yes, it's an executable, trust me, it's not a virus. If you're paranoid, you can download it from somewhere else. But anyway, go to where you downloaded that and copy that. And what I want you to do is go back to your C drive and create a new folder. And this one's going to be called winutils. Okay, now open up that winutils folder, and inside of that, I want you to create a bin folder. All right, and now inside of that bin folder, I want you to paste in that winutils.exe file that we downloaded. Okay, so you should have C winutils bin and then winutils.exe. Okay, make sure you get all this right. I mean, everything needs to be spelled properly in exactly the right place, or else you're going to run into trouble. So be careful. Double check everything you're doing. Hit pause to keep up with me. Take your time, okay? All right, now we need to set some environment variables in order for things to work. So to do that, I'll show you how to do it on Windows. Basically, you can just right-click on the Start menu here and go to Control Panel under Windows 10 and hit System and Security. And then hit System. And from there, Advanced System Settings. And from here, hit Environment Variables. Now, this is a very Windows-specific way of setting environment variables. On other operating systems, you'll use different processes. So remember, this is Windows-specific, and if you're on a different OS, you'll want to look up how to install Spark on it. All right, so we're going to set up some new user variables here. The first one is going to be called, I hit New here for a new user variable, and we're going to call it Spark_home, just like that, okay, all uppercase. And this is going to point to where we installed Spark, which is going to be for us C:\\Spark, just like that. All right. Now we also need to set up a Java home, Java_home, to where we installed Java, which for us, recall, was C:\JDK. Okay. And we also need to set up Hadoop home, just like that. And that's going to be where we installed the winutils package. So that's going to be C:\winutils. So far, so good. All right, last thing we need to do is modify our path. So you should have a path environment variable here. If you don't, it's a little bit fishy. You might be on a managed system where they don't actually let you change these things. So you might want to see if you can run it under an administrator account or something like that. But if you do have a path, click on it, edit it. If you don't make one, if you don't have one, you can create a new one. And what you want to do is add in a couple of things here. So first of all, make sure you have Java home enclosed in parentheses \bin in there already. If you don't, add that in. Should have been added by the JDK installer automatically, but sometimes things go wonky. Now I want you to hit new, and what we're going to type in here is %, make sure you get this exactly right, spark_home %bin, okay? So basically this makes all the binary executables of Spark available to Windows wherever you're running it from. Hit OK, hit OK again, hit OK again, and we have finally everything set up. So let's go ahead and try it out in our next step. All right, let's get a payoff for all the setup work that we've done. Let's actually run some actual Spark code using Python for real. All right, let's open up a command prompt in Windows, preferably as an administrator. And if you don't have a handy-dandy shortcut like I do, you'll find it under the Start menu. Go to All Apps and go to Windows System, and there's a command prompt there. Okay, but you'll probably want to keep a shortcut in your taskbar like I do. All right, so I want you to cd to c:\spark, which is where we installed Spark in our previous steps. Make sure that we have Spark in there, so there's all the contents of the Spark distribution pre-built. And let's look at what's in here. So there's this big changes.txt file that's a change log. That's an interesting file. So let's write a really simple Spark program that counts how many lines of text are in that file. All right, so all we're going to do is type in PySpark, just like that. And when I hit that, it should launch my Python environment through Canopy, and then launch Spark itself, just like that. Woo! Check it out, we're running Spark interactively. Now, if you're not seeing this and you're seeing some weird Windows error about not being able to find PySpark, go back and double check all those environment variables. Odds are there's something a little bit wrong with your path or with your Spark home environment variables. And sometimes you need to log out of Windows and log back in order to get environment variable changes to get picked up by the system. So if all else fails, try that. Also, if you got cute and installed things to a different path than I recommended in the setup videos, make sure that your environment variables reflect those changes. Some other common problems, if you chose to put it in a folder that has spaces in the name, that can cause problems as well. And if your path is too long, if you have too much stuff in your path, that can also cause problems. So some things to look at if you're running into trouble there. One other possibility is that you're running on a managed PC that doesn't actually allow you to change environment variables. So you might have thought you did it, but there might be some administrative policy preventing you from doing so. If so, try running the setup steps again under a new account that's an administrator if possible. But assuming you've gotten this far, let's have some fun. So let's write some code, shall we? Let's type this in, rdd space equals space sc.txt file with a capital F, open parenthesis, quote, changes.txt, just like that. So make sure you get that exactly right. Remember, those are parentheses, not brackets, and case can matter on some operating systems, so that all matters. What this is doing is creating something called a resilient distributed data store, and we're going to talk about this a lot more shortly. That is constructed of each line of input text in that changes.txt file. And Spark can actually distribute the processing of this object through an entire cluster. Now let's just find out how many lines are in it. How many lines did we import into that RDD? RDD.count, open close parenthesis, and we'll get our answer. It actually ran a full-blown Spark job just for that. And the answer is 34,960 lines in that file. Now, your answer might be different depending on what version of Spark you installed, but the important thing is that you got a number there. And you actually ran a Spark program that could do that in a distributed manner if it was running on a real cluster. So congratulations. Everything's set up properly. You have run your first Spark program already on Windows, and now we can get into how it's all working and doing some more interesting stuff with Spark. So to get out of this, just type in quit, open close parenthesis, and once that's done, you can close this window and move on. Okay, last thing we have to do before we start actually writing some code is to get some data to mess around with. And there's some really cool movie ratings data out there from a site called movielens.org. And they actually make their data publicly available for researchers like us. So let's go grab some. I can't actually redistribute that myself because of the licensing agreements around it. So I'm going to have to walk you through actually going to the MovieLens website and downloading it onto your own computer. So let's go get that out of the way right now. Okay, one last piece of housekeeping. So before we actually start analyzing data using Spark, we first need to get some data to analyze. So what we're going to do is get some movie ratings data that is freely available for researchers from a site called GroupLens. And if you just go to grouplens.org, you should come to this webpage here. And what this is a collection of movie ratings data. They have over 40 million movie ratings available in their complete data set. So That qualifies as big data. The way it works is people go to movielens.org, and if you want, you can go create an account there and play with it yourself. It's actually pretty good. And the way it works is you just rate a bunch of movies that you've seen before. For example, Godfather, not really my cup of tea. Casablanca, of course, great movie, 4.5 stars for him. Spirited Away, love that stuff. And the more you rate, the better your recommendations become. And it's a good way to actually get some ideas for some new movies to watch, so go ahead and play with it. And enough people have done this that they've actually amassed, like I said, over 40 million ratings. And we can actually use that data for this course. So now we're going to be running at first just on your desktop. So we're not going to be running Spark on a cluster until later on. So for now, we're going to use a smaller data set. So click on the Datasets tab here of grouplens.org. You'll see there are many different data sets you can get. Their smallest one is 100,000 ratings. And one thing you have to keep in mind is that this data set was released in 1998, so you're not going to see a whole lot of new movies in there. Well, you won't see any new movies in there. But things like Star Wars, some of the Star Trek movies, some of the more popular classics, they'll all be in there, so you still recognize some of the movies that are in there. Go ahead and click on the ml-100k.zip file to download that data. And once you have that, go to your Downloads folder and right-click on the folder that came down, extract it, and you should end up with a ml-100k folder here. Now, remember back in the first lecture, we set up a home for all of your stuff for this course, and we set it up in the C folder under Spark course. So navigate to your C Spark course directory right now, please, and I want you to copy the ml-100k folder into your C Spark course folder. So go ahead and hit pause if you need to go do that right now. And that gives you everything you need. Now inside that ml-100k folder, you should see something like this. There's a u.data folder file, which contains all the actual movie ratings, and a u.item file that contains the lookup table for all the movie IDs to movie names. And we're going to be using both of those files extensively in the lectures coming up. So at this point, you should have a ml-100k folder inside your Spark course folder, and we now have the data we need to start playing with and actually run some interesting Spark scripts. All right, all the housekeeping's out of the way now. You've got Spark set up in your computer running on top of a JDK and a Python development environment, and we have some data to play with from MovieLens. So let's actually write some Spark code. All right, we just installed 100,000 movie ratings, and we now have everything we need to actually run some Spark code and get some results out of all this work that we've done so far. So let's go ahead and do that. So let's construct a histogram of that ratings data. Out of those 100,000 movie ratings that we just installed, let's figure out how many 5-star ratings there are in that data set, how many 4 stars, 3 stars, 2 stars, and 1 stars, for example. And it's real easy to do. First thing you need to do, though, is download the ratings-counter.py script from the resources for this lecture. So if you haven't done that already, please hit pause and go take care of that right now. I'll sit here and wait for you. And when we're ready to move on, let's walk through what to do with that script, and we'll actually get a payoff out of all this work and run some Spark code and see what it does. Okay, after all that work we've done to install a development environment and some sample data, let's get a little bit of payoff for that and actually run a Spark program on some real ratings data. So from the resources for this lecture, you should be able to get the ratings-counter.py file from the resources. Remember that big friendly blue button in the upper right-hand corner of the lecture? Go click on that and download the ratings counter script to your computer and copy it into your Spark course directory. So if you need to hit pause while you go take care of that, please do so. Again, ratings counter needs to be downloaded into your Spark course directory. Once you have it there, if you've installed Nthought Canopy or whatever Python development environment you like, you should be able to just double click on that file. And up comes Canopy. Now, I don't want to get into too much detail as to what's actually going on in this script yet. I just want you to get a little bit of a payoff for all the work you've done so far. But if you look at it, it's actually not that hard to figure out. We're just importing the Spark stuff that we need for Python. We're doing some configuration, some setup of Spark up here. We're going to load the u.data file from the MovieLens data set that we just installed. So that is the file that contains all the actual movie ratings for 100,000 ratings. We then parse that data into different fields, and then we call a little function in Spark called countByValue that will actually split up that data for us. what we're trying to do is create a histogram of our ratings data. So we want to find out of all of those 100,000 ratings, how many 5-star ratings are there, how many 4 stars, how many 3 stars, how many 2 stars, and how many 1 stars exist. And back at the time that they made this data set, they didn't have half-star ratings. There's only 1, 2, 3, 4, and 5. So those are the choices. And what we're going to do is count up how many of each ratings type exist in that data set. When we're done, we're just going to sort the results and print them out. So that's all that's going on here. So let's go ahead and run that and see if it works. If you go to the Tools menu in Canopy, you have sort of a shortcut here for a command prompt that you can use, or you can open up a command prompt anywhere. Just make sure that you get into your Spark course directory where you actually downloaded the script that we're going to be using. There it is, ratings.count. Ratingscounter.py and the ML100K folder should be both in here. And all I need to do to run it is type in spark-submit ratings-counter.py. So please follow along with me here. If you need to catch up, hit pause and do so. And I'm going to hit enter, and that will let me run this saved script that I wrote for Spark. Off it goes. And there's our results. So it made short work of those 100,000 ratings. 100,000 ratings, not really big data, but we're just playing around on our desktop for now. And the results are kind of interesting. It turns out that the most common rating is 4-star. So people are most generous with 4-star ratings, with 34,000 of them in the data set. And people seem to reserve 1 stars for the worst of the worst. Only about 6,000 1-star ratings out of our 100,000 ratings. So it might be fun and go to see what actually got rated 1 star. If you want to find some really bad movies to watch. And there you have it. That's an actual running Spark script on your desktop doing some real data analysis of real movie ratings data from real people. How cool is that? Let's move on and actually start to understand what's actually happening under the hood with Spark here and how it all works and how it fits together. And then we'll go back and study this example in a little bit more depth. All right, we actually ran some Spark code of our very own. It actually worked. We just analyzed 100,000 movie ratings data in just a couple of seconds, really. So pretty nifty results. It wasn't that hard. So later on, like I said, we'll go into more detail about what that code actually does that we looked at. But for now, let's review some of the basics of Spark and how it works and what it's used for, and kind of give you some of that fundamental knowledge that you need to understand how this script actually works. So let's do that next. So before we start diving into some code, let's do a brief overview of what's Spark all about. What's it for? Who uses it? Why is it so popular? Why is it so hot? Let's explore. All right, so let's do a little introduction to Spark. What's it all about? What's the big deal? Well, according to Apache on their website, they say Spark is a fast and general engine for large-scale data processing, and that's actually a really good summary of what it's all about. If you have a really massive data set that can represent anything, weblogs, genomics data, you name it, Spark can slice and dice that data up. It can distribute the processing amongst a huge cluster of computers and take a data analysis problem that's just too big to run on one machine and divide it and conquer it by splitting it up amongst multiple machines. And the way that it scales it is it can run on top of a cluster manager. So your actual Spark scripts are just everyday scripts written in Python or Java or Scala, and they behave just like any other script. Your driver program is what we call it, and it will run on your desktop or on one master node of your cluster, and it behaves just like any other script. But under the hood, when you run it, Spark knows how to take the work and actually farm it out to different computers on your cluster or different CPUs on your same machine even. So Spark can actually run on top of different cluster managers. It has its own built-in cluster manager that you can use by default. But if you have access to a Hadoop cluster, there's a component of Hadoop called Yarn that Spark can also run on top of to distribute work amongst a huge Hadoop cluster if you have one available. For example, you can use Amazon's Elastic MapReduce service to get cheap and easy access to a Hadoop cluster, and we'll do that later on in this course. And that cluster manager will split up the work and coordinate it among various executors. So Spark will split up and create multiple executors per machine. Ideally you want one per CPU core. And it can do all the coordination using the cluster manager and also your driver program itself to farm out work and distribute it to different nodes, and also give you fault tolerance. So if one of your executors goes down, it can recover without actually stopping your entire job and making you start it all over. So the beauty of it is that it scales out to an entire cluster of computers. It gives you horizontal partitioning, horizontal scalability, which basically the sky's the limit. But from a user standpoint, from a developer standpoint, it's all just one simple little program running on one computer that feels a lot like writing any other script. So that's kind of a nice aspect of Spark. Why do people use Spark? Well, it has a lot in common with MapReduce, really. It solves the same sorts of problems. So why are people using Spark instead of MapReduce? MapReduce has been around a lot longer, and the ecosystem surrounding it and the tools surrounding it are more mature at this point. Well, one of the main reasons is that Spark is really fast. And on the Apache website, they claim that Hadoop MapReduce is 100 times slower than Spark in some cases, and 10 times faster on disk. Now, that's a little bit of hyperbole, to be honest. I mean, that's in a very contrived example. In my own experiments, if you compare some of the same tasks that we run on Spark to the same tasks that we run using MapReduce, it's not 100 times faster, maybe 2 to 3 times faster, but it's definitely faster. So it definitely has that going for it. And the way that it achieves that performance is by using what it calls a directed acyclic graph engine. The fancy thing about Spark is that it doesn't actually do anything until you actually ask it to deliver results. And at that point, it creates this graph of all the different steps that it needs to put together to actually achieve the results you want. And it does that in an optimal manner. So it can actually wait until it knows what you're asking for and then figure out the optimal path to answering the question that you want. It's also very hot. If you go to this web page here, it will give you a list of some known people that are using Spark. A lot of big companies are kind of secretive about what they're doing inside, so I'm sure there's even more people using it than what are listed here. But a lot of the big players are already using Spark: Amazon, eBay, NASA's Jet Propulsion Laboratory, Yahoo, and many others. The list isn't as long as MapReduce because Spark hasn't been around as long as MapReduce, but it's definitely gaining some big adoption quickly. And the beautiful thing about Spark is it's not that hard. It allows you to code in Python, Java, or Scala. So if you're already familiar in Python, you don't have to learn a new language. And from a developer standpoint, it's built around one main concept: the resilient distributed data set. There is one main kind of object that you will encounter in Spark over and over and over again, the RDD. And various operations on that resilient distributed data set will let you slice and dice and carve up that data and do what you want with it. So what would take many lines of code and different functions in a MapReduce job can often be done in just one line and much more quickly and efficiently using Spark. So if you actually took my MapReduce course, we're going to be doing a lot of the exact same problems in this Spark course, and you might find it interesting how much simpler and how much easier those same problems are to solve in Spark compared to MapReduce in many cases. Spark is made up of many components. We're going to be focusing a lot on Spark Core, so just what can you do with these resilient distributed data set objects, and how can you use that to distribute the processing of data and the mapping and reducing of large data sets. But on top of Spark Core, Spark also includes several libraries that run on top of it. So we have Spark Streaming, which actually gives you the ability to analyze real-time data streams, for example, from a set of web logs coming in from a fleet of web servers that need to be continually updated. And we'll talk about that later in the course. We have Spark SQL, which lets you run Spark on top of a Hive context and actually deal with structured data within Spark and actually run SQL queries on top of it. So if you're already familiar with SQL and you want to treat Spark as sort of a data warehouse, you can do that too. It also includes something called MLlib, which is a series of machine learning algorithms. And if you're going to be doing any sort of machine learning or data mining with Spark, it contains a lot of useful tools you can use to simplify a lot of common operations. For example, if you need to do Pearson correlation or get statistical properties of your data set, MLlib makes that very, very easy to do. And finally, we have GraphX. That's not, the kind of graphs where you're drawing on graph paper. It's actually managing graphs of information, network theory sort of stuff. So if you have a graph like, for example, a social graph of people that are friends with each other, things of that nature, or citations between documents and scholarly articles, things of that nature, GraphX can help you make sense of those sorts of networks and give you high-level information about the properties of those graphs. And that all runs on top of Spark Core. So Spark has a lot to offer, and it's expanding all the time. Now, people who are already familiar with Spark might say, why the heck are you using Python in this course? Well, yeah, I'm using Python as the scripting language that I'm going to be working with, and there's some pretty good reasons, so I want to kind of defend my choice here a little bit. Now, for one thing, it's a lot easier to get up and running with Python under Spark. You don't have to deal with dependencies and running Maven and figuring out how to get, jar files where they need to be and whatnot. Python, you just type your code. You don't have to compile it. It just runs, and that makes life a lot simpler. Really, I want to focus in this course on the concepts behind Spark and, how to deal with RDDs and what you can do with them and how you can put these different things together. And I don't really want to be focusing on things like, the mechanics of compiling and distributing jar files and dealing with Java and Scala stuff. It's just a lot quicker to get up and running. Also, there's probably a better chance that you're already familiar with Python as opposed to Scala, which is a newer language. And Java is just a little bit more complicated, like I said. However, I will say that Scala is the more popular choice with Spark, and that's because Spark is written in Scala. So if you write Scala code, it's native to Spark. It doesn't have to go through any sort of interpreter to sort of convert your Python code and get it running in a Scala environment. Now, I've never really run into problems with Python running on Spark, but in theory, Scala should be a little bit faster and a little bit more reliable. The other thing to consider is that new features and libraries tend to come out in Scala before they come out in other languages in Spark. A good case in point is the GraphX library that we just talked about today that only is available in Scala, but they're pretty far along in introducing support in Python and Java for GraphX right now, and by the time you are taking this course, there's a good chance it'll be available already. Similarly, with Spark Streaming, as of right now, that's only partially implemented in Python, but again, it's moving forward quickly, and I do believe that they will have feature parity among the three languages pretty quickly, so that shouldn't be too much of a concern going forward. Another reason that choosing Python isn't that bad of a choice for this course is that Python code in Spark looks a lot like Scala code in Spark, even though they're very different languages from each other. Within Spark, they look very much the same. They're both, use a lot of functional programming paradigms. We're using Lambda functions in Python as opposed to, the syntax in Scala for doing the same thing. But besides having to qualify some of our variables as being vals in Scala, where they're just untyped in Python, the code looks very, very similar in most cases. In fact, these two bits of code do exactly the same thing, and you can see the code actually looks extremely similar to each other. So even if you learn Spark using Python, it's not going to be hard to transfer that knowledge to Scala if you need to later. So that's Spark at a very high level. What's the big deal about it? Why is it so fast? Why are people using it? It's pretty cool stuff, and it's very easy to use, it turns out. So let's, come down from the high level and get a little bit more technical. We're going to take a closer look at how Spark works under the hood and what the resilient distributed data set object is. So let's do that next. So let's go in a little bit more depth about how Spark works. Under the hood, there's something called the resilient distributed data set object, and it's kind of the core of everything Spark does. So let's dive in and figure out how that works and some of the things you can do with RDDs. All right, so let's stop being all high level and hand wavy and talk about how Spark really works from a technical standpoint. So we're going to talk about RDDs, the resilient distributed data set object in Spark, and that's sort of the core object that everything in Spark revolves around. Even for the libraries built on top of Spark, like Spark SQL or MLlib, they're also using RDDs under the hood or extensions to the RDD objects to sort of make them look like something a little bit more structured. But if you understand what an RDD is in Spark, you're like 90% of the way there in understanding Spark. So let's talk about RDD in sort of reverse order, because I'm weird like that. So fundamentally, it's a data set. It is an abstraction for a giant set of data, and that's the main thing you need to know as a developer. What you're going to do is setting up RDD objects and is loading them up with big data sets, and then calling various methods on the RDD object to distribute the processing of that data. Now, the beauty is that although RDDs are both distributed and resilient, they can be spread out across an entire cluster of computers that may or may not be running locally, and they can also handle the failure of specific executor nodes in your cluster automatically and keep on going even if one node shuts down and redistribute the work as needed when that occurs. But you don't have to think about those things. That's what Spark does for you, and that's what your cluster manager does for you. So even though an RDD is distributed and resilient, which is a very powerful thing, you don't have to worry about the specifics about how that works because it's kind of magic. All you need to really know as a developer is that it represents a really big data set, and you can use the RDD object to transform that data set from one set of data to another, or to perform actions on that data set to actually get the results you want from it. Now, from a programming standpoint, you're going to be given a Spark context object. Now, remember when we first tested out Spark just to see if it was running, we ran something called PySpark, which gave us an interactive shell for Spark. And that gave us an SC object automatically that we could use to run operations on. Once you have that Spark context, you can use that for creating RDDs. And it's a little bit more useful, obviously, to have a script that you can actually run over and over again. So in the case where you're actually running a standalone script, you will create that SC object by hand and initialize that the way you want to. But either way, the SC object stands for Spark context, and it is sort of the starting point that you have from a programming standpoint. And that SC object gives you methods you need to actually create an RDD. Now, one simple example is that you can use the sc.parallelize function to take a hard-coded set of data and make an RDD out of it, but that's not very interesting. That's not really going to be useful in a real production setting, because if you could hard-code the data, then it's not really a big data set to begin with now, is it? More often, we're going to be using something like sc.text file to create an RDD object. So, for example, if I have a giant text file full of, movie ratings data, for example, on my hard drive, we can use sc.text file to create an RDD object from the Spark context, and then we can just use that RDD object going forward and process it. Now, again, if I have a set of information that fits on my computer, that's not really big data either, but you can also create a text file from an S3 location or from an HDFS URL. So these are both examples of distributed file systems that can handle much larger data sets than what you might be able to fit on one machine. And you can just as easily use an S3N or an HDFS URI as well as a file URI to load up data from a cluster or from a distributed file system, as well as from a simple file that might be running on the same machine as your driver script. You can also create RDDs from Hive. If you have a Hive context object that's already been connected to an existing Hive repository, you can create an RDD from that. If you don't know what Hive is, then don't worry about it, but Hive is basically another thing that runs on top of Hadoop that is for basically data warehousing. And you can also create RDDs from things like JDBC. You can tie it directly to any SQL database that has a JDBC or ODBC interface. You can also use popular NoSQL databases like Cassandra. And it has interfaces for things like HBase and Elasticsearch and a lot of other things that are always growing all the time. Basically, any data format that you can access from Python or from Java, depending on what language you're using, you can access through Spark as well. So you can load up JSON information, comma-separated value lists, and you can also talk to things like sequence files and object files, and also load compressed formats directly. So there's a lot of ways to create an RDD. So pretty much whatever format your source data might be in, odds are you can create an RDD from it in Spark pretty easily. So one common thing you're going to do once you have an RDD is transform it in some way, shape, or form. And these are some of the basic operations you can do on RDDs. It's not a complete list, but these are all of the most common operations that you can do on an RDD. And it's not that long of a list, is it? So there's not a whole lot to wrap your head around here. The thing is, although there's not a lot of different operations that you can do to transform an RDD, they're all very powerful. So let's start with the map function on an RDD. That allows you to take a set of data and transform it into some other set of data given a function that operates on the RDD. So for example, if I wanted to square all the numbers in an RDD, I might have a map that points to a function that just multiplies everything in that RDD by itself. And what the map function does is it has a one-to-one relationship so that every entry in your original RDD gets mapped to a new value in your new RDD. So your new RDD will have just as many entries as your original RDD. Now, FlatMap is very similar, except it has the capability to produce multiple values for every input value that you have from the original RDD. So the RDD that you transform using FlatMap may be larger or even smaller than the RDD you started with. But still, fundamentally, it transforms one RDD into another using some function. It just has the ability to blow that out into multiple results or even no results per original entry. Also, the filter operation can be used to trim out information you don't need. So let's say, for example, you have an RDD filled with weblog data, and you want to filter out everything but error lines in that weblog. You could have a filter function that just looks for the word error in a line of text, and if it doesn't have error in it, it throws it away, and that's what a filter would do on an RDD. And then there are some less common operations here, like distinct, if you just want to get the distinct values, the unique values that are in an RDD and throw out all the duplicates. You can call sample on it if you just want to take a random sample from the RDD and get a smaller data set to work with and experiment with. That can be very useful while you're testing a script on a large data set and you just want to run it locally to work out the bugs. And finally, you can actually do intersections of various types between two RDDs. So there are methods that can take two different RDDs as input and output a single RDD that is the union of the two, or the intersection, or subtracting one's values from another, or even the Cartesian product where you get every possible combination between every element in the RDD. And obviously that blows up really quickly. So again, not a lot of different operations, but they're all very powerful, and they allow you to input your own functions for transforming one data set into another using RDDs. Here's an example just to make it a little bit more real. So let's say we have an RDD that's just hard-coded to contain the values 1, 2, 3, and 4. In Python, I could just say rdd.map and pass this lambda function of x points to x times x. And that one line will go ahead and square every value of that original RDD, and it will return a new RDD that contains the values 1, 4, 9, 16, which are the squares of 1, 2, 3, and 4. What was that lambda thing? Well, if you're kind of new to Python, that might be a new concept for you. Basically, a lot of Spark is kind of centered around this concept called functional programming. It sounds fancy, but it's really not that complicated. The only thing is, many of the methods on RDDs actually accept a function as a parameter, as opposed to a more typical parameter like a float or a string or something like that. Instead, you're passing in some function, some operation that you want to perform on every value of the RDD. And lambda is just shorthand, really. So it's exactly the same thing as passing in a function directly. So just like I could say rdd.map lambda x gets transformed into x times x, I could just define a function called square it, or whatever I want to call it, that takes x as a parameter and returns the square of that argument. And then I could say rdd.map and then the name of that function. Does exactly the same thing as this line. This is just a little bit more compact. And for simple functions that you want to use for your transformations on RDDs, that can save you a little bit of typing and a little bit more clarity. If you do want to do something more complicated while you're mapping one RDD into another, you probably do want to write a separate function for it, and that's an option too. But yeah, the basic concept is that you're passing in functions to your RDD methods instead of more traditional parameters, and that's all there is to that. I mean, that's all there is to functional programming, really. It wasn't that complicated, right? It'll make more sense the more examples we look at. In addition to transforming one RDD into another, you can also perform actions onto an RDD. So once you have the data that you want into an RDD data set, you can then perform an action on it to actually get a result out of it. So you can call collect to just dump out all of the values that are in there right now and just print them all out, or whatever you want to do with them. You can get a count of all the values that are in it. You can call count by value, which will actually give you a breakdown by unique value of how many times each value occurs in your RDD. There are things like take and top that let you sort of sample a few values from the RDD final results. And more powerful is the reduce function, which actually lets you, again, write a function that lets you combine all the different values for a given key value and boil things down into a sort of a summation or some sort of aggregation of your RDD, and that'll make more sense as we look at more examples. There are more examples of actions you can do as well, but these are the more common ones. And another thing to understand with RDDs is nothing actually happens until you call an action. And we talked earlier about how Spark is so fast because it constructs this directed acyclic graph as soon as you ask for an action to happen, because at that point it knows what actually needs to be done to get the results that you want, and it can compute the most optimal path to make that happen. So it's important when you're writing your Spark driver scripts that your script isn't actually going to do anything until you call one of these action methods. And at that point, it will actually start farming things out to your cluster or run it on your own computer, whatever you've told it to do, and actually start executing that program. So you won't actually have any results or any processing whatsoever until one of these action methods are actually called within your script. So important to keep that in mind. So that's what an RDD is. It's sort of the foundation of Spark. So now that we understand how to use RDDs and what they're for, let's go back to that ratings histogram example and figure out what it's actually doing under the hood there. Remember that ratings histogram code that we ran for your first Spark program? Well, let's take a closer look at that and figure out what's actually going on under the hood with it. All right, so understanding concepts from PowerPoint slides is all well and good, but nothing beats looking at some real examples. So let's go back to that ratings histogram example that we started off with in this course and break it down and understand exactly what it's doing under the hood and how it's using RDDs to actually get the results for the ratings histogram data. So the first couple of lines is just boilerplate stuff. One thing you'll see in every Python Spark script is the import statement to import Spark conf and Spark context from the PySpark library that Spark includes. And you will at a minimum need those two objects. The Spark context we talked about earlier, it's sort of the fundamental starting point that the Spark framework gives you to create RDDs from. And you can't create a Spark context without a Spark conf, which allows you to configure the Spark context and tell it things like, do I want to run just on one computer, or do you want to run it on a cluster, and if so, in what way? And the other bit of housekeeping from the beginning of our script was importing the collections package from Python, and that's just because we want to sort the final results when we're done. That's just standard Python stuff. Next, we actually create our Spark context, and this is going to look very similar in every Spark script that we write in Python. So let's look at what's going on here. We have the Spark conf object that we imported earlier, and we're telling it to set its master node as the local machine. So basically it says we're going to be running on a local box only, not on a cluster, just on this one system. And there are extensions to local that tell you to actually split it up among multiple CPU cores that you might have on your machine, but this is a very simple example, so we're just going to run it in a single thread on a single process, and that's what local means. So we're not really doing any sort of distribution of the data in this case. It's just sort of running on one process to keep it simple for now and kind of get the concepts across. Later on, we'll run more complicated jobs that actually use every core of your computer, and ultimately we'll run a job on a real cluster using Elastic MapReduce. Finally, we need to set the app name as part of this call. We're going to call this app ratings histogram, and that's just so if you actually look in the Spark web UI to actually see what's going on while it's running, you'll be able to look up the job by its name there and understand and identify it. Now, this job runs too quickly for you to even see it in the UI, so we're not going to worry about that, but it is good practice to give every app a name here. And finally, using that Spark configuration object, we create our Spark context object and assign that to something called SC. And by convention, we will always call that SC for Spark context. So now we're going to load up our data file. And if you remember from the previous lecture, a very common way of creating an RDD is through the sc.textFile method. So this is actually going to go out to our local file system and go to the ML100K 100,000 rating dataset from Movie Lens and load up the data file that includes all of the movie ratings data. Now, if you were to open up the u.data file in some sort of a text editor, it would look something like this, only with 100,000 lines. And what TextFile does is it breaks up that input file line by line so that every line of text corresponds to one value in your RDD. So the first value of the lines RDD is going to be this entire line of text, and the second line will be this line of text, and the third value will be this line of text, and so on and so forth. So if this were my entire u.data file, my RDD would consist of 5 values, where each value is a string that represents a line of text. Now later on, we'll actually break that up into what that string means. And that's what our mapper function does. So remember, the lambda sequence allows us to have a shorthand of passing some sort of function that we want to pass into our map. So lines.map lambda x, where x gets passed into split, and we extract the 2 number field. Now remember, in programming, we always start counting with 0. So what that's going to do in every line is take the line of input. It's going to split it based on white space individual fields. So running split on each line is going to result in a list of values of 196, 242, 3, and this big number. And what these numbers represent are the user ID, the movie ID, the rating value, and a timestamp. So the way to interpret the u.data file is user ID 196 watched movie 242, gave it a rating of 3 out of 5, and he did this or she did this at this particular timestamp, and that can be translated, into an actual human readable time. That's epoch seconds if you're curious. And the second field, if we count from 0, 0, 1, 2, is actually the rating itself. So what's this map function actually doing? Again, it's splitting up each line into its individual fields based on white space, and then it's taking field number 2, which is 0, 1, 2, the actual rating value. So for every line, it sucks out the rating value and puts that into a new RDD that we're calling ratings. So make sure you understand what's going on here. This is a very fundamental thing to understanding Spark. And if you need to hit pause and stare at this some more, do what you got to do, because it's very important that you get this concept. If you don't, you're going to have a hard time going forward. So understand that this little one line of code here is going to take every individual input line from our lines RDD, which contains the raw input data, split it up into fields, and we just happen to know that this means that user ID watched this movie ID, gave it this rating at this time, extract the rating, which is field 2, and put that into a new RDD called ratings. So we start with this, and after this map operation, the ratings RDD gets populated with these values. So our new RDD called ratings will contain 3, 3, 1, 2, 1, because those are the ratings values extracted from the source data. It's also very important to remember that the map function and all the action functions don't transform the RDD in place. So your lines RDD remains untouched. What it's doing is creating a new RDD called ratings, and you need to remember to assign the result of that transformation to a new RDD, or else it will just go nowhere. Very common mistake there. You can't just call lines.map and expect it to change everything in your lines RDD. You need to assign that result to a new RDD. In this case, we called it ratings. So if you got that, great, let's move forward. If not, again, hit pause, rewind, do what you got to do to understand this slide. Very, very important concept. All right, finally, we're going to perform an action on our RDD. So we've transformed the RDD into the form that we want. We've taken our raw input data and created an RDD that contains nothing but ratings as its values. So at this point, we call our ratings RDD includes just the rating values in our example 3, 3, 1, 2, 1. And now we're going to call an action method on that RDD, count by value. And this is a very easy way to cheat and very quickly create something like a histogram. What it does is it counts up how many times each unique value in the RDD occurs. So in this particular example, we know that the rating 3 occurs twice, the rating 1 occurs twice, and the rating 2 only occurs once. And that's the output we'll get. We'll get these pair values, these tuples, if you will, of rating and then the number of times it occurred. 3 occurred 2 times, rating 1 occurred twice, and rating 2 occurred once. And that's what will end up in our result object. And all that's left to do at this point is to print that out. Now this is an action, so it's actually returning, just a plain old Python object at this point. That's no longer an RDD, so we can do what we want to do in order to sort those results, which is the final thing we do. And this is all just straight up Python code. There's nothing Sparkish about it. All it's doing is using the collections package from Python to create an ordered dictionary that sorts those results based on the key, which is the actual rating itself. And then we're going to iterate through every key value pair of those results and print them out one at a time. So the output of this bit of code is going to be rating 1 occurred twice, rating 2 occurred once, and rating 3 occurred twice. That's all that's going on here. So we're taking those original key value pairs that were returned by count by value, and we are sorting them just using this boilerplate Python code. And I realize you may be new to Python, but if you look at this, it's pretty self-explanatory what it's doing. As we go into more exercises in the future, you can use a lot of these examples that we're going to give you to actually create what you need and piece together the pieces that you need to actually construct your own program. So kind of keep these snippets of code in your toolbox for future use. It's just that easy. So, we only had a handful of lines of code. Let's actually look at it as a whole again and take a look at that program all in one piece within Canopy and run it one more time just to reiterate what's going on. So now that we have a better idea of what's actually going on here, let's take another look at that ratings counter script as a whole. Go back to your Spark course directory there and open it back up in Canopy. And here we are. So again, here it is all together. Looks a little bit neater in here. So once again, let's review what's going on here. We're importing from PySpark the SparkConf and Spark context objects, and you're going to have that at the beginning of pretty much every Spark Python script that we write. We're also going to be using the collections object to sort our results, so we're going to import that now. Next, we create the Spark context object using a SparkConf that we create with a name of ratings histogram, and we're going to run it locally just on one process for now. Now, the magic of Spark starts happening here. We create an RDD called lines by calling sc.textfile, given an absolute path to our data file for the movie lens dataset. And again, that data file contains 100,000 rows, 100,000 lines, and at this point, every one of those lines will be a value in this lines RDD. Now, we're going to apply a map to that lines RDD and pass in a lambda function that splits out that line, breaking it up by white space and taking field number 2 out of each line. And again, each line of the u.data file represents a user ID, a movie ID, a rating, and a timestamp. So field number 2, given that we start counting from 0, ends up being the rating value from each line. So what this line does is it takes our lines RDD that contains raw lines of text from our raw input data and creates a new RDD called ratings, which contains only the ratings values from that input data. And now that we have our RDD transformed into the form we want, where every line, every value of the RDD is a rating value, we can call count by value to get a count of how many times each unique rating value occurs. And that gets output into a plain old Python object called results. And we can then turn around and use the collections package to sort those key value pairs of keys representing the ratings and values the count of each rating. We're going to sort those, and then we're going to iterate through each result and print them out to the screen. So just plain old Python code there, given the result generated by our ratings RDD when we called count by value on it. One more time, let's run this again just for good luck. Now that you know what's going on, it makes a little bit more sense. Spark Submit is just a tool that's part of the Spark framework that allows you to submit Python scripts to the Spark framework, and it does all the magic that needs to happen under the hood to make that actually run in a Scala environment for Spark. And we pass in the name of the script, ratingscounter.py, and off it goes. You'll see these warnings every time we run on our local machine here. You can safely ignore them, by the way. And there's our results. So once again, 34,000 4 stars, 21,000 5 stars, so on and so forth. And you can see now how that all happened. It was through the magic of RDDs. We started with one RDD that represented every line of our input data. We created a new RDD that just extracted the ratings from each line, and then on that RDD we used count by value to produce these final counts for each rating type. And then we just did some plain old standard Python code to sort and display those results when we were done. And that's all there is to it. All right, now you've not only run your first Spark program, but you actually understand how it works, hopefully. So let's start building upon that and do more and more complicated things with Spark and kind of work our way up to some more complicated examples. So next we're going to take a look at how Spark handles key value data, and we'll go into more depth on that next. All right, so we understand a simple example of using Spark. Let's build upon that and start doing some more complicated things. So a powerful thing to do with RDDs is put more structured data into it. So one thing we can do is put key value pairs of information into Spark RDDs, and then we can kind of treat it like sort of a very simple database, if you will. So let's walk through an example where we have sort of a fabricated social network set of data, and we'll analyze that data to figure out the average number of friends broken down by age of people in this fake social network. And we're going to use key value pairs in RDDs to do that. So let's cover the concepts, and then we'll come back later and actually run the code. Okay, let's build upon what we've learned about RDDs and extend it to a new kind of RDD, a key value RDD. And we're going to do this in the context of a real example where we're going to look at some fake social network data and try to figure out the average number of friends broken down by age for people. So RDDs can hold key value pairs in addition to just single values. In our previous examples, we looked at an example where an RDD included, for example, lines of text for an input data file, or an RDD contained movie ratings. So in those cases, every element of the RDD contained a single value, in that case either a line of text or a movie rating, but you can also store more structured information in RDDs. So there's a special case where you have a list of 2 items that it contains, and that is considered a key value pair RDD. And these are really useful things because once you start storing key value pairs in an RDD, it looks a lot like a NoSQL database. It's just a giant key value data store at that point, and you can do some things where you can aggregate information by key values, for example, and that can come in handy, for example, in this example we're about to do. So syntactically, there's nothing really special about key value RDDs. It's all kind of magic in Python. If you are storing a list of 2 items as your values in the RDD, then it is a key value RDD, and you can treat it as such. So here's a simple example. If I want to create a totals by age RDD out of a original RDD that contains a single value in each element, my lambda function here, x, can take each, say, rating, and then, or each number, whatever happens to be in x, and transform that into a pair of the original number and then the number 1. So the syntax with the parentheses just indicates that this is a single entity as far as Python's concerned, but it consists of 2 elements. It's a list of 2 things. And in this example, the first item will be the key, and the second item will be the value. And again, the key is important because we can do things like aggregate by key. And that's all there is to creating a key value RDD. And it's also okay to have complex things in the value there. So I could keep the key as being the original value here from the first RDD and make the value itself a list of however many elements I want to. So I'm not limited to just storing one thing in the value of a key value RDD. I can store a list of things there if I want to as well. And we're going to do that in this example too, just to illustrate how that works. So like I said, one of the most useful things you can do with a key value RDD is reduce by key. And what that does is combine all the values that are found for the same key value using some function that you define. So for example, if I want to add up all of the values for a given key, let's say all of the numbers of friends for a given age, just to pull that out of the air, something like this would do the job. So when you call a reduce function in Spark, it will get not just an x but also an x and a y value. You can actually call those whatever you want, but what you need to do is define a function that defines how to combine things together that are found for the same key. And in this case, our function is just x plus y, so it says we're going to keep adding things together to combine things together for a given key value. So, for example, again, if I was doing a reduce by key on a key value RDD where the keys were ages and the values were number of friends, I could get the total number of friends found for that age with something like this, because every value that's found for that key will be added together using that function that just has x plus y. There are other things you can do as well with key value RDDs. You can call group by key, so if you don't actually want to combine them together quite yet, you can just get a list of all the values associated with each key using group by key. And you can also do sort by key, so if you want to sort your RDD by the key values, that makes it easy to do. And you can also split out the keys and the values into their own RDDs using keys and values. Don't see that too often, but it's good to know that it exists. And like I mentioned before, you've kind of created a NoSQL data store here, right? It's a giant key value data store, so you can start to do SQL-ish sorts of things since we have keys and values in play here. We can do joins and right outer joins and left outer joins and cogroup and subtract by key. So these are ways to combine 2 key value RDDs together to create some joined RDD as a result. And later on, when we're looking at making similar movie recommendations, we'll have an example of doing that by joining one key value RDD with another to get every possible permutation of movies that were rated together. Now, this is a very important point with key value RDDs. If you're not going to actually modify the keys from your transformations on the RDD, make sure you call map values or flat map values instead of just map or flat map. And that's important because it's more efficient. It allows, getting a little bit technical, it allows Spark to maintain the partitioning from your original RDD instead of having to shuffle the data around, and that can be very expensive when you're running on a cluster. So anytime you're calling map or flat map on a key value RDD, ask yourself, am I actually modifying the key values? If the answer is no, you should be calling map values instead, or flat map values. And just to review, again, map values will have a one-to-one relationship. So every element in your original RDD will be transformed into one new element using whatever function you define, but flat map can actually blow that out into multiple elements per original element. So you can end up with a new RDD that's actually more, longer or contains more values than your original one with flat map values. Now, one thing to keep in mind is that if you're calling map values or flat map values, all that will be passed into your function that you're using to transform the RDD will be the values themselves. So don't take that to mean that the keys are getting discarded. They're not. They're just not being modified and not being exposed to you. So even though map values and flat map values will only receive one value, one value, which is the value of the key value pair, keep in mind the key is still there. It's still present. You're just not allowed to touch it. And I realize this is a lot to digest. It's going to make a lot more sense when we look at a real example. So let's look at a real example. Bear with me. So to get back to what we're going to try to do to illustrate these concepts, what I've done is generated a fake data set just completely at random, and it represents a social network. And what it has in it on every line is a user ID, a username, the age of that user, and the number of friends that user has. Okay? So for example, user ID 0 might be named Will, and he's 33 years old and has 385 friends. And these ages and numbers of friends are all completely assigned at random, so don't associate any sort of deep meaning to them. And you might notice that I'm a Star Trek fan here. So that's our source data that we're going to work with. And our task is to figure out the average number of friends by age. So for example, what's the average number of friends for the average 33-year-old in our data set? Well, let's figure that out. So our first step is just to parse that data into what we need. And, typically, nothing special here. We're just going to start by creating a lines RDD that is calling text file on our Spark context with our source data. And that's just going to give us an RDD where every individual line of that comma-separated value list is an individual entry in our RDD. And now things get interesting. So I'm going to transform my lines RDD into an RDD, very creatively named, by calling map on it. And I'm passing in the parse line function to actually conduct that mapping. So every line from my lines RDD will be passed into a parse line one at a time. And I'm going to parse it out. And first thing we're going to do is split it based on commas, and that will bust out the different fields we need. And I will then extract the fields that I'm interested in. So if I'm just trying to figure out the number of friends by age, all I care about is the number of friends and age information. The user IDs and the usernames are irrelevant, so I'm just going to discard those. So I will extract the age from field number 2, which is actually the third field because we start counting from 0, remember? And this is an important point here. I'm actually casting it to an integer value because I want to treat this as a numerical value. And that allows me to do arithmetic operations on it later. Now, if I didn't do that, it would just keep treating it as a string, and I wouldn't be able to do things like add them up and divide them, which I'm going to have to do if I want to get averages at the end of the day. Similarly, I'm going to cast the number of friends to an integer value as well, using the syntax int, in between parentheses. So fields 3 will give me back a string value of some number, and int will actually make sure Python knows that it's actually a number, and I should treat it as such, and I can perform arithmetic on it. And here is where we actually transform things into a key value RDD. So instead of returning a single value, I'm returning a key value pair of the age and the number of friends. So the RDD I'm creating with this parseLine mapper function is creating a new RDD that is a key value RDD with a key of age and a value of num friends. With me so far? So for example, transforming the original data that I showed in the previous slide, the output will be a key value pair RDD that contains something like this. So the first user in our data had an age of 33 and 385 friends. The second user had an age of 33 and 2 friends. The third user was 55 years old and had 221 friends, and so on and so forth. With me so far? This is an important concept to grasp, so feel free to hit pause and stare at the slide a little bit longer if you need it to sink in. Let's move on. All right, so now I'm going to throw you into the deep end of the pool here. Look at that big scary line. But if we break it down into its components, what's going on here is pretty straightforward. What we need to do next is aggregate this information somehow. So the first thing we're going to do, let's just break this down one component at a time. So you see we have sort of a compound operation going on here. We're taking our RDD of age and number of friend key value pairs, and we're calling map values on it. And then we're taking the resulting RDD and calling reduce by key on it. So let's take this one step at a time. We'll start with the map values piece of it. So what this does is transform every value in my key value pair, because remember we're calling map values, so the X that's getting passed in is only going to be the value piece of the original RDD. So let's take that first line for an example. The first entry in our RDD is an entry that has a 33-year-old that had 385 friends. So the value 385 gets passed in through map values for every line, and that's our X here in the lambda function. And our output is going to be a new value that is actually a pair, a list if you will, of 385 and the number 1. And the method behind our madness here is that in order to get an average, we need to count up all of the total number of friends seen for a given age and the number of times that age occurred. Okay, so later on, if we sum up all of these pairs of information, we will get the total number of friends for that age and the total number of times that age occurred once we look at the totals for a given age. So that's kind of our strategy here. Build up a running total of how many times 33-year-olds were seen and the total number of friends that they had. And that's what we're trying to accomplish. But to get back to the syntax here, just to review again, map values will receive each value, which in our case is the number of friends, and output a new value, which is actually a tuple that contains the original number of friends and the value 1. So again, this is an example of a key value pair that we end up with where the value is not just a single value or a single number, it's actually a collection of numbers, a list, and that's perfectly okay. So our output is a new RDD that is still a key value pair, but the keys are untouched because we call it map values, and the values are now transformed from just a number of friends to this pair value of 385 and the number 1. Now we need to add everything up together, and that's where the reduce by key part comes in. So again, reduce by key just tells us how do we combine things together for the same key. So again, going back to our example here, let's say that we're looking at every 33-year-old, so we're looking at keys of 33. Our lambda function here takes in 2 values and says how do we add them up. So for example, in this case we have X coming in as 385 and 1, and Y might be 2 and 1, and this just says add up each component. So take the first element of each value and add them together, take the second element of each value and add them together. And the output in this case would be 385 plus 2 is 387, and 1 plus 1 is 2. And we'll keep doing that repeatedly for every time we encounter values for the key 33 and add them all up together. So you see what we have at this stage is the grand total of number of friends and the number of times we saw that key for the given key, and it will do that for every single key. So that's what reduce by key does. And with that, we have the information we need to actually compute the averages we want. We'll do that in the next slide. But probably a good idea to hit pause at this point because even I had a hard time wrapping my head around this at first. So if you want to step through this through your head a little bit more, run through it in your mind, it might be useful. So go ahead and hit pause and let this sink in if you need to. Let's move on. So the last step is just to transform these pairs of total number of friends and number of times that key was encountered to an actual average value. And that's what this final line does with map values. Again, we're just receiving the value part of our key value pair into our lambda function because we're calling map values and leaving the keys untouched. So the age, in this example 33, will remain untouched and not even shown to us in our lambda function. But our lambda function will receive the value, which is this pair of total number of friends and number of times that age was encountered, and just divide the two to get an average value. So the output at this stage for the key 33 would be, we would transform 33 in this pair of the total number of friends and number of times 33-year-olds were seen to 33-year-olds had an average number of friends to 193.5. And now we have our final results. All we have to do is call collect to get them and print them out. Now, one thing I want to mention is that, remember, nothing actually happens in Spark until the first action is called. And if you go back to when we called reduce by key, that's actually the first action in our code. So nothing actually occurred in our script until reduce by key was called, which is kind of interesting. And the other action that we have in our script is this collect call. So at both stages, Spark will go out and actually construct that directed acyclic graph and figure out the optimal way to compute the answer we want. So again, that's the key to why Spark is so fast. And there we have it. So let's take a look at the actual code and dive in and actually run it and see what happens. Okay, so that's the overview of how we're going to use key value pairs in our RDDs to actually analyze our data set of our fake social network. And And now that we've walked through how that code's going to work, let's make it real. So in our next lecture, we're going to actually run this code for real on an actual data set. See you there. Okay, let's make it real. Let's actually get some real code and some real data and actually analyze the average number of friends by age in our fabricated data set here and see what we come up with. All right, so let's make this real. Let's actually run the script to find the average number of friends by age here. So at this point, you should go to the resources for this lecture if you haven't already and download two things. One is the friends by age Python script, and the other is the fakefriends.csv file, which is my randomly generated data that's completely fictitious, but useful for illustration. So go take care of that now. When you're done, move it into your C Spark course folder, or wherever you're installing stuff for this course, and come back when you're done. All right, so at this point in the course, your Spark course folder should look like this, and specifically we need friendsbyage.py and fakefriends.csv here. So let's double click on the friendsbyage.py script, and nthought canopy or your Python environment of choice should come up. And here we have it. So let's just review again what's going on here. So we start off with the usual boilerplate stuff. We import what we need from PySpark for Spark, and we set up a Spark context object that's just going to run locally on our own computer here on one process, and we're going to call it friends by age. All right. So first thing we do is pretty typical. We call text file on the Spark context to parse our input data, our fakefriends.csv file, and if you do have that in some other folder, make sure you modify that here first. And we will use that and put it into our lines RDD. And then we call our map function parseLines to transform our input data one line at a time into a new key value RDD. And again, what it's doing is splitting up the source data by the commas that are in it, extracting the age and number of friends from each line and casting them as integer values so we can perform arithmetic on them later, and returning key value pairs where the key is the age and the value is the number of friends seen for this individual. So at this point, we have a new RDD that contains key value pairs of ages and number of friends for each person in our data set. Next, we get to that big, long, scary line that does a bunch of stuff at once. And get used to this, because you see a lot of this in Spark where people kind of chain operations together like this. I just want you to get used to it. But just break it down one thing at a time, left to right. Figure out what's going on. For the first thing we're doing is this map values call. And again, map values leaves the keys untouched, so our keys, which are ages, will still remain, and only the values, which are the numbers of friends, get passed into our function here. So x, in this case, in our lambda function, is the number of friends for each individual in our RDD. And we're going to transform that into these compound objects, these tuples of number of friends and the value 1, so we can add those all up together later. So again, at the end of this, we have a new RDD under the hood where the key is still the ages, but the values are now these compound values of number of friends and the number 1. And then we need to aggregate everything together for each age. So reduce by key does that. It will gather all the values found for each age, which is our key value, and combine them together using the function that we provide. So again, x and y are two things that we're trying to add together for a given, or combine together for a given key, for a given age, and we're just saying by this function all I want to do is add up each component. So take the first element of each value and add them together, and take the second element of each value and add them together. So what we end up with is a new RDD where the key is still the age, because we're not messing with the keys, but the values are the total number of friends seen for each age and the total number of times that age was encountered. And with that, we have everything we need in the totals by age RDD to compute the averages. So our final transformation will take each value, we're going to call them map values. So again, our value at this point is a tuple, a composite value of total number of friends and total number of times that age was encountered, and it just divides those two values to get our average number, and that's our final result. So finally, we call the collect action on the resulting RDD, averages by age, and we just print them out. So let's see if it works. Let's go up to the Tools menu here and go to Canopy Command Prompt, or however you like to get to your command prompt. And we'll type in spark-submit friends by age.py, and off it goes. We'll get the usual warnings that we see whenever we run something locally. Safe to ignore, and we should quickly get a result. There we have it. So, this is all random data. There's really no meaning behind it that you can try to glean, but just through random luck of the draw, it turns out that 63-year-olds are pretty popular with 384 friends on average. So, there you have it, our average number of friends by each script, illustrating the use of key value RDDs and also the concept of storing more complex lists of information or composite values or tuples, whatever you want to call it, within the information that we're passing around. So, both very important concepts. Feel free to play around with this script, make it do something different, experiment, get your hands dirty. It's the best way to learn. All right, let's move on. All right, that's a second example now. Some real hands-on code there of using Spark on your own desktop. Got some real results there, and we've covered the concept of using key value pairs in RDDs and some of the special things you can do when you have key value pair data in an RDD. Very important concept. So let's move on to our next examples. Okay, so next we're going to introduce the concept of filters on RDDs, a way to strip out information we don't care about. And we'll do this in the context of another real example. We have some real weather data from the year 1800, and we're going to find out the minimum temperature observed for each weather station. So let's go through the concepts and walk through the code and get started. Okay, let's introduce the concept of filtering RDDs next. It's just a way to strip down an RDD into the information you care about and create a smaller RDD from it. It's pretty straightforward, but let's do it in the context of a real example. So we have some weather data from the year 1800 that I've gotten off the internet. And what we're going to do is try to figure out the minimum temperature observed at various weather stations in the year 1800. While we're at it, we'll also use the concept of key value RDDs as well as part of this exercise, so we'll reinforce that from the previous lectures as well. So filter is just another function you can call on a mapper. It transforms it by removing information, potentially, that you don't care about. And in our example, our raw weather data actually includes things like minimum temperatures observed and maximum temperatures for every day, and also the amount of precipitation observed for every day. But all we care about for the problem we're trying to solve is the minimum temperature observed at a given station for the year. So we need to apply a filter that just looks for weather data types of Tmin and allows those to pass through to our new RDD that we're calling min temps, but everything else, like Tmax entries or precipitation entries, will just get discarded. So we can take our parsed lines RDD, filter out anything that's not a Tmin entry, and construct a new min temps RDD out of it. So basically, filter takes a function that returns a Boolean value, true or false. If it comes back true, then that value is passed on to your new RDD. If not, it just gets discarded. It's just that simple. That's all there is to it. Another common example of using filter might be if you're processing log data from a website and you only care about analyzing certain types of events or certain types of transactions or maybe certain kinds of error codes. Filter is a way to strip out all the other stuff in the log that you don't need and then have a much smaller RDD that you can then work on more quickly and more efficiently. So let's take a look at our actual source data here that we're working with. This is real weather data from the year 1800. And the format of our data is a comma-separated list of values on each line, where each line indicates a given observation at a given day at a given weather station. And the format here is weather station ID. If I remember right, this corresponds to Paris and the Prague, followed by the date, and that's in year, month, day format, so 1800, January 1st in this example. And then the observation type, so here that's Tmax, so the maximum temperature observed on January 1st, 1800 for that weather station was -75, and that's actually in tenths of a degree Celsius, so that means -7.5 degrees Celsius was the maximum temperature observed on January 1st, 1800, and I believe that's Paris. Pretty cold day. And then we have a bunch of extra fields that are unused in this data set, and we can just discard those. So what we care about are the Tmin entries, because we're trying to figure out the minimum temperature observed for each weather station for the entire year. So again, for this line here, we'd have the weather station ID, the date, min temperature is the type of observation, -14.8 degrees Celsius was the coldest temperature observed, the minimum temperature on that date at that weather station. First thing we need to do is load that data up into an RDD, so we'll call text file on our Spark context and load every line of that input into a lines RDD. And we'll take that RDD that we called lines and apply our parseLine mapper function to it to create a parseLines RDD. So what that's going to do is split out our fields by commas, and then we'll extract the station ID text field, the entry type, which is going to be Tmin, Tmax, or precip, and we will then convert the temperature to degrees Fahrenheit because I'm a Fahrenheit kind of guy. I live in the United States. First thing we're going to do is extract the actual field, the numerical field of the temperature from the line. We're going to tell Python that is a floating point numerical value so it can actually perform arithmetic operations on it. I will first convert it from tenths of a degree Celsius to degrees Celsius, and finally apply this little bit of math here to convert from Celsius to Fahrenheit. And what I'm going to return is this composite value, this list that consists of the station ID, the entry type, tmin or precip, and the value of precip, the actual temperature observed. Okay, so basically I've parsed out my input data into something a little bit more structured, where the new values are these composite values that consist of a station ID, the entry type, and the temperature. Okay, so that's what my new RDD contains. One of these for every observation seen for every weather station ID on every day of the year. All right, now I'm going to call a filter on it. Now you remember that we stored the entry type in field number 1. We start counting at 0, so field 0 is the station ID, 1 is the entry type, 2 is the temperature. So if we see tmin in field number 1 of our value, we are going to let that pass. Otherwise, we will discard it. So what we're going to end up with here is a new RDD called min temps that contains only tmin entry types, observations. And the actual format of the RDD will be the same. We're still going to have station ID, entry type, and temperature composite values here, lists, if you will. But we're only going to have entry types that contain tmin at this point. Okay? So, given that everything in our RDD consists of tmin, we don't really need that tmin anymore, so we can strip those out now. And we're going to apply a new map to our RDD that does exactly that. So we're just going to transform every composite value to a new one that just consists of 2 values, which is the station ID and the temperature. And at this point, we have a key value pair in our new station temps RDD. Since we're down to just 2 values, our key is the station ID and the value is the temperature observed, which again at this point is in Fahrenheit. So at this point, for every day of the year, we have a minimum temperature observation for a given station ID. Finally, since we want to find the minimum temperature for the entire year for every station, we can call reduce by key to do that. So that's going to aggregate together every minimum temperature observed for every weather station ID, and our lambda function will determine how we do that aggregation. So we're saying that for whenever we try to combine 2 observations together for minimum temperature for a given station, we're going to call the min function to actually only take the minimum value between those 2. And as we keep feeding more and more observations for each weather station in there, only the smallest value, the minimum value, will survive in the end. So at the end, we have our final result. We have a min temps RDD that's going to be reduced by key. So all we have is 1 entry for every weather station ID that contains the minimum temperature observed throughout the entire year for each weather station. Finally, we need to call the collect action to actually kick it all off and make Spark go do something, and collect the results into a regular Python list called results. And we will just iterate through that and print them out. And we'll do a little bit of fancy formatting here. If you're new to Python, this is just saying that we're going to print the weather station identifier string followed by a tab character, and then do some formatting to ensure that the actual temperature is truncated to 2 decimal places to the right of the decimal point. And we'll stick the letter F at the end just to indicate that the result is in Fahrenheit and not Celsius. So let's go look at the code and actually run this thing and see what it does. All right, so that's how we're going to use filters to actually boil down the minimum temperature observed for each weather station, and we'll use the key values to do that and reduce by key to actually boil down the final results just like before. So let's dive into the code. It's going to make a little bit more sense when you see it all together. So let's take a closer look and actually run it and see what the answer is.